So very good morning to all of you. I hope you all are doing great. Good morning, good morning, good morning everyone. You just write in the comment section, is all fine or not? Is everything okay? Audio, video, everything fine? And after that we are going to start a very important topic of mechanical engineering, that is applied thermodynamic portion. In this portion, my dear, we are going to discuss power plant engineering, Brayton cycle, Rankine cycle, compressor, after that my dear turbine, all the type of compressor we are going to discuss, compressible flow, after that my dear refrigeration, and then IC engine, and then simply psychrometric. All these important topic we are going to cover in this session. So just before starting the session, you just write in the comment section everything fine or not. Malish, very good morning. Okay, yes, Surya, good morning, good morning. So once you share the session in your group so that number of your friend can join and we can start the session, my dear. Okay, yes, good morning, good morning. Join fast. Let me change the color of the pens. I think yellow will be good for you. Is it? Is this color good? Yes. Okay, great. So this is all about me. We are not stopping in this slide for so much of time. Yes. Before starting the session, let me share a few important information for you guys so that you can just take the benefit of this entire thing if you want. All India mock test is going to conduct on between 10th to 16th of July. You are having the time. If you are going to write the GATE 23, then definitely you must write at least once. Good morning, Naveen. Mega marks of 7 success mantra for the GATE 24 beginners. Date will be 15th of Jan and time will be 12:30. It will be conducted by Abhinav sir. Yes. Okay. Good. Good morning. Dheeraj sir is also in the session. Okay. After that, after the entire session of the applied thermodynamic, my dear, I'll just share my entire PDF of the class in this Telegram channel. You will get. Okay. So let's start the topic. So these 4 topics we are going to cover in this portion. One is the power plant engineering. Let me tell you, my dear, this is one of the biggest topic of the today's session. That is the power plant topic, my dear. Somewhere like, first of all, gas power plant we are going to discuss. Steam power plant we are going to discuss. After that, all type of compressor we are going to discuss. First of all, reciprocating compressor. After that, my dear, centrifugal compressor, and after that we are going to discuss the steam turbine, my dear. And in this topic of the steam turbine, we are going to discuss all the type of steam turbine, like impulse turbine we are going to discuss with the numerical aspect, impulse turbine, and after that we are going to discuss reaction turbine. And in the reaction turbine, my dear, we are going to discuss the special kind of turbine, that is the Parsons turbine. And Parsons turbine is also known as, can you please tell me the specific property of the Parsons turbine? In this Parsons turbine, there is a one important point you all know. So in this session, my dear, we are not going to cover only the theory or only the formula. In each and every topic, I am going to cover every formula, and I'll tell you how the question will be asked, how you are going to tackle these all the type of problem. Please write in the comment section. This Parsons time, sir, MSQ question may be asked in this case. No, not at all. No. Anyone else? Naveen, serious? Yes, this one is also known as, my dear, 50% reaction turbine. Okay, this one is also known as 50% reaction turbine. So let me tell you the topic which are very well known to you, like gas power plant, like steam power plant. We are not going to discuss these topic in so much depth, but topic which are not very clear to you, or somewhere you forget the formula or you forget the procedure, how the numerical will be asked in this portion, my dear, like reciprocating compressor, centrifugal compressor, impulse turbine and reaction turbine. Generally you are not going to go through these all the topic. You जल्दी ज्यादा से ज्यादा आप इसको भागने की ट्राई करते हो. Similarly, in this topic, I am going to discuss all the possibility of the area from which question may be asked related to the internal combustion engine or IC engine, like Mean effective pressure is a very important topic for all the IC engine topic, my dear. So in this way we are going to cover each and everything. Similarly psychrometric. So anyway, let's start the topic. Can we start now? अभी सो के नहीं उठे हो क्या? Are you all guys sleeping? Venu, good morning. You all guys are sleeping or you are in energy mode? Have you taken your tea? Yes or no? Okay, good. पता नहीं दिल भेज रहा है. Very nice. Okay. Because daily, my dear, day by day, you are just attending 6 to 8 hours of the marathon, and after that you are solving a lot of time. Then definitely it requires the very, very big amount of the energy. So you are just very nice. Okay, sis. Good. Okay. Chali. So let's start the topic. We are going to start from the power plant, my dear, and in the power plant, whatever we have written now, we will move forward in the same way. Okay. So introduction of the power plant. What is the ultimate purpose of the power plant, my dear? Ultimate purpose of the power plant is only the one thing, that heat must be converted into the work, and that must be converted into the efficient manner. So for this one, we require the three important process. One is four important process. One is the compression process, my dear. Second, it will be the combustion process, and then it will be the expansion process. Combustion, and then it will be the expansion process, and after that this will be the heat rejection process, either in the open cycle or it is the closed cycle. If it is the open cycle, then fourth component will be the atmosphere. If it will be the closed cycle, my dear, then fourth component will be the heat exchanger. So this is the simple function of the power plant. Generally, what work we are producing, that work is the turbine work, my dear. Okay. Let me tell you, Pintu, in this session we are going to cover each and everything like theory, formula, and utilization of the formula in the numericals, because generally you just mug up maximum of the formula, but when the question from the steam turbine is asked in the test series, when the question from the centrifugal compressor is asked in the test series, when the question from the reciprocating compressor is asked in the test series, you generally try to skip that question. So definitely in this session, I'll just more focus on each part, that how will you utilize these all the topic in your numerical portion. Okay. So the total work, or you can say net work, output, in this case will be generally written by turbine work minus of compressor work. These all things are very well known to us. Let's move forward to discuss each and every portion. Sir, first is the gas power plant we are going to discuss. Sir, can you please tell me what is the working medium in it? What is the working medium if nothing is mentioned? Definitely air. If I'll talk about the important process, then four process of this gas power plant, or simply you can say the Brayton cycle is there, my dear. One is the isentropic compression in the compressor. Yes. After that, constant pressure heat addition. After that, isentropic compression, and after that, my dear, constant pressure heat addition. Generally, in all these processes, whatever we have discussed, for example, if it is the compressor, my dear, then these all are the example of, tell me, these are the example of open or the closed system. Then definitely all the process are conducted in open system. So if you will write the numerical value of the work done in compressor, heat supply in heat exchanger, work done in turbine, and after that heat reaction in the heat exchanger, my dear, then answer of all the parameter will be nothing but change of enthalpy. Are you getting my point? Compressor, heat exchanger, turbine, and these all the points. No. We are coming on the same point. Yes, we are coming on the same point, and yes, I'll try to have one session based on the numerical part also, and I am very well known to this portion, my dear. Gas power plant is not a problem for maximum of engineers. I know very well. Rankine cycle is not a problem for the maximum of the engineer. The main problem is the turbine, my dear. Main problem is the compressor, and main problem is the centrifugal compressor. So definitely I am going to cover that part, that up to which part you have to You have to recognize, you have to just mug up the formula, utilization of the formula are covered. Then the gate question or at least question from this topic will be very easy for you. Come back. Yes, Pintu. Come back, sir. So, can I write the answer of each and every component, my dear? It will be purely related to the change of enthalpy. Can you please tell me that in this analysis, air can be assumed as an ideal gas, my dear? This is the assumption. Air can be assumed as an ideal gas. After that, if we write the total work in compressor, my dear, can we write the total work in the compressor? H2 minus of H1, that will be equal to MCP T2 minus of T1. You can't say no, because sir, in this topic of basic thermodynamic, my dear, we have already discussed that enthalpy is the function of temperature for an ideal gas. Yes or no? After that, if I want to write the heat supply, that also can be written like H3 minus of H2, that will be written by MCP T 3 minus of T2. Sir, don't write the formula only. Try to know the thing. कौन सी चीजें आपको दी होंगी, which parameters are okay. Let me move side. Okay, sorry. After that, what is the work in the turbine, my dear? That will be equal to H3 minus of H4. That will be equal to MCP T 3 minus of T4. So, let's draw the TS diagram. TS diagram is this one. Sir, can you please tell me what is the efficiency of the Brayton cycle? Yes. मैं side हो गया था. Don't worry. Yeah. What is the efficiency? Good morning, Umar. Efficiency of the Brayton cycle can be write like this. 1 minus heat reject divided by heat supply. That will be equal to 1 minus of heat rejection T4 minus of T1 divided by T3 minus of T2. Now you have to stop at this point and you have to analyze everything, my dear. Now you have to analyze everything. Okay. No issue. From next time, I'll just focus on this part. Sir, in this case, T1, T2, T3, T4 means my efficiency, heat supply, heat rejection, any question related to Brayton cycle is asked, then one thing is very sure for all of us, that sir, problem is purely related to the temperature of all point. Yes or no? Problem is only related to the temperature point. If we are able to know the temperature of each and every point, we are 100% sure we can solve every problem of the Brayton cycle. What do you say? Yes or no, my dear? Is it or not? Yes. So, exactly. So, in this case, let me tell you this T3 temperature. This T3 temperature, my dear, is the Tmax temperature, and the T2 temp or T1 temperature is the T mean temperature, my dear. These values are already given to us. Why, sir? In the numerical portion. Why, sir? Reason, minimum and maximum temperature of any cycle are fixed. These are never going to change. Maximum temperature is limited to the for the metallurgical problem, and minimum temperature limit is also the fixed due to the atmospheric condition. So always in the question, minimum and maximum temperature limit in any Brayton cycle is given to us. Good. After that, sir, if the cycle is the reversible cycle, for reversible cycle, my dear, reversible Brayton cycle, efficiency of the Brayton cycle can be written like 1 minus 1 divided by gamma minus 1 upon gamma. That is RP, my dear. Where the RP is the pressure ratio. Where the RP is the pressure ratio, my dear. But let me tell you, this is valid only when the efficiency of the compressor, efficiency of the turbine is 100%. Are you getting my point? This formula, whatever you have written in the last section now, this one will be the valid only for the case let me make this portion a little bit small so that each and everything will be known to us. Okay. अब थोड़ा ज़्यादा सही होगा. Is it? Now is everything fine? Yes. Now is everything okay na? Good. Great. So these all formula, this formula, my dear, it will be valid when efficiency of the compressor is 100%, efficiency of the turbine is 100%, and let me write one more point. Sir, effectiveness of all heat exchanger is also 100%. Okay? Is also 100%. So this formula will be valid only for this case. But this formula, my dear, will be valid for every case. Either the efficiency of the compressor is 100% or not. Efficiency of the turbine is 100% or not. Effectiveness of the heat exchanger is 100% or not. Sir, whenever efficiency, there are two formulas. Whenever the efficiency of the Brayton cycle is of the compressor and turbine is given to us, then you will be following the formula number 1. Are you getting my point? The biggest problem for the mechanical engineering in this type of question, what you do, whenever the compressor ratio is given to us, gamma is given to us, efficiency of compressor is given to us, blindly you will apply the second formula. Sir, if the efficiency of the compressor, heat exchanger, anything is given to us, you are not going to accept this formula. This formula is valid for number of important assumption. Getting my point? Are you getting this point from the simple Brayton cycle? When the efficiency of the compressor and turbine will be given, you will be go for one formula. When the efficiency of the compressor and turbine either not given or it is the 100%, you will go for the second formula. So second formula is valid only for few assumption, my dear. Good. Very good. Sir, my point is again, Naveen, the same. If you want to write something, you can write. Otherwise, you can download the PDF. The point is, whenever, sir, we know very well that this one is the compressor, this one is the turbine, is it or not? This one is the compressor, my dear. This one is the heat supply or the combustion chamber, you can say, heat exchanger. And this one is the heat rejection, that is the second heat exchanger. Are you getting my point? Yes, on that part I am coming. Don't worry. On that part I am coming, my dear. Now the question comes from here. Sir, what is the value of RP? RP की value क्या है? Means RP, my dear, here is known as the pressure ratio. Pressure ratio, and this pressure ratio is given by P2 by P1 like this. Or similarly, you can also write that T2 by T1 will be equal to P2 by P1 for adiabatic process raised to gamma minus 1 upon gamma, or RP raised to gamma minus 1 upon gamma, my dear. Okay. So in this case, the point is, if you are able to find the value of the pressure ratio, you will be able to find the temperature and pressure of all the points. Let's move forward and yes, find some more problem related to the work ratio. Sir, efficiency of Otto and Brayton formula is same? Yes. In the term of temperature, formula is same if the temperature, all temperature limits are same. If the all temperature limits are having the same numerical value, then they will have the same efficiency. Okay, come back, sir. In the power plant, your turbine work is somewhere like this 100%, my dear. Then out of the 100%, near about 40 to 60% of the work is go into the negative portion, and near about 40 to 60% of the work is go into the positive work done. Like if it is the 40, then this will be the 60. If it is the 60, then it will be the 40. So related to this one, there are few important points we must know. Generally, these topics or these questions are asked because, sir, from the temperature limits, you are able to find the work done, yes or no? You are able to find the work done of the compressor, work done of the turbine, heat supply and heat rejection. What do you say, my dear? Are you or not? क्या कहते हो, Naveen? From the simple Brayton cycle, are you able to find the value of the work done, value of the heat transfer, value of the work done by the compressor? Everyone? Yes. And generally, few questions are asked just only in the term with which you are not aware. Like one term can be given. What is the work ratio of this question? Even the similar question I have also asked in one session. So my dear, work ratio is written as, that is net work done divided by, my dear, positive this turbine work. What is net work done? Turbine work minus of compressor work divided by turbine work. It can be written, my dear, 1 minus compressor work divided by turbine work. One thing. Second term is also asked related to this one, my dear, that is known as back work ratio. Very nice, wonderful. Back work ratio, my dear. Back work ratio is also asked. That can be written as, that back work ratio means what is the work back to the system or negative work done. That is the work done in the compressor, and in this case this will be the work done by the turbine. That will be written as back work is equal to 1 minus work ratio. And let me tell you, back work ratio is near about 40 to 60%, my dear. 60%. For gas power plant, MSQ, very important question. Very important question for MSQ, my dear. And work ratio, back work ratio is only 1 to 2% for steam power plant. So I think I need not to write. What is the work ratio? Can you please write? What is the work ratio for the power plant? What is the work ratio for steam power plant? Anyone? Serious, Males? What is the work ratio for the steam power plant? I am waiting for the answer. Good. What is the work ratio for the steam power plant? It is near about 98 to 99%. Excellent. It is near about 98 to 99% is the work ratio. So these questions are asked, sir, you are able to know the work ratio, you are able to know the work done in the turbine, but indirectly he can ask like this, he can also ask like this. Okay, let's move forward. After that, sir, you know very well that my compressor is having the 100% efficiency, and after that, my dear, we get the answer from here. What is the efficiency we have got from here? Sir, this one. This was the efficiency we have earlier written, that efficiency of the Brayton cycle 1 minus Rp raised to gamma minus 1 upon gamma is the efficiency of the Brayton cycle. Now the question comes from here that, sir, if you will increase the compression ratio, if you increase, pressure ratio, then definitely your efficiency will increase. Yes or no? And if you will increase the gamma, my dear, then definitely your efficiency will increase. This is the gamma for 1.4. This is the efficiency having the gamma as 1.67. 67 you can say helium, and 1.4, my dear, you can say air. So this is the different value of the air and, my dear, helium, and you can check what is the efficiency, how the efficiency is going to increase. Generally this question is also asked. If I am using MSQ question, I am going to tell you, if I am using air, helium, monoatomic gas, diatomic gas, polyatomic gas in the Brayton cycle, then having the same pressure ratio, which gas will give me the maximum value of the efficiency. This question is asked generally. Are you getting my point? So from this topic, what we are getting, my dear, as the compression ratio is increasing, as the pressure ratio is increasing, the efficiency is also going to increase. So let's increase the pressure ratio and decide all the parameters from here. Very good answer. Yes, absolutely right. Naveen, yes, great. Now the next question will be asked. Topic is changed, my dear. Till now, whatever you have discussed, that is only related to the simple Brayton cycle, my dear. After that, next question is asked, what is the limiting condition for the maximum work? Sir, can you please tell me what is the purpose of the power plant? To produce the work power output? Are yes or no? What is the purpose of the power plant? Either you are using the gas or you are using the steam. To work or the power output? Yes, power output. So can you please tell me what should be the condition, of the power plant at which your power plant must run to produce the maximum power output? ज्यादा से ज्यादा पावर आउटपुट प्रोड्यूस करे, कुछ ऐसा पावर प्लांट बना सकते हो? यस सर. रीजन, we have already known that if I will increase the pressure ratio, my efficiency will increase. But up to what limit? Because you know very well, as the pressure ratio increase, my dear, yes, I am coming on the same point. Yes, as the pressure ratio increase, let me tell you, efficiency will definitely increase. But my dear, what the net work done? First it will increase, my dear. Then, my dear, it will be maximum, and then it will start to decrease. Are you getting my point? So in this case, this T3 limit is the maximum. In this case, this T1 limit is the minimum. So you have to adjust your T2 and T4 in such a manner, my dear friend, so that you can produce the maximum amount of the work done. Let's see what are the important result. Sir, if you want to find the condition, then first of all, condition for the maximum work done, intermediate temperature T2 and T4, these must be geometrical mean of T1 and T3, and T1, T3, my dear, maximum and minimum temperature. I'm not going to write it again. Clear? Okay. Second, sir, what is the work done at this stage? Can we write the work done at this stage will be equal to T max, that is the T3, minus of T mean raised to square. Second important condition. What is the condition of the efficiency at this time, my dear? Can you please tell me what will be the efficiency? That will be equal to 1 minus of under root of T mean divided by T max. After that, what is the optimum pressure ratio at this point, my dear? That will be equal to T max divided by T mean under root raised to gamma upon gamma minus 1. Can you please tell me how many of you, yes, how many of you, my dear, are aware with these all the points? Please write in the comment section. Everyone know the condition of the maximum work output. And after that, my dear, what is the relationship between the R optimum, very nice, wonderful, and R optimum, that can be written by R maximum. And my dear, R maximum is nothing but, let me write, R maximum is equal to T max divided by T mean. Okay, let me give you one important point for this gas power plant, my dear. Believe me, if you are very well aware with these 3 points, then definitely you can solve each and every problem of the Rankine, Brayton cycle. First, sir, first important point, that T1 is the minimum temperature. It will never be mentioned in any question that one, yes. Okay. In compressible flow, my dear, I am going to cover everything in a very detail. Don't worry about this. Yes, sir. Sir, Umar. In this case, I must know that T1 is nothing but minimum temperature. T3 is nothing but maximum temperature. Means after the combustion chamber, what temperature I am having, that is the maximum temperature. If you are aware with these 2 points, and compressor or the pressure ratio is utilized only for the adiabatic expansion and compression process in the Brayton cycle, then you are able to find the temperature of all the limits, my dear. Yes, exactly. These are some limit for this one. This maximum work condition, my dear, we are only able to drive whenever all the process are 100% reversible. You are not allowed to apply the condition of the maximum work when the compressor is not having the 100% efficiency, turbine is not having the 100% efficiency. Getting my point? When the turbine and compressor and heat exchanger, everything, sir, whatever you are driving now, that everything is valid for the 100% reversibility of all the component. Okay, good. This formula, all the formula will be applied when it is clearly mentioned in the question that you need to drive only for the maximum work done, my dear. Sir, maximum work done आपको drive करना हो, then you can drive these all the formula. After that, let's come to the regenerative Brayton cycle. Sir, now, till now, you have decided some limitations or some special condition of the maximum work. After that, you want to do the modification. Yes, exactly, Sruth. Yes, in this case, we are doing some modification so that either you want to increase the efficiency, my dear, or you want to increase the work done, or you want to increase both. What is the modification? Because these are the modifications, like you are doing the regeneration in the Brayton cycle, you are doing the intercooling in the Brayton cycle, you are doing the reheating in the Brayton cycle. These all are the modification in the simple Brayton cycle, whatever we have discussed till now. So why these all the points, my dear, there? These all points, why there? Because you want to increase either efficiency, you want to increase either work done, or you want to increase both. It is up to you. So let's see. If first of all, what is the regenerative cycle? It is the exchanging of the energy between the hot gases after the turbine and the cold gases after the compressor, because cold gases require after the compressor some heat, so that in the combustion chamber less heat will be required, and hot gases, when they are just releasing to the atmosphere, they require to reject some heat, so that less loss of energy will be there into the atmosphere. Sir, this is the exchange portion. After that, let's come to the point. What is, very good morning Sahu. After that, what is the meaning of this regeneration? We are 100% able to understand. After that, let's know what is the effect of the regeneration. Sir, best and the most important question for the MSQ, whatever we are going to write, most important question of the MSQ, my dear. What is the value of the net work done, my dear? Constant. It is not going to change. Yes or no? But what is the heat supply in this case, my dear? Can you please tell me? Increase or decrease? Heat supply. What is the heat supply? Definitely it will decrease. Yes, exactly. No, both are not interdependent. And what is the efficiency? It will 100% decrease. So these are the questions may be asked to us. Yes, these are the questions, my dear, may be asked to us, that what is the compressor work, what is the effect on the turbine work, what is the effect on the net work, what is the effect on the heat supply, or what is the effect on the regenerative efficiency in this case. Regenerative efficiency in this case. And after that, let's come to the numerical part, sir. Again, the numerical portion is the same, that T1 and T3, my dear, is also T1 and T3 is also the fix. You have to keep one point in mind, that whenever minimum and maximum temperature is given, that is nothing but T1 and T3, my dear. Okay. Because name of the temperature will never given, like this is the T1, T2, T3. You must know in most of the problem. Yes, heat rejection will also decrease. Absolutely right, Chaudhary. Heat rejection, my dear, will also decrease. After that, let's come to some numerical portion, sir. For regenerator, we must know the effectiveness of the regenerator will be written as actual heat transfer. What is the actual heat transfer? T5 minus of T2 divided by ideal heat transfer, T4 minus of T2. or it can be written by T4 minus of T5 heat rejection, sorry, T6 divided by T4 minus of T2. Now you can't ask, my dear, I have already drawn this regenerative cycle. Sir, 1 to 2 is the compression in the compressor. 2 to 3, my dear, 2 to 5, it's a regenerative cycle, means in this regeneration. 2 to 5, this. If regenerator was not there, then this process was not conducted at that time. Are you getting my point? After that, 2 to 3 will be the process at that time. So 2 to 5, I have added this amount of heat in the regenerator. So are you not feeling only this amount of the heat will be supplied in this case of the, okay, good. No, it will be T4 minus T2. Sir, what is the effectiveness in the HMT you have already discussed? Yes, I am coming on the same point. Don't worry. Yes. I am coming on the same point, sir. First of all, Chaudhary, your question. First of all, you know what is the basic TS diagram of the Brayton cycle? Yes. Simple Brayton cycle, I am very well aware with the simple cycle. Okay. 1, 2, 3, 4, my dear. This one. This is the simple 1, 2, 3 and 4. But between the compressor outlet and, my dear friend, combustion chamber inlet, I have added one regenerator. So half of the heat I will take, half, 50%, 30%, 20%, I will take from the regenerator, and other portion I will take from the combustion chamber. Similarly, in the starting, when regenerator was not there, then heat rejection was 4 to 1, my dear. Chaudhary, yes or no? After that, a little bit amount of the heat I am going to reject in the regenerator. So this heat is not the rejected to atmosphere. This is the inter-exchange. Are you getting my point? This heat is going to supply here, my dear. So it is going to reject the heat to this one. So this is taking the heat, and temperature of 2 will be increased by 5. Temperature of 4 will be increased by 6. Are you getting my point? Yes. So what is the effectiveness? Now it is the question. What is the effectiveness? Effectiveness in the heat exchanger, topic of HMT, give you the idea that, my dear, temperature or, my dear, total effectiveness will be equal to actual heat transfer. What is the actual heat transfer? T2 is going to increase by T5. T5 minus T2 is the actual, divided by ideal heat transfer. What is the ideal heat transfer? Total heat transfer must be equal to T4 minus of T2. This is the ideal. T4 temperature working medium is coming from here. T2 temperature working medium is coming from here. I want to check what is the maximum heat transfer. That is the temperature difference of both. T4 minus T2. If it is the infinite body. Are you getting my point? So this is the ideal temperature. Similarly, what is the heat rejected, my dear? In this case, that will be equal to T4 minus T6 divided by ideal temperature. Now, after that, for perfect regeneration, exactly, for perfect, my dear, regeneration, the efficiency of regenerative Brayton cycle can be written as 1 minus T minimum divided by T maximum into Rp raised to gamma minus 1 upon gamma. Sir, you have to mug up these type of formula. ये formula आपको बहुत अच्छे से याद करने की जरूरत है. You need to mug up these type of formula because there is no other option of these type of problem. Because the question are generally asked that if the pressure ratio of the simple Brayton cycle is given to us, minimum and maximum temperature is given to us, then what is the efficiency of the simple Brayton cycle? What is the efficiency of regenerative Brayton cycle? Sir, first question I am going to tell you from the regenerative question, regenerative topic, what may be the first quality of the question, first topic of the question. In that part, he will ask what is the effect of the regeneration. Is it clear? In the MSQ, he may ask what is the effect of the regeneration. Second question, he may ask what is the total effect or what is the overall efficiency of the system. And third and last question, he may ask from the topic, my dear, that what is the compression pressure ratio and the efficiency of regenerative cycle. This is the pressure ratio. The next question he may ask like this. So this is the efficiency of regenerative Brayton cycle. So you know very well that efficiency of the simple Brayton cycle increase with the pressure ratio, but the efficiency of regenerative Brayton cycle decrease with the pressure ratio. Sir, first all the questions, theoretical, numerical questions are clear to us? Yeah, definitely. Everything we are going to discuss, don't worry. First tell me, related to the regeneration, how the question may be asked, how we are going to tackle these all the questions. Are you able to solve? Theoretical question I have already discussed. This question I have discussed. Sir, each and every point you need to discuss. Yes, what we mean, my dear? Yes, Surut. According to Surut, there is a one question. Sir, for the perfect regeneration, what is the effectiveness or what is the meaning of T4 is equal to T2 or T2 is equal to somewhere like this? Come back to the point, sir. Sir, in this case, you check it very clear. If the effectiveness of the system will be 1, then my dear, this will be the 1. T2 and T2 will be cancelled. Then in that condition, T5 will be equal to T4 and T6 will be equal to T2. What is the meaning of this? If the effectiveness of the regenerator will be the perfect or the 1, then at that time the temperature after the regenerator will be equal to temperature before the regenerator. Getting my point? Yes. Okay. Yes, good. Let's move forward. Already regenerative Brayton cycle we have discussed. Efficiency we have already written. Sir, Brayton cycle after the intercooling. Brayton cycle, generally you are using more than one compressor to increase the net power output or to decrease the negative work done. Compressor work done will be decreased when you are using the intercooling between the compressor. So negative work will decrease, total positive work will increase. If I draw the cycle, then my dear, if I want to increase the pressure from P1 to P2, my dear, this is my requirement. Okay, this one is my requirement. In that condition, I can directly write, my dear, that my compressor work will be written like somewhere like this, something like this. Okay. After that, if I'll ask the first theoretical question from the section, effect, what will be the effect on the intercooling? Can you please tell me what is the effect on compressor work? Sir, the most important question for MSQ. Compressor work decreased, turbine work constant, not going to change. Can you please tell me network increase? Can you please tell me heat supply? First of all, it was the heat supply. Right now it is the heat supply. Yes. You can get the value. You can just compare both the efficiency. You substitute the value, you will get the answer. Sir, efficiency of the simple Brayton cycle is, good morning Ram, simple Brayton cycle efficiency is 1 minus 1 upon R raised to gamma minus 1 upon gamma. Already we have written the efficiency of the regenerative Brayton cycle. Compare both, you will get the answer. So heat supply, definitely it will increase. After that, can you please tell me overall efficiency, my dear? Next question, can you tell me overall efficiency? Decrease, na? So after that, sir, Rishikesh, very good morning. Yes, no, it will decrease. Okay, because the mean effective temperature will decrease at the time of heat supply. Quality you are going to supply in this case is having the lower quality, my dear. Low quality of the heat you are going to supply. That's why overall efficiency will decrease. After that, what is the net work done? Can you please write? What is the net work done? MCP Turbine work, what is the answer? T5 minus of T6 minus of T4 minus of T3 minus of T2 minus of T1. What is the heat supply, my dear? Yes, yes. We are talking about the compressor, not compressor, plant efficiency. After that, what is the overall efficiency? It will be equal to W net divided by heat supply. Okay. W net divided by heat supply. So again, are you not getting the parameter? What exactly we need to find numerically? Each and every parameter is again the function of temperature. Or yes or no? Each and every parameter is purely the function of temperature, and already from the starting we are very well aware to find the value of the temperature. Let's come to the next point. What is the condition in this case for minimum work required, my dear? What is the condition? Minimum work required. Anyone? What is the condition for this minimum work required by the compressor? Whenever both values are increasing, then at that time you just compare all the parameters. You compare all the parameters with the quality of the heat supply or the quality of the heat rejection. Because let me tell you, when you compare the efficiency with the numerical value of the work done and the heat supply, then you get the answer when one thing is increasing and second is decreasing, then only numerically you get the answer. But overall, why you are getting the more work from the less heat? The point is only one, that you are going to supply the high grade of energy, high quality of the energy. So mean temperature in this case decrease at the time of heat supply. That's why your overall efficiency decrease, my dear. Okay. Yes. Yes. For minimum work done, there must be perfect intercooling. What is the perfect intercooling? That in the second compressor, my dear, yes. In the second compressor, when your working medium is going, that is T3, must be equal to T1. After that, the few star points are there. That one condition is this one, T1 is equal to T3. Second condition, intermediate pressure must be equal to geometrical mean of P1 into P2, like this. After that, work done of compressor 1 is equal to work done of compressor 2 is equal to MCP T1, my dear, and under root of P2 by P1 under root of gamma minus 1 upon gamma minus of 1. Clear to all? And in this case, the total minimum work done will be equal to 2 MCP T1. It will be equal to under root of P2 divided by P1 raised to gamma minus 1 upon gamma minus 1. Sir, again, let me tell you, if you say now that I am not good in solving the numerical of the power plant, it means you are having the 100 of formulas. You are having the 100 of important key points. You are not able to revise all the points. You are not able to recall all the points and formulas at the time of exam, at the time of test, whatever you are writing, my dear. Either you believe or not, but most of the time you feel, sir, मुझे formula ठीक से याद नहीं आ रहा. It was the under root P2 by P1 or it was only P2 by P1. It was gamma minus 1 upon gamma or it was gamma upon gamma minus 1. You are having the doubt like this only at the time of numerical. So again in the Brayton cycle, that is the reason I am going to justify each and everything whenever we are going to discuss. Will you accept or not? ऐसा हुआ है कभी problem में? Okay. Serious. Somewhere I am feeling the problem in numerical, but theoretical part is very theoretical part I'm feeling the problem, but numerical part is very clear to us. So let me tell you, Raghu is facing the same problem, Malis is facing the same problem. Serious, let me tell you very honestly, sir, if you are going to write the GATE exam, then in the GATE exam, theory of this entire thermal hardly asked 1 to 2 marks. Hardly asked 1 to 2 marks, right? Major portion you must have the command over the numerical portion, must have having the command over the numerical portion, and especially over the numerical portion. In this applied thermodynamic, my dear, you must focus related to the steam turbine, you must focus on compressor, all type of compressor, right? Because let me tell you, these Brayton cycles, these Rankine cycle, most of the engineers bug up the formula 100 of time. But when they start from the Brayton cycle, they go to the this Rankine cycle, वो इतने ज़्यादा थक जाते, the engineers are so much tired that they leave, they don't try to, they don't dare to check the steam turbine, check the centrifugal compressor, check the reciprocating compressor. So again and again, when the students start to revision of these power plant topic, my dear, they start with the Brayton cycle with full lot of energy. After that, Rankine cycle, energy a little bit less. After that, as the turbine will come directly, energy will be negative. नहीं अब कुछ नहीं हो पाएगा. And in the compressor, my dear, 0 पहुंच जाते हैं. Okay. No. I have not started all the cycles, my dear. I have just started with the Brayton cycle. We are discussing the Brayton cycle. All other cycle are yet to come. Don't worry. All other cycle we need to discuss, my dear. Yes. Okay. Good. Siddharth. Good. Sir, that is the reason in each and every problem I am going to tell you that one is the numerical aspect of that topic, and second one, my dear, is the theoretical aspect of this topic. Sir, this one is the theoretical aspect of this intercooling, and this one is the numerical aspect, and this one is the spatial aspect. What is the spatial, sir? Spatial aspect means you are having some spatial condition. Otherwise, let me tell you in general way, somewhere write this point in your mind or heart, that in general way, when I say it is a basic term, then answer of all the basic term in the Brayton cycle is only the temperature term. If you are able to know the temperature of all the points, you will be able to know each and everything. If it is a basic question, when it is some special question means you need to find maximum work. A special word is added, maximum. You need to find minimum work required. A specific word is added, minimum condition. At that time, definitely a lot of condition you have to discuss, you have to know. But if nothing is mentioned, my dear, then answer of each basic question will be the answer of change of enthalpy or change of temperature. That's all. Good. I'm coming. I'll just revise after the repeat each and everything after the completion of this. Let's complete everything first of all, and after that we are coming on the topic, my dear. Good. Sir, reheating. Reheating. Like in the intercooling, you are doing the reheating, my dear. And if I will check all the effect of the reheatings, again, theoretical question related to reheating. First of all, my dear, what is the turbine work? Sir, it will increase. What is the compressor work? Sir, it will be same. Yes or no? Sir, what is the heat supply, my dear friend? It will definitely increase. What is the efficiency? It will definitely decrease. Because again, heat or the temperature of the heat supply, mean effective temperature of the heat supply decreases. So in the Brayton cycle, either in the reheating or in the intercooling, efficiency does not increase. Efficiency increase only in case of regeneration. When you are doing the regeneration, very good morning, Karthike. Yes, no issue. Because your important part is yet to come. Don't worry. Sir. After that, let me write the important points. What is? Can I ask what is the value of the turbine work from here? Let's discuss some numerical portion. Sir, Can you please, what is the turbine work from here? So turbine work can we write mCp T3 minus T4 plus T5 minus T6. Similarly, can we write compressor work mCp T2 minus of T1. Can we write heat supply, my dear? Heat supply can be written by, how much is the heat supply? One heat supply is here, then mCp plus of T5 minus of T4. And efficiency will be equal to turbine work minus compressor work divided by heat supply. After that, let's discuss some special condition. For maximum turbine work. Condition for maximum turbine work, my dear. Anyone are aware with this topic? First, perfect reheating. Perfect reheating. Exactly. First condition is the perfect reheating, that T3 must be equal to T5. What is it? After that, work done in turbine 1 must be equal to work done in turbine 2, and this must be equal to, my dear, mCp. T3 is a common. Then 1 minus under root of P1 divided by P2 raised to gamma minus 1 upon gamma. Or, my dear, total net work done of the turbine maximum will be equal to 2 mCp. T3 is the answer. 1 minus under root of P1 divided by P2 raised to gamma minus 1 upon gamma. After that, what is the condition? P intermediate will be equal to under root of P1, P2, where P2 is the pressure of the second compressor, like this, second turbine. This one is a P2 pressure maximum, and this one is the P1 pressure in that turbine. If you want to draw the TS diagram, it is not required, but you can draw if you want. That TS diagram can be drawn like this. Sir, 1 to 2 compressor. All of you, 2 to 3 heat supply, 3 to 4 one compressor, 4 to 5 second compressor, 5 to 6 and 6 to 1, my dear. Are you getting my point? So first requirement, this temperature must be same, my dear. Second, this is P2 pressure, this is P1 pressure, this one is PI pressure. Sir. Yes, only the effective when they are combined with the regenerator. Absolutely right. Yes, Chaudhary. Absolutely right. So this is all about the modification in the simple Brayton cycle. When you are modifying your simple Brayton cycle, what is the theoretical change? What is the numerical change? You need to find, sir. Now let me summarize everything whatever we have discussed till now in previous 1 hour, my dear. First of all, we have started with the simple Brayton cycle, where you need to find the numerical value of the work done by the compressor, work done by the turbine, work done or heat supply, heat rejection, efficiency. Simply answer of all parameter you have found in the term of temperature. Numerical question. Pure numerical question. Second, my dear, what is the numerical value of the efficiency of the Brayton cycle in general and for the reversible cycle? Yes. Third, when you want to find the condition for the maximum work, 4 important result, purely numerical topic. After that, regenerative cycle, on one hand you are having the theoretical question, what is the effect on this parameter of the regenerative cycle. Numerical, on the other hand, you are having what is the total value of the work done in the regenerative cycle. What is the overall efficiency in the regenerative cycle. After that, intercooling. What is the effect of the intercooling? All theoretical question for MSQ. Numerical, what are the value of the work done by the compressor, work done by the turbine, or total work done, heat supply, or the overall efficiency. And last special question from this topic of the intercooling, what is the condition for minimum work required? That T1 must be equal to T3, intermediate pressure must be geometrical mean, intermediate must be the geometrical mean. After that, first compressor work must be equal to second compressor work, and after that, my dear, yes, after that, total work done will be the double of both the compressors. Similarly, for the reheating, on one hand you are having all the theoretical question, on second hand you are having all the numerical question. You must know what is the general formula of the work done by turbine, work done on the compressor, heat supply, and overall efficiency. But at last, my dear friend, you all are having the condition for maximum turbine work, these all. Yes, now question is, sir, is to mug up these all the formula, or if we are aware with the all formula, are we able to solve the numerical? Answer is no, because already I have told you that in the question, because if अगर सिर्फ आप अगर सिर्फ और सिर्फ फॉर्मूला से क्वेश्चन कर पाते, then it will be better I'll directly give you the PDF, that this will be the formula, I rewrite and I directly give you the PDF. Here during the session I am going to tell you that this value will be given in the exam with which name. I've already told you in all the Brayton cycle, most of the time minimum and maximum temperature is given to us, not like T1, T2, T3, T4. Now you need to understand that maximum temperature is T3 and minimum temperature is T1. You have to recognize this. तो आप इनसे भी aware होने चाहिए, then and only then you can solve the question. And these all the things whatever we have discussed, these are valid up to when efficiency of the compressor and turbine is 100%. Are you getting my point? Because if the efficiency easily, and let me tell you, you need not to remember these all the formula. What you need to do, you need not to read these all the formula. What you need to do, whatever we are writing here, whatever we are discussing here, you just, I'll share the entire PDF in my Telegram channel, my dear. उसके बाद में आपको क्या करना है, serious and all my dear friend. After that, you just start your day, take 1 hour to write everything. You will hardly in 1 or 2 hours, you will complete one subject, short notes, like this. All the formula, all important point, every point, you rewrite everything in the rough way. Then you start, you just make your plan in such a way that every day, आज उत्कर्ष नहीं है, otherwise उसको मैं बहुत पहले बताया था, तेजू and उत्कर्ष, yes, that you follow the same thing. Okay, good. So if you follow the each and everything somewhere like this, that every morning I'll start my day at least one subject, rewrite everything whatever we have written in the short notes or in this PDF. If you are not having the short notes, then if you will follow these entire thing, my dear, then after 20-30 days it will be the time, it will be the situation or condition of you that you will be easily able to write each and every formula, even if you will close your short notes, even if you will close your proper notes. You just start from one point and directly each and every formula will be written by you on the notes without any problem. Okay. Next, sir, after the reheating, what will happen if these all the system are not having the 100% efficiency? All the system are not having the 100% efficiency, then efficiency will not be 100%. It means, sir, again all parameters are given to us to solve the numerical. Means you can say in the question T minimum is given to us, that is in the form of T1. T maximum is given to us, my dear, that is in the form of T3, and R P is also given to us. But with this one, efficiency of the compressor and efficiency of the turbine is given to us. Are you getting my point? These all numerical parameters are given to us in the question. It is the indication that you have to solve these type of problem, not by the general formula, whatever we have studied till now. Everything must be changed. So in this case, first of all, if I'll write isentropic efficiency of turbine, my dear. And from this point, one thing is very clear to me that you all guys are able to find T1, T2, T3, T4 from these all parameters. Yes or no? T2, T3, T1, T4, everyone can calculate. After that, if the efficiency of the turbine is given, can we write W actual of the turbine divided by W ideal of the turbine? All of you? Yes. What is the W actual? That will be equal to T3 minus of T4 dash divided by ideal T3 minus of T4. Sir, after that, T3, T4 and efficiency of the turbine is known to us. Can we write here from here isentropic efficiency of compressor that will be just reverse, my dear. Ideal divided by actual. What will be the answer? Ideal T2 minus of T1, that is the ideal, and T2 dash minus of T1. Sir, can you please tell me from here, are you able to find the numerical value of T2 dash and T4 dash? How many of you are sure if the actual efficiency of the compressor and my dear turbine is mentioned in the question, are you able to find the actual value of the T4 dash and actual value of the T2 dash in this given question? How many of you are sure? T1, T3, RP, efficiency of compressor and turbine is given to us. कुछ हलचल मचाओ in comment section if you are able to write, able to calculate the numerical value of the T4 dash and T2 dash. Umar, yes. Ram, only two of you are able to find. Sure, Umar, only Umar. Truth, Shreyas, you can't find. Good, great. Sir, after that, in that case, every question will be written like this, that now it will be the question of actual work, my dear. Yes, yes. Now it is the question of actual work. Actual work means direct the difference of temperature, like T3 minus of T2. What is the work done of turbine? Like direct difference of, sorry, compressor work I have written wrongly. Compressor work I have written wrongly, my dear. T2 dash minus of T1. Similarly, if you want to find the heat supply, so from here again you are able to find each and every parameter. In this case, without any problem, if you are able to find the temperature limit of all the questions, all the parameters. After that, sir, what will be the energy balance equation on the combustion chamber? From here, generally air fuel ratio is to calculate. Sir, this one is the combustion chamber. No, Chaudhary, not. Sir, the working medium is entering with the mass of Ma. Energy from this is coming with the fuel of this, and energy is going out with the mass of Ma into Mf at a temperature of T3, my dear, at a temperature of T2. Table, are you talking about the steam table? Serious? Are you talking about the steam table? Sir, if there is the efficiency of the combustion chamber like this, so I will write the energy balance equation. MA is coming with Cp at a temperature of T2, mass of the fuel is coming with the calorific value of Cv, and the efficiency of the combustion chamber is Cp, then my dear, Ma plus of M fuel is leaving the system with Cp at a temperature of T3. If I'll divide the entire equation by Mf, then my dear, Ma divided by Mf into Cp_T2 plus of Cv into efficiency of the combustion chamber will be equal to Ma divided by Mf plus of 1 into Cp and T3, my dear. So in this case, what you can do, you can find the value of the air fuel ratio. So whenever in the Brayton cycle, my dear, air fuel ratio is given now, blindly you apply the energy balance equation at combustion chamber, you will be able to find the air fuel ratio. Yes, for air fuel ratio, you always apply the energy balance equation in the combustion chamber and you will be able to find the air fuel ratio in the combustion chamber, sir. And again, let me tell you, if this is again related to actual cycle, then T2 will be again replaced by T2 dash, T3 will be okay. And in this way, efficiency of the combustion chamber is 100%. You are not going to mention the efficiency of the combustion chamber, that will be Cv, calorific value only. Now, there is one more question from serious side. Sir, can we know the steam table? Sir, even you need not to get anything from the steam table because you are not able to recall each and every value of the steam table. Sir, and again, let me change my statement. Steam table will also not given in the exam. Only the data which will be required. Are you getting my point? Only the data which will be required to solve any numerical value of the steam table, steam power plant or the refrigerant or the refrigeration, my dear, only that row of the steam table will be given to you. Okay, बस उतना ही data दिया जाएगा, directly that will be given. You must know what is the meaning of VF, what is the meaning of VG, what is the meaning of HF, HG, HCP, superheating region क्या है, saturated region क्या है. These all points are very well known to us. Then you will be able to find or able to solve each and every problem of the pure substance. Okay. Now, sir, there are two important topics are also asked. One is the air rate, that will be written by, my dear, 3600 W net kg per kilowatt hour, and second is the heat rate, that is just a reciprocal of overall efficiency of the Brayton cycle. Sir, this is the last of the Brayton cycle. This is the last topic of the Brayton cycle is generally asked. Let me tell you everything, whatever we have completed, let me revise for next 10 seconds and then I'll ask how many of you, sir, it is SSC. Come back now. First of all, air radius. Okay, come back. First, we have started with the simple Brayton cycle, efficiency of the Brayton cycle. Then after that, condition of the maximum work done, then regeneration, then intercooling, then reheating, then actual efficiency of the compressor and turbine. After that, my dear, to find the air fuel ratio on the combustion chamber, I have to apply the energy balance equation on the combustion chamber. And at last, my dear, what is the air rate and heat rate? First of all, you need to know, are you able to find each and everything? सारी चीजें clear हो गई हैं? Is it clear to everyone? Whatever we have discussed, 6-7 topic in the simple Brayton cycle we have discussed. Is it clear to everyone? Write in the comment section. All of you. You just send me a signal in the comment section. If each and everything is clear to us, then we can move forward, my dear. You just send me a signal in the comment section. Is everything fine till now? Okay. Again, Teju is back. 4 बूंदों वाला निर्मा सुपर पाउडर पता नहीं क्या है. Yes. Okay. Good. Very good. क्रिस्टल क्लियर. क्रिस्टल क्लियर से काम नहीं चलेगा रघु. You have to use these all the formula for numerical also. So you can do one thing, you just put this entire PDF one side and after that you check everything my dear. Okay, तो अगर क्लियर हो गए just like the session. उसके बाद सेकंड पोर्शन पे बढ़ जाते हैं. That will be the Rankine cycle or steam power plant. And let me tell you my dear, Rankine cycle or the steam power plant, you are not having so much of problem because already you have just completed the portion of the Brayton cycle, completed the portion of this enthalpy term. In the Rankine cycle, you are not going to face any problem. Yes, but I will definitely tell you, sir, if it is the question, then how will you tackle? If this type of question will be there related to the Rankine cycle, how will you tackle? Or which are the topic from where maximum possibility of the question is there? Definitely these portion I am going to discuss in that part. चलिए आगे बढ़ते हैं. Let's move forward. कोई doubt था स्रोत का? I could not read. Can you again write? शायद मैं ध्यान नहीं दे पाया. किसी को पता हो? If anyone else is able to read the answer, read the statement from Surut and able to write the answer, you please write. I could not. Okay. क्या था उसका question? Yes. Refrigeration, psychrometric, everything will be covered. But in this session, let me tell you very honestly, if you are going to attend the session, my dear, at least you will be aware, you will be able to solve the numerical of all the applied thermodynamic portion. Yes, because here I am going to discuss only those point or to the point which can be asked in the exam, my dear. Yes. Okay, let's start. Let's start the simple Rankine cycle, or sir, we are given the mechanical efficiency. How to such efficiencies are asked? Means mechanical efficiency you give in the IC engine. We are coming on that. Okay. We are coming on that mechanical efficiency in IC engine, my dear. Because let me tell you, when the mechanical efficiency you just compare, that mechanical efficiency means you are just going to compare the mechanical power with the mechanical power. Like mechanical power is the ratio of the brake power. Mechanical efficiency is the ratio of the brake power to the indicated power. So one form is coming at the outlet of the piston, that is the mechanical efficiency, mechanical power, indicated power. Second, at the shaft we are getting, that is also the mechanical power. So mechanical efficiency generally utilized when one mechanical energy is going to transfer to at some other place, and in that place, my dear, you are having lot of friction loss at that time, because total mechanical energy from here is not converted to here. That's why you have to introduce the efficiency, because actual conversion of the energy to the maximum conversion of the energy. So when mechanical energy is just reaching from one place to or converting from one form to another form, like mechanical energy of rotation is going to convert into the sliding. Sliding is going to convert into the rotation. At that time it is given. Getting my point? Good. Great. Absolutely right. Okay. चलिए बढ़ जाइए. Let's start the second topic, my dear. Topic is steam power plant and the simple Rankine cycle. Can you please tell me first of all what is the working medium in this case? Same thing I am going to discuss here, na? Same thing I am going to discuss here, my dear. You are just transferring the mechanical power in the gearbox. You are transferring the mechanical power in the shaft. So from one point to another point, you are transferring the mechanical power only. Getting my point? In the simple word, I am going to explain here, right? But in the class, we have discussed with a lot of example, क्योंकि हमारे पास time बहुत था उस समय. Clear? Okay. Anyway, come back to the point. Sir, what is the working medium in this case? I'll write pure substance, two-phase system, or the pure substance. Sir, when pure substance is when pure substance is the point or the topic in this case, my dear, then one thing must be clear in my mind, that question of this cycle is not other than the question whatever it was asked in the Brayton. But here the change of enthalpy will never be written like MC30. Are you getting my point? Sir, how this change of enthalpy will be known? first of all, from the pure substance, we must know, from the pure substance, we must know how to find the value of enthalpy, how to find the value of entropy. If the dryness fraction is not given, what point will help you to find the dryness fraction? If the point is in superheated region, what will be the value of these all points? Okay, sir. Now, pure substance is there. First of all, you need to tell me, have you attended the marathon of basic thermodynamics? Are you aware with all the point of the pure substance, how the enthalpy is calculated, how the numerical value of the entropy is calculated, a specific volume is calculated? Are you aware with all the points, my dear friend? Good. Aware na? Very nice. Wonderful. After that, you must know each and every process. Very good. Very nice. Just like the session. Open system. एक बार धमाका मचाओ यहाँ पे यार. And just maintain the full level of the energy till the evening. ऐसा ना हो कि 1 घंटे के बाद सोना स्टार्ट कर दो, because after this topic, most important topic is coming from your side, coming for your side. Reason? After that, most of the engineer feel the problem. Sir, ये question कैसे होगा? This is the compressor. छोड़ने जा रहे हैं. This is the turbine. We are going to skip the question. So up to turbine, up to this steam power plant, everything go in a very well manner. After that, you start to divert from here to there. Come back to the point. Sir, first of all, 1 to 2 isentropic expansion of the turbine. Sir, focus on this point. Focus on this point, that S2 will be equal to S1, my dear. S2 will be equal to S1. Focus on this important point. Second, in this case, my dear, pressure is constant, means P2 is equal to P3, my dear. After that, 3 to 4, isentropic compression of the work done, my dear friend. Isentropic compression of the work done. What is it? Sorry. S3 is equal to S4. And after that, P4 is equal to P1. Let's move forward and check what is all the diagram of steam power plant. This is the Rankine cycle. We are going to draw. This is not a Rankine cycle, let me tell you. The Rankine cycle, now we are going to draw, my dear. Sir. This is the Carnot cycle. This is the Rankine cycle. You have discussed everything like that. One point is at the inlet of the boiler. So let me write like this. Second point at the outlet of the boiler. From the starting you have written like this. 2 to 3 is the turbine. 3 to 4. 3 to 4 is the condenser. And 4 to 1 is the pump. Because I don't want to change your notation, so that you will be clear, able to understand. So from here, S2 will be equal to S3, my dear, because it is a turbine. From here, after that, it is the heat exchanger, condenser. P3 and P4 both will be the same. P4. Then, my dear, after that, P in the pump, S4 and S1 all will be the same. And after that, at last, 1 and 2 will be the same. In this case, constant volume process boiler, 1 to 2 will be the same. Okay. Now, sir, first of all, let me write this. At the inlet of this one is pump. Outlet is this. 3 is this and 4 is this one. 4 is outlet of the turbine, but in this case it is 3, I think. No issue. Let's change the number accordingly. 1 is at the inlet of the boiler, second outlet of the boiler, 3 turbine, and 4 is this steam turbine. Sir, first of all, in general or the basic cycle, let me change the color of this pen, otherwise Carnot and this will be the same, जो नहीं होनी चाहिए. Color is okay. Now, one by one, you must know in basic cycle, sir, few points are very well known to us in basic or the simple Rankine cycle, my dear friend. Simple Rankine cycle. Simple Rankine cycle, if nothing is mentioned, then point number 4. Point number 4 means at inlet of pump, saturated liquid state. Are you getting my point? These all the things were never given in the question. ये सारी चीजें कभी क्वेश्चन में नहीं दी होती हैं आपको. You have to use the presence of mind that at the inlet of the point, this is always there, that this is the saturated liquid point, my dear. Are you getting my point? Good. This is the condenser pressure and this one is the boiler pressure. So always your power plant work between boiler pressure and the condenser pressure, my dear. So this one is the boiler pressure and this one is the condenser pressure. This is already given to us that in the Rankine, in the steam power plant, your boiler pressure is this one and your condenser pressure is this one. Your power plant is working between these two pressure limit. Good. After that, my dear, next. After that, at least one point will be given to us. What is one point? That at inlet of condenser, condition of the steam must given to us either at the inlet of condenser or at the inlet of this turbine or at the inlet of this turbine, my dear. Condition is given at this inlet of the turbine, temperature of the steam is given, my dear, and temperature of the saturated is given to us. Sir, why these parameters are required? Because whenever it is given now that at the inlet of the turbine, your temperature of the steam is given to us like this, T superheated. So at the boiler pressure, when it is starting like this, what you will do, my dear? You will check is the superheated pressure or the superheated temperature is more than this T saturated or less. Means at least one condition is already given to us that your working medium is located where. Because if this point is known to us, I will draw this one. After that, this point may be here, my dear friend. It may be the saturated liquid, na? Why not? It may be the superheated, but this may be the bed vapor. Are you getting my point? So this is 2 to 3. This is also 2 to 3. Even this is also 2 to 3. These all points are okay. 2, 3, 2, 3. Everything is right, my dear. Are you getting my point or not? Yes. Write in the comment section. This is purely the simple Brayton cycle. If it is mentioned at the inlet of the turbine, working medium is in saturated vapor condition, it means you are somewhere here, my dear friend. If it is mentioned at the outlet of the turbine, the working medium is somewhere like this. This type of question may be asked. So these type of question you need to solve at last. Otherwise, from the Rankine cycle, most of the time easy questions are asked. Easy means you need not to do lot of calculation, my dear. So after that, if I'll write what is the turbine work, can you please write what is the turbine work? Can we write H2 minus of H3 kilojoule per kg? Is it or not? What is the value of pump work? That is the H1 minus of H4. It is also equal to VF most important formula you engineer never write. Most important formula, my dear. Raghu, you engineers never write. Most of the time this formula will help you a lot to find the pump work. You never write VF into dP is also one more formula to find the value of the vapor pressure. After that, my dear, what is the value of the heat supply? That is equal to H2 minus of H1. And what is the heat rejection, my dear? That will be equal to H3 minus of H4. Sir, from these all the points you know very well from where these terms are coming, steam table. From the steam table, you are able to find the each and every value if you are able to know the dryness fraction, know the superheated condition and all, my dear. After that, if I'll write the efficiency of the Brayton cycle, efficiency of the Rankine cycle, can you please tell me the answer? What is the efficiency of the Rankine cycle from here, my dear? Can we write efficiency of the Rankine cycle? That will be equal to W net divided by heat supply. That will be also equal to 1 minus heat supply, heat reject divided by heat supply. That efficiency of this can be written minus 1 minus heat rejection. That will be equal to H3 minus of H4, and this one heat supply will be equal to H2 minus of H1. The point is this, are you able to find that answer of each and every question in the Rankine cycle is purely related to answer of each and every question of the Rankine cycle is purely related to, are you not getting to find the enthalpy? It will purely depend upon the ability of yours to find the enthalpy of all the region in the pure substance. Raghu, if you are able to find the enthalpy of all the point in the pure substance topic, you will be able to get the answer of each and every question in the steam turbine. The main problem is you think that Rankine cycle topic is the problem of the Rankine cycle or the steam power plant. No, Rankine cycle is the problem of the pure substance. Are you getting? If you are in the bed vapor region, you know that in the bed vapor region, my dear, formula is HF plus X into HFG. If you are in the superheated region, you know the numerical value, because first of all, you know the requirement, and after that you will start to find the solution of everything. Getting my point? Yes. So in this case, like the Brayton cycle, you are not going to follow the T2 by T1 is equal to P2 by P1 condition. Outlet condition of turbine is not given. Then we should find the dryness fraction. Yes, sir. If the outlet condition of the turbine is not given, so you will start your question from the consideration that at the outlet of the turbine, my steam condition is bed vapor. You will take the assumption. If you are having the doubt, whenever you are having the doubt, you will take the assumption if it is clearly mentioned, directly or indirectly. Sir, how directly and indirectly will be given? Directly will be given in such a way like that steam at the outlet of the turbine is saturated, clearly mentioned in the question. Are you getting my point? Clearly mentioned in the question. Okay. Or like condition may be given like this: steam at outlet of the turbine, if you want to ask of turbine, like this saturated, like this bed vapor, or like this superheated vapor. This is the direct mention. Are you getting? This one is the direct mention in the question. What do you say? Washing powder Nirma, क्या कहते हो? This is directly given in the question that steam at the outlet of the turbine is somewhere like this, or the temperature of the steam, just a minute, at turbine outlet given. This is indirectly mentioned, my dear. This one is the indirectly mentioned. If the temperature of the steam at the outlet of the turbine is given to us, now you start to think, sir, how? For example, if the temperature of the outlet of the steam is given like this, 320, and you know very well at the outlet of the steam means condenser pressure, that is 2 bar or the 1 bar, my dear, and at the 1 bar, T saturated is equal to 100 degrees centigrade. Yes or no? These all points are known to us. So I know that when the steam is expanded, then its temperature is 320 degrees centigrade. But at 1 bar, when it will be expanded, its temperature should be 100 degrees centigrade. It is having 320 degrees centigrade. What is the meaning of it? What is the meaning of it? It is the indirect mention of the steam turbine. It is the indirect mention. Yes, tell me what exactly, what is this indicator you are getting from this question? आपको क्या इंडिकेशन लग रहा है इस क्वेश्चन से? Umar, Malays, this is just a hint given to you that solve the question like this. At the outlet of the turbine, temperature is given to us, that is 320 degrees centigrade, but at condenser pressure, exactly. ये आपको एक इंडिकेशन दे रहा है उमर. This one just a indication that at the outlet of the turbine, your working medium is somewhere in this range, my dear. Somewhere in this range. Like this. Are you getting my point? Somewhere like this. Agree or not? Yes. Hint also may be given like this. Hint also may be given like this. Steam at inlet of the turbine saturated or wet vapor. This is also a hint for you. Steam at the inlet of the turbine is the saturated steam or the wet vapor. What you all guys getting from this statement? What will be the steam at the outlet of the turbine? What will be the steam at the outlet of the turbine, my dear friend? What exactly you all guys getting from this point? अरे आंसर बताओ जल्दी से. What exactly you are getting from this point? What is the meaning? What is the steam at the outlet? Very good, very nice. Males, what do you say? Wonderful. Yes, wet vapor. Anyone else? So these are the conditions. These are the indication given to us to solve any numerical problem. It will reach till that you are not going to make a single mistake in the applied thermodynamic, my dear. इस level पे पहुंच जाओगे, you are not going to make the mistake. These are the indication given to us, serious. That this is purely related to the wet vapor condition. Exactly. Sir, are you getting the point? Reason, let me tell you. Reason, sir, check from here. If I am in wet vapor region, superheated region, then at the outlet it will be wet vapor. If I am already in the wet vapor, at the outlet it is already wet vapor. Are you getting? These are some indication that how will you start your diagrams. Once diagram is clear now, you are not going to make a single mistake in the topic of this gas power plant and the steam power plant, my dear. Clear to everyone? Good. Great, great, great. Some, let me write some hint in the question. ये कुछ hint होते हैं in question. Are you getting this point? They are some hint in the question, my dear. Yes. Next question comes Sir, if nothing mentioned in the question, then what cycle will be the perfect cycle? Yes, let me tell you. When nothing mentioned in the question, then my dear, there is only one cycle I am going to draw, and that cycle is this one. This will be the ideal cycle if nothing is mentioned in the question, my dear. Red color cycle is the ideal cycle if nothing is mentioned in the question. Clear to all? Yes. If nothing is mentioned, then this will be the cycle you need to assume. Okay? Clear? Is it clear to all? Umar, it is your question. If sir nothing will be mentioned, then what will be the cycle? At the inlet of the pump, working medium must be saturated liquid. At the outlet of the turbine, working medium. Feeling ना सबको आ रहा है सबको? Everyone feeling, my dear? Yes. Wonderful. Great. Good. कौन यो यो कर रहा है? Great. Now, performance parameter we have already written. After that, let's do some modification, my dear. Reheat cycle. Again, these are the modification. Very good. These are the modification in the Rankine cycle. Sir, are you aware with these type of question or not? Sometime numerical value are directly written on the diagram. कुछ क्वेश्चन ऐसे भी आए, इतने आसान लेवल के भी क्वेश्चन आए हैं यहाँ से. Yes. Good, good, good. Great, Umar. So, at this point, my dear, 1, 2, 2, 3, to 4, to 5, and to 6. Sir, generally, this is 1 at the inlet of the boiler, na? Yes. 2, outlet of the boiler. 3, reheating. 4, outlet of the reheating. No. Sorry. 1, inlet of the pump. 2nd, inlet, outlet of the pump. 3rd, outlet of the boiler. 4th, outlet of the turbine. 5th, outlet of the reheater. Sir, nowadays we are using the reheater in such a manner, my dear, that reheater is integral part of the boiler. So that is the reason sometimes this type of figure can also be given in place of reheater. After that, second, low pressure turbine, that this 4 to 5, my dear. 5 to 6 is low pressure turbine like this, and 6 to 1 somewhere like this. After that, again, one part theoretical question, one part, my dear, theoretical question. So in this case, in the reheating, if I'll ask the theoretical question first, what is the turbine work? Can you please tell me in the reheating? Turbine work. Sir, first, when one turbine was there, then this was the work done. These are the theoretical questions. Tell me the answer. Definitely increase. My dear, pump work, definitely constant or the same. Very nice, very nice. After that, what is the net work? Increase. Sir, most important question, please write somewhere. What is the effect on the quality of the steam? What is the effect on the quality of the steam whenever reheating is done? Tell me the answer. Tell me the answer, my dear friend. What is the effect on the quality of the steam whenever reheating is done? Yes. This is the most important question in the theoretical part. Yes, it will increase, my dear. Yes, all of you? Good. यार कितने 25-26 लोग तो यहाँ पे दिख रहे हो, but you write only 2-3 people, you are just writing the answer. बाकी सब लोग सोफे पे सो तो नहीं रहो? Are you sleeping on sofa or bed? Okay, come back now. After that, what is the efficiency? Okay, efficiency will increase. So these are the best choice for the MSQ question. Okay, no issue. Yes, this one is the best choice for the MSQ question. In the reheat Rankine cycle, what is the numerical effect on these all the parameters? After that, I will not write so much for the numerical problem, because numerical is nothing but, my dear, numerical questions are again the same, whatever you have discussed. For example, if you want to write the net work done, what will be the answer? It will be equal to mass flow rate into, what will be the mass flow rate of a steam? What is the steam? 3, 4 and 5, 6. H3 minus H4 plus H5 minus H6 minus of H2 minus of H1. What is the heat supply from here, my dear? What is the heat supply? That will be equal to mass flow rate into first heat supply. Yes. Okay. Yeah, it may increase or decrease. That will depend upon the numerical value of, that will depend upon the numerical value of the temperature, what exactly you are going to increase. Yes, absolutely right. Come back. Heat supply, sir. Heat supply H3 minus H2 plus of H5 minus H4. Yes. Good. After that, what is the overall efficiency? Again, it will be equal to W net divided by heat supply. Sir, I should say that every numerical can be solved only from this slide related to reheat Rankine cycle. Whenever you are going to solve the question, whenever you are going to see the exam, write the exam for reheat Rankine cycle, you just watch this slide. It will be more than sufficient. But one thing you must know, that how the H2, H3 and these all values are calculated from the pure substance topic. Because this thing we need not to discuss again and again. Because if the pure substance topic is clear to us, then you are not going to make a single mistake in this topic, my dear. After that, again, most expected topic for GATE 23 is regenerative Rankine cycle. In this Rankine part, my dear, this one is the most expected topic you can expect for GATE 23. Yeah, you are 28 in the comment section and likes are only 26. Make it at least 30. कम से कम 30 तो बना दो. Not for me or anyone, at least for the people who are writing in the comment section. They are working a lot. Not me, but maximum of you are working a lot in this comment section, especially ये चार मूंदों वाला. You are Teju ना? Champak? You are Teju or Champak? Okay, come back. Okay, come back, sir. Okay, sir. In this case, yes. So, first of all, our theoretical question we are going to discuss here. After that, second one, my dear. Second one, we are going to discuss numerical question from here. And I am going to discuss what type of numerical question may be asked. Sir, mark my point. In this Rankine cycle only, if the question will be asked, then this is the most expected topic of the Rankine cycle. Okay, come back. Forget 23. Sir, you know very well that regenerative Rankine cycle is the exchange of the energy between the high temperature and low temperature working medium before rejecting the heat into the atmosphere. But in this case, it is not possible. The reason is because at the inlet of the boiler, working medium is having the higher temperature than the inlet of the condenser. Because after the turbine and after the compressor, you exchange the energy. But in this case, it's just a reverse. Reason is very simple, my dear, because heat will be rejected from this medium in place of this medium. So what you do, with the partial expansion in the turbine, you take some mass out of the system. In any test series, you just write in the comment section, my dear. In any of the test series, have you seen the question like where this total complete question is given to us related to regeneration and overall efficiency or overall network is asked in place of mass of the steam bleeded off? Most of the time in the test series, the question is asked like this: what is the mass of the steam bleeded off from the turbine? But whenever difficult question will be there, whenever most difficult question will be there, in place of steam bleeded out, he is going to ask, my dear, what is overall efficiency? कहीं पे आया ऐसा क्वेश्चन? Yes, Umar sir, I have written. Good. I have solved. Very nice. Wonderful, my dear. Great. Okay, come back. Sir, let me tell you, in this portion, you are not going to make any mistake if you are aware with one point, my dear. Sir, first of all, from here, 1 kg per second mass is going to enter. If after the partial expansion, after not a complete expansion, in between the blade, because you know very well, steam turbine is the example of the blade in series. Thousand of row of the stages are there, 100 of row of stages are there, my dear. So what you do, you steam, you just pass the steam up to middle of the blade, and after that you take the blade off or you take out that steam, and after that the complete steam is allowed to fully expand. नहीं उत्कर्ष पता नहीं आजकल नहीं आ रहा है, आ जाओ वापस, वो अभी स्लीपिंग मोड में है. So these are the blade, these are the blades, and these number of blades are very much. I'll show you the complete diagram of the steam turbine in the next topic, my dear. You will be able to get the clear-cut idea of this topic. Okay, let me show you the topic, it will be better. Let me show you the complete topic like this. These type of blades are there, my dear. Yes, a row of the stator and rotor blades are there in the series, my dear. Clear? So what we do, from this portion we take some steam out like this, because most of the engineer ask, sir, how it is possible, how we take the steam out of the turbine? We can take the out of the turbine because steam is passing through like this. If I'll make the hole, a small hole, and other it will be allowed to in this part, definitely it is possible, my dear. Okay, good. Okay, I think he is yes, he is having one exam. Okay, come back. Good. So mass is taken. Sir, what is the point from here? 1 is somewhere here. At this 1 point, 1 kg mass is entering, and 1 to 2, again 1 kg mass is entering at this place. Okay, this is the 2 point. But from 2 point, m kg mass is going to enter into open feed water heater. From here, it is enter into open feed water heater. In this case, 1 minus of m kg mass is enter into the condenser, my dear. That is the 3 point. After the condenser, 3 to 4, 4 to 5 is the pump, 5 to 6, my dear, 5, 2 are mixing and they are making 6. 2 is coming from here with the enthalpy of H2, and 5 is coming from here with the enthalpy of 5,2, and mass is 1 minus m, and they are making H6. After that, my dear, 6 to 7 is the second pump. Okay, second pump, and 7 to 1, it is the example of the complete turbine. Okay, good, great. So in this case, first question come, sir, if first question come, my dear friend, if this open feed water heater was not there, or you can simply say, if the regenerator was not there, my dear, if the regenerator was not there, let me ask first theoretical question from your side. Effect, theoretical effect, my dear, if this open feed water was not here, then definitely 1 kg of the heat will start to reject from this point to this point. It will start to expand. So I want to know what is the effect on overall work done of the turbine. I mean, lower, higher, or constant. What do you really feel? It is lowering, it is higher, or it is the constant, my dear? Tell me the answer. Tell me the answer of this question. Wonderful, wonderful. These are the GATE theoretical question. What is the effect of regenerative Rankine cycle, my dear? Decrease. Reason? Mass is bleeded off. That's why total mass of the steam is not expanded over the turbine blade, my dear. Are you getting this point? Total number of the steam, mass of the steam is not expanded over the turbine. Yes. Next. What is the heat supply? Anyone? छोटे वाले चंपक. What is the heat supply? What is the heat supply? If this open feed water heater is not installed, what is the heat supply in this case, my dear? Open feed water heater is not supply. What is the heat in this case? Absolutely right. It will decrease. Yes. Excellent. Decrease, my dear. Umar, let me tell you why. Sir, if the open feed water heater is not there, then it is working like this boiler pressure. Then you have to do this work. Is it or not? You have to do this work. So this portion of the work is reduced because heat is supplied under this and this, my dear, 7:1. But if the open feed water heater is not applied, then this heat will be supplied from here to here. Are you not feeling this area is the loss of the work, heat? Ye loss of the heat? Yes. So heat supply will be decreased in this case. Heat supply will be decreased in this case. Are you getting, all of you? Yes. Decrease. What is the overall efficiency? Can you please tell me? These are very important theoretical questions for MSQ, my dear. Just tell me the answer. What is the numerical value of efficiency? Definitely it will increase. For this purpose only we are doing everything. Naveen, for this purpose, I mean to increase the overall efficiency of the power plant, we are doing the regeneration, my dear. Okay. Yes, exactly. So heat supply will decrease. Yes, absolutely right. And at the last point, let me ask the question, what is the quality of the steam at the outlet of the turbine? Sir, mark this point. Whenever quality is asked, quality of the steam is asked. Quality of the steam we always check at the outlet of the turbine blade. Means here we are going to check. Yes, please tell me the answer. What is the quality of the steam of this turbine, my dear? Here we are going to check the quality of the steam, my dear. What is the quality of the steam? If no open feed water heater is used, no, not a single open feed water heater is used, what is the dryness fraction, my dear? क्या फर्क पड़ेगा? These type of questions are the best choice for the MSQ. Best choice है MSQ के लिए. Sir, first of all, this was the dryness fraction. Right now, this is also the dryness fraction. So dryness fraction is not going to change in this case. That's why you will write the total numerical value is the constant. Dryness fraction will be the same. At the outlet of the turbine, you are going to check. यहाँ आप check कर रहे हो at this point. Umar, Teju, Malays, at this point, my dear friend, you are going to check. You all are going to check at this point number 3. What is the value of the dryness fraction? Yes, sir, even if open feed water heater is not there, hota hi nahi, then definitely 1 to be expanded up to 3 point. So 1 and 3 point are not going to change, only the mass is going to change. Total net mass is going to change, 1 and 3 point are not going to change in this case. Are you getting my point? Yes or no? 1 और 3 number के point change नहीं हो रहे हैं. That's why your dryness fraction is not going to change. Clear? After that, sir, best question, what is the mass of steam, my dear? Numerical question that is asked generally, bladed off. In most of the test series, you have seen this question, yes or no? In most of the test series, if I'm not wrong, you have seen this question, my dear, that M mass is entering from 2. That is leaving with the 6, and this is entering with 1 minus M at a enthalpy of 5. So if I'll write the energy balance equation on open feed water heater, my dear, can we write that M mass is entering with the enthalpy of H2, plus 1 minus m mass is entering with the enthalpy of H5 and is equal to H6. That is the energy balance equation that can be applied on open feed water heater. That can be applied on open feed water heater, my dear. After that, if you will write what is the value of overall efficiency, maximum of engineer write somewhere, do the mistake in this question by writing 1 minus heat reject divided by heat supply. Biggest mistake you are doing, my dear. Biggest mistake you are doing if you are writing the formula of the efficiency in this case like this. This formula will never be valid in this topic, my dear. What formula will be valid then? The formula will be valid that W net divided by heat supply, my dear. Okay. What is the W net? It will be equal to, for 1 kg we are doing, it will be equal to H1 minus H2, my dear, plus 1 minus M H2 minus H3 minus compressor work 1 minus M. What is the compressor work, my dear? Compressor work, this is the pump work, H this 4 5 6 7 4 5 5 minus H4 minus again 1 kg H7 minus H6 divided by what is the heat supply? Heat supply is H1 minus H7 for 1 kg. Most important formula you can apply. Let me tell you, when this type of question will be given to us, when this type of question can be given in the GATE exam, my dear, in the GATE exam either this type of system is mentioned or this type of TS diagram is mentioned, then enthalpy of all point is asked to us. सारे point की enthalpy is directly given to us, my dear. Then in these type of questions you can easily apply this formula and this time you can solve the question. But in GATE question, enthalpy of all point is not given directly. Never come into the trap. Even you can solve this question, but you will take minimum 15 minutes. कम से कम 15 मिनट लगेंगे उस क्वेश्चन को सॉल्व करने में, whenever enthalpy of all the points is not mentioned in the question, my dear. Like H1, H2, H3, H4, 5, 6, 7, all the point enthalpy is mentioned, my dear. Then and only then you can solve the problem of this overall efficiency, first for the M mass, percentage of bleeded off, and after that efficiency. Otherwise, if this value of the enthalpy at all the point is not given the question, it is given in the form of table from the steam table, then my dear you will take near about 15 minutes to solve this single type of problem. I'll suggest leave this question for the last. Are you getting my point? समझ रहे हो? In this smart way you have to attempt each and every test also, not only for the GATE exam. In this way, my dear, you need to attempt the every test of your GATE exam. Are you getting? Can we move forward? Regenerative Rankine cycle, all of you? Great. Wonderful. After that, what is the effect of the superheating, my dear? Good. What is the effect of the superheating? This 1 to 2 to 3 to 4 and to 3 dash to 4 dash is after the superheating. Superheating of the steam increase the net work output and the efficiency of the cycle, because mean effective temperature decrease. It decrease the moisture content or the quality. Temperature to which steam can be superheated is limited by the metallurgical problem near about 650. So again, these are the effect you must know. Theoretical questions are there. Next, increasing the boiler pressure. Sir, 1 to 2 to, my dear, 3 and to 4. 1 to 2 dash to 3 dash and to 4 dash is the boiler pressure. Sir, increasing the operating pressure of the boiler lead to increase in the average temperature at the heat is supplied to the system. raise the efficiency of the cycle. Again, it raise the efficiency of the cycle, right? After that, decreasing the condenser pressure, 1, 2, 3, 4, 1 dash, 2 dash, 3, and my dear 4 dash. What is the effect on the condenser pressure? All theoretical questions are good for MCQ also. Shaded area of the diagram represent the increase in the work done, result in the increment of the work done. Heat input required also increase, but this increase is very small. Overall effect is the lowering the condenser pressure is an increment in the efficiency. All the improvement, all the modification in the Rankine cycle are increasing the overall efficiency of the system. Okay, if you will increase the boiler pressure, efficiency will increase. If you will decrease the condenser pressure, efficiency will decrease. Are you getting my point? Yes. If you do the superheating of this Rankine cycle, my dear, then one benefit is you are increasing the quality of the steam, and second benefit is you are increasing the efficiency of the entire system. Good. Next, simple steam rate. I need not to write again. Steam rate we have already written. What is the steam rate, my dear? 3600 divided by W net, unit will be equal to kg per kilowatt hour. Is it or not? Similarly, if I'll calculate the value of the heat rate, my dear, that will be equal to 1 upon overall efficiency of the power plant. Clear? These are some numerical point may be asked to you. So ये सारे questions है जो पूछे जा सकते हैं related to the Rankine cycle. After that, we are going to move forward to discuss the next important topic of the Rankine cycle or the power plant, my dear. Most dangerous topic for all the mechanical engineer is the steam turbine. Sir, tell me in this topic first. Tell me in the comment section how many of you are planning to skip this topic, this and compressor. Anyone? How many of you have already planned to skip this topic, my dear? नहीं, बहुत सारे कॉल आते हैं सर. That's why I'm going to ask. No one? No one is there? Okay, Midhun, देखो एक. Yes. Okay. No, sir. Good. Great. Only one of you are there. I'll suggest few important point to you. Don't worry. Okay. Don't worry. I'll suggest few important point for you. If you are, I've read it only the two formula. That is, I know the formula. If the question will come from the formula, my dear, then I can do. And let me tell you, most of the time, Umar, most of the time, question will ask directly related to the formula. आपको लगता है ज्यादातर टाइम पे इस टॉपिक से जो क्वेश्चन आने वाले हैं, these are related to the point formula. But what we do, my dear, we already plan everything that the question related to the steam turbine will come into the exam. I'm going to skip this question. So this topic of the steam turbine and the topic of the compressor, my dear, is purely related to the numerical formula. If a few numerical formula are clear to you, and you must know that this numerical value will be given with which name, then you are not going to skip that topic. You are not going to skip the question related to the steam turbine. Sir, one by one, I will tell you how the theoretical question will be asked in the exam. And let me tell you in advance, my dear friend, let me tell you in advance that theoretical question is asked from this topic, then all the theoretical question I am going to cover in the session. How many maximum possibility of the theoretical question will be there, then we are going to cover these all the theoretical question within the session. It is only the question of numerical part. Let's move forward. Okay, can we start? Third important topic we are going to discuss. Can we start? कुछ energy बनाओ यहाँ पे. How is your energy level? How is your energy level? Is it zero, medium, high, or what? Or sleeping mode? Right. Good. Super. Very nice. अब पता नहीं रघु बोल ही रहे हो कि दिल में भी है. Yes. Because let me tell you, you are hardly 10 to 5% of the mechanical engineer this year who are going to make the history. The reason is very simple, because other 90% are just fighting for the qualifying marks. If you can sit for the 8 to 10 hour in day and 5 to 6 hour in night, my dear, then you are definitely working for the top 100 rank. Definitely. But again, you have to maintain this level of the energy for continue throughout the day and throughout the night, my dear, until the GATE exam. Let's see. Right now. Because a very simple point I told you number of time, if you know the Hindi, right? कई बार मैं आपको ये पॉइंट बोला हूं कि बड़ी खाक छाननी पड़ती है, ऐसे ही धूल का बवंडर नहीं बनता, और एक बार जीतने से कोई सिकंदर नहीं बनता. राइट ना? आ जाओ वापस. Come back to the point. Sir, what is the steam turbine? First of all, let's try to understand. A steam turbine is a prime mover which convert the potential energy, and from here, anyone can write in English for Teju. Your best friend is not here, Utkarsh. Otherwise, he can write very easily. Yes. Anyway, come back to the point. In short, it is the point. Every day you have to fight whatever you want in your life. Every day and night also. Come back. Yes. You must miss Teju. Miss to this Gajodhar. Or I think he is also the Tomato Singh, if I am not wrong. Bhaiya Tomato Singh. Yes, come back. Sir, if it converts the potential energy, and let me tell you, my dear, in short, it is enthalpy. Yes. Steam turbine is a prime mover that convert the potential energy of the steam, or you can say the potential energy of the fluid also, in the topic of fluid mechanics. Transfer into the kinetic energy. Kinetic energy is converted generally into the nozzle, my dear. Okay, nozzle. Kinetic energy is converted into the nozzle, and after the nozzle, this kinetic energy is imparted over the moving blade that transform into the mechanical energy due to the rotation of the moving blade. Are you getting my point? So here, before starting the topic, you must know two important points are there. Two important points are there. One point, my dear, that your enthalpy is converting into the kinetic energy. Second, your kinetic energy over the moving blade is converting into the mechanical work. Are you getting my point? When already you have written in the steam turbine, my dear, steam power plant, that work done in the turbine is the change of enthalpy. Yes or no? Work done in the turbine is the change of enthalpy. H2 minus H3 or whatever. Have you written like this or not, my dear? Yes or no? Vedun, Raghu, all of you, Umar, Naveen. Change of enthalpy is the turbine work. Yes or no? Change of enthalpy is the turbine work. This is the very general statement. This is the very basic statement in thermal. Here what we are doing, my dear, this change of enthalpy you have written. That H2 minus H1 is the change of enthalpy. Or change of enthalpy is the work done. But in this topic, what is the purpose of this topic, my dear? You must know. Purpose of this topic is to convert this change of enthalpy into the mechanical work. इसी को convert करना है mechanical work में. How it will be converted into a mechanical work? Because this change of enthalpy is there. But how this change of enthalpy is possible? So what you are doing? First of all, you are converting the enthalpy into the kinetic energy on nozzle. That is fixed, my dear. That one is the fix. And after that, this high kinetic energy fluid is imparted over the moving blade that is doing some work. Means when high steam velocity or jet will be imparted over the blade, that will start to rotate the shaft. And when the shaft will be rotating, my dear, then definitely it will produce some power on the generator. And in this way, your electricity will be produced. Are you getting my point? So, this entire procedure we need to discuss how the kinetic energy is converted and how this kinetic energy is utilized to the mechanical work. Are you getting my point? And this nozzle plus moving blade is known as one stage. For example, if you are going to discuss this point, my dear, so what is the meaning of this? You must know, sir, between this, when you write na H1 and H2, this is the change of enthalpy. And after that, this one is nozzle where the enthalpy is going to convert into the mechanical energy. And after that, it is going to convert it into the work done. So this is known as one stage, my dear. Are you getting? What is the ideal change of enthalpy? Ideal change of enthalpy, that is the moving blade. So अगर मैं ideal work की बात करने आऊं, what is the ideal work? Can be written like this, H1 minus of H2. This is ideal possible work. In this case, are I say yes or no? This is the ideal possible work in this case, my dear. All of you agree? अरे आपको दिख नहीं रहा, sorry. Ideal possible work can be written like this. Check it. Very nice, wonderful, great. Nice. So keep this point in mind that ideal work according to thermodynamic is the change of enthalpy. Now we need to discuss this ideal work is changing in this steam. How, sir? This steam is coming from here. Video is not there. Even the same video is also available from the YouTube. It's a thank you for that video from where I have just taken the screenshot. Yes, sir. When steam will imparted over this one, then this row of the steam turbine is there. If I will just enlarge one section of this steam or of this steam turbine blade, my dear, then it will look like this. Are you getting? The steam is going to enter like this. Steam is going to enter. Steam is going to enter like this. And at the inlet, it will be a nozzle, my dear, and this will be a moving blade. So this one is the stage. This one is the stage. And this one is the stage, my dear. These all are the stages. Are you getting my point? So these are known as stages of the turbine or compounding of the turbine. When lot of stages are connected to each other now, then this method of the connecting the turbine is known as compounding on the turbine. So before moving forward, let's discuss what is the compounding, my dear. And if I will discuss the type of blade, my dear, then the type of these moving blade may be two type. दो type के blade हो सकते हैं. Either the moving blade are somewhere like this. Can you please tell me what are these blade, my dear? What are these blades, my dear friend? Are you not feeling these are the aerofoil type of blade? These are the aerofoil type of blade. And what are these blade, my dear? Are you not feeling these are the profile type of blade? Yes or no? These are the aerofoil type of blade. All of you agree or not? What do you say? One is the aerofoil type of blade and second is the, yes, good, great. And they are converging blade, my dear. What is the meaning of the converging? Means as you are moving in this way now, the cross section area is going to decrease. Please keep this point in mind. And when from here, the working medium is moving in this way now, then this cross section area is same. Like this. Let me tell you, sir, from the previous figure now, I have taken only one row. मैंने यहाँ से एक row उठा लिया ये. To just give you the clear-cut vision how this steam is flowing, my dear. Like this. So, based on the profile of the blade, there are two type of the turbine. One is known as impulse turbine. Theoretical question we are going to discuss here. One is known as impulse turbine. Second is known as, my dear, reaction turbine. Let me tell you. When the blade are the perfectly profiled type of blade, can you please tell me? When the blade are perfectly profiled type of blade, these are the moving blade, these are the nozzle, my dear, then the turbine is known as impulse turbine. When the blade are perfectly impulse type of, profile type of blade, that is the moving blade we are talking about here. Moving blade we are talking about here, my dear. When the blade are moving blade are the profile type of blade, turbine is impulse. When the the turbine blade, moving blade are the aerofoil type of blade, and converging blade, these are the example of these are the example of reaction turbine. Sir, now from this part only theoretical question may be asked, like, first of all, in impulse turbine, pressure, velocity. My dear, nozzle and moving blade. Most expected MCQ question, MSQ question for your exam. What is the effect on the pressure on nozzle, my dear, if it is the impulse turbine? What is the effect in nozzle, my dear? Decrease. What is the effect? It will increase. What is the effect on the pressure? On moving blade, same. What is the effect on velocity? Decrease, my dear. Most expected question. Similarly, in reaction turbine, same question may be asked to you. Same question may be asked to you in reaction turbine. Pressure, velocity. Pressure, velocity, nozzle and moving blade. Please. Nozzle pressure decrease, velocity increase, velocity decrease. What you are getting from here? We are getting the net work done in the reaction turbine more than the net work done in the impulse turbine, my dear. Pressure decreasing in both, velocity increasing in nozzle, but on moving blade it is decreased because it is going to convert into the mechanical work. Velocity is going to decrease in the moving blade because it is going to convert into the mechanical work. This is only the condition. Yes, you can read all the statement whatever I have discussed till now. Pressure will decrease only in nozzle, not on moving blade. Let me change the color of this pen. On the moving blade, pressure will decrease. Area will be the constant. Profile type of shape are there, my dear. Area is converging cross section area, most important point, because later on this will increase the relative velocity. Let me tell you in advance. Aerofoil type of blade, not all round and complete, all round and complete. Diaphragm contain the nozzle. Fixed blade similar to the moving blade are there, and they are just attached in such a manner that they work like a nozzle, my dear. Power not so much, very high much power is produced in this case, my dear. After that, now sir, there are several methods of reducing the speed and to the lower value. Compounding of the turbine. Why the compounding of the turbine is done? Because the pressure difference at the inlet and outlet of the turbine, my dear, is very high. Pressure difference at the inlet and outlet of the turbine is very high. That's why we try to decrease the velocity in a very slow manner, or we try to decrease the velocity in a very slow manner. When you're decreasing the velocity in a very slow manner. Velocity you are decreasing in a very slow manner. This compounding is known as velocity compounding. And my dear, the example is Curtis turbine. Till now, this is the best question for the theoretical part. Curtis turbine. Pressure compounding Retiu turbine is the example of pressure compounding. Let's discuss how the question may be asked from the pressure compounding, my dear. In the pressure compounding, directly you can see impulse type of stages are connected. I am very sure from here you started to feel fear. Yes or no? Because number of stages are given. Sir, you have to focus on the theoretical question in a very well manner. Sir, what are the question? If it is the pressure compound, then how the question may be asked? Question is directly asked, sir, if it is the moving blade like this, okay? If it is a fixed blade like this, if it is the moving blade like this, if it is the fixed blade like this, and if it will be the moving blade like this, then you need to give me the answer how the pressure is going to decrease in moving blade, how the pressure is going to decrease in fixed blade. Now you need to tell me in pressure compounding, my dear, if it is the fixed blade, can you please tell me on the fixed blade, what is the pressure? What is the pressure on the fixed blade? What is the velocity on the fixed blade? If it is the question on the moving blade, my dear, what is the pressure? Sorry. कुछ उल्टा लिख दिया गया है. Just a minute. If it is the question of moving blade, what is the pressure? My dear, same. And what is the pressure? It will decrease. And what is the effect on the velocity? Velocity will decrease. Just only you need to focus on these parts. That's all. बस इतने पार्ट पे फोकस करने की जरूरत है. Sir, if it is the example of the impulse turbine, then my dear friend, your pressure will decrease and your velocity will increase on the fixed blade. But on moving blade, your pressure will be constant and your velocity will decrease. Example is Retiu turbine. That's all. This part you need to focus. Sir, fixed blade, pressure decreasing, velocity increasing. Moving blade, pressure constant, velocity decreasing. That's all. These may be the question of the pressure compounding. You just see this type of figure and you start to worry about the GATE exam. Only you need to feel, sir, there is one stage in the turbine, only one stage. In this one stage, one is the velocity compounding. One is the fixed blade, second is the moving blade. What you need to know? No, you need to know only the change of pressure. You need to know only the change of velocity, that point. Similarly, in the velocity compounding, my dear, you are decreasing the velocity in a very slow manner. Check again. Fixed blade are there, my dear. Fixed blade and moving blade are there, my dear. What is the pressure on the fixed blade? Tell me. Not changing. What is the pressure on the moving blade, my dear? It is also not changing. What is the velocity on the fixed blade? It is same, my dear. What is the velocity on moving blade? It is decreasing, my dear. That's all. These question you need to focus. An example, if I am talking about, what is the example of Curtis turbine? Example of this one is, yes, Curtis turbine. So this is the way to summarize the theory, whatever you study. This is the time you need not to study how this turbine is moving, how this diagram is drawn. If you will write the summary of the entire diagram now, then after that you need to focus only the points. Sir, in the velocity turbine, in the velocity compounding, the example is Curtis turbine. In the fixed blade, neither pressure nor volume is changing, but on the moving blade, pressure is same, but my volume is velocity is decreasing, my dear. Getting my point? Similarly, you can think like this. On the fixed blade, my dear, on the fixed blade, on the moving blade, how the things are changing. If you will be able to know this point, each and everything you can solve very easily, my dear. Yes? Is it clear to everyone? Tell me. Compounding of the turbine is clear to everyone, my dear? Write the answer in the comment section. Compounding of the turbine, is it clear to everyone or not? Then we can move forward. These are the theoretical questions. After that, no theoretical question is there, my dear, from the steam turbine. These are the theoretical questions. If you want, I can summarize the entire thing, whatever we have discussed till now. If you will just ask, I will summarize the same thing again, whatever we have discussed in steam turbine, or can we move forward? It is up to you. Please tell me the point. Can we move forward or should I summarize everything? Move forward. You say, okay, summarize. Someone of you say summarize. Okay. Okay. Sir, first of all, just a minute. First of all, you need to feel that you can design. देखो बहुत 3-4 लाइनें समझनी है. Leave your pen and paper and focus on few important points. Sir, think like that I can design two type of blade. One, maybe the perfectly profile type of blade, means arc of a circle, that is known as impulse type of blade. Moving blade I am talking about. My stage is a combination of the fixed and moving blade. If I define my steam turbine based on the impulse and turbine, these are the type of blade. Means when you say na impulse turbine or the Britten turbine, these are not the type of turbine, my dear. These are the turbine blade type. So you can design your moving blade type into two ways. One, it is the profile type of blade when it is the example of the impulse turbine. Second is the aerofoil type, and aerofoil is also the converging type. Okay. So blade may be the impulse, maybe the reaction. So after that, it may be the ask that sir, in the nozzle, whenever fluid will be allowed, then definitely kinetic energy will increase and pressure energy will decrease. So in the nozzle, I am not going to ask any question for the impulse or the reaction turbine, but if it is the impulse turbine, perfect profile is there. Perfect profile is there, my dear. Inlet and outlet cross section area is same of the blade. Then pressure in the moving blade of the impulse turbine will be same, but kinetic energy is converted into the mechanical work. That's why kinetic energy will decrease. So listen this point. In the impulse turbine, nozzle will decrease the kinetic energy and increase, nozzle will increase the kinetic energy, decrease the pressure energy. First point you need to recognize. Second, but moving blade will have the constant pressure and decrease the velocity, part of impulse turbine. But in reaction turbine, again nozzle will increase the velocity and decrease the pressure, but moving blade will decrease the pressure and increase the velocity, and decrease the velocity again. Impulse में प्रेशर कांस्टेंट रहता है. रीजन इज वेरी सिंपल, बिकॉज द क्रॉस सेक्शन एरिया ऑफ द ब्लेड इज नॉट गोइंग टू चेंज. सर, फर्स्ट ऑफ ऑल, सो कैन बी राइट इन इंपल्स टर्बाइन प्रेशर ऑन द मूविंग ब्लेड रिमेन सेम. इन reaction turbine, pressure on the moving blade is decreasing. In impulse turbine, velocity on moving blade decreasing. In reaction turbine, velocity on moving blade is also decreasing, because ultimately it is doing the mechanical work. It is converting into the mechanical work. That's why in the impulse and reaction turbine, on the moving blade, in both the case, my dear, both the case, your kinetic energy is decreasing. Sir, is this summary clear to all? Please write in the comment section. Is this summary clear to everyone? देखो one by one when you will cover na, I'll try my best. This topic is the most difficult topic for you guys. One is the steam turbine, second is the compressor. I'll try my best. Within this session you will be so confident that tonight or tomorrow you are able to solve 5 to 10, 10 to 20 problem related to steam turbine or related to the compressor, my dear. Good, because I know very well steam power plant and gas power plant is moreover clear to you, but you are having most of the time you try to skip this topic, my dear. After that, now the question come, so this point whatever you have discussed now, this is just the structure of the blade. You have divided two type of turbine based on the structure on the moving blade. Yes or no? Agree or not? Write in the comment section. Agree or not, my dear friend? Write in the comment section. You have divided your turbine into two parts, that is clearly based on the moving blade cross section, based on the structure of the moving blade. But the big question is, sir, it is not possible. It is not possible to decrease the pressure, so much of pressure on a single blade. Are you getting my point? It is not possible to decrease the pressure on the single blade. So what you do, you connect the row of blades. आप बहुत सारी row connect कर रहे हो. Now the compounding of the turbine is the method. It's a way to connect the number of stages in such a manner so that you can decrease either pressure in a very slow manner or the velocity in a very slow manner. So compounding is the connecting of the stage in the series. In the axial turbine like this you are having the lot of series. Are you able to feel? 10, 20, 30, 40 series are there. One stage means moving blade, fixed blade, one stage. Second stage, third, fourth, sixth, like this. So in which manner you are just connecting these all the stages so that you can do or you can compound all the stage and you can decrease either pressure very slowly or velocity very slowly. Are you feeling the difference between the impulse turbine difference and compounding topic? Are you feeling the difference? Impulse and reaction is the difference between the blade structure, but compounding is the method of connection of the stage. Getting this point? Now, when you are talking about, yes, each stage is having the fixed blade. Yes, we are coming. Sujis, now, what is the meaning of the pressure compounding, my dear? Pressure compounding is you are having a target in such a manner. You are having a target in such a manner, my dear friend, that you are decreasing the pressure in a very slow manner. If you focus on this point now, so for this case, what you are doing, you are in the starting, you are attaching a nozzle, after that moving blade, then fixed blade, then moving blade, then fixed blade. So what you are doing, moving blade are just like an impulse blade. So in this case, when moving blade are just like an impulse blade, then can you please tell me what will be the effect on the pressure on the impulse blade? Sir, constant, na? What is the effect on the velocity? It will decrease because it will do the mechanical work. After that, on fixed blade, it will behave like a nozzle. Pressure will decrease, velocity will increase. Are you getting my point? After that, again moving blade, pressure will be constant, velocity will decrease because it is doing the mechanical work. After that, nozzle. After that, moving blade like this. After that, pressure and this. Focus on the pressure line. Focus on the pressure line, my dear. Are you not feeling pressure is going to decrease in a very slow manner? Check it. Are you not feeling, my dear, that pressure is going to decrease in a very slow manner? Yes or no? Your focus is to decrease the pressure in a very slow manner. Check it. In stages, it is going to decrease. Sujis, in stages, it is going to decrease because on the fixed blade, it is not going to change. On the moving blade, it is not going to change. On the fixed blade, it is going to decrease. Getting my point? velocity is constant, velocity is decreasing. So this is the point. So this is the way of compounding, how you are attaching these all the stages. अब clear हुआ? कुछ difference समझ में आया? What you are doing with these all the topics, my dear? Are you feeling? All of you? Everyone? All of you feeling from here what we are doing in this case, my dear? Yeah, I'm coming on the velocity turbine. Now, what is the velocity compounding? Sir, in this case of the velocity turbine compounding, what you do, in fixed blade, you are not using the nozzle. In the fixed blade, you are also using the profile type of blade only. This is the difference. You are using the profile type of blade only. This one. This one. You are using the profile type of blade. Getting? So, if it is the profile type of blade on the fix, then definitely pressure is not going to decrease. Velocity will be constant, my dear. So, velocity is constant on fixed blade, pressure is constant because the cross section is same. But on the moving blade, velocity is converted into the mechanical work. So, velocity is decreasing and it is doing the mechanical work. So, this is the compounding or the cartridge turbine. Okay. After that, the velocity triangle, my dear, alpha 1, beta 1. This is the beta 2 and this one is alpha 2, my dear. Now, this one is a simple nozzle velocity is given to us because it is the conversion of the kinetic energy. It one is the conversion of the kinetic energy. But if it is the impulse turbine, my dear, impulse turbine, let me tell you, if it is the example of the impulse turbine, like this. Can you please tell me, in the impulse turbine, this space at the inlet and outlet is same or different, my dear? In the impulse turbine, write the answer correctly. In the impulse turbine, this space is constant, increasing or decreasing? Yes. In impulse turbine, this area, cross section area is constant. No, constant. In profile type of blade, constant area is there, my dear. No. This area is constant. We always draw the profile in such a manner that this area is constant, my dear. Generally, there are two important velocity, you know. One is known as V1 velocity, that is the absolute velocity at inlet and outlet. All good? Okay. I think it was the network problem, if I'm not wrong. Okay. Now is all good now? Yes. Just give me 1 minute. Let me connect all the devices. Yes. You just write in the comment section, is all good or not? Now, let me check the audio, video. Is everything fine? Okay, great. Can we move forward? Yes. So there are two important velocity, you know, that one is the relative velocity and second is the absolute velocity. So in turbine, my dear, V1 is greater than V2. Absolute velocity is going to decrease. Reason is very simple. It is going to convert into the mechanical work. But relative velocity in this case, let me tell you, is constant if there is no friction. Otherwise, if there is a friction between the blade, my dear, then definitely VR1 is greater than VR2 if it is a friction. Otherwise, this is the very important indication. In ideal condition, my dear, ideal condition, relative velocity at the inlet and outlet will be the same. Why it is not working? Okay. If it is the inlet and outlet condition, then relative velocity will be the constant in impulse turbine and relative velocity will increase in reaction turbine. Okay, it will increase in reaction turbine. That VR2 is greater than VR1. You must know this point. In reaction turbine, your relative velocity is increasing, and in impulse turbine, your relative velocity is constant. Do you know the reason? Because in the impulse turbine, you are having the perfect cross-section area on the moving blade. But my dear, in case of the reaction turbine, you are having the aerofoil type of shape of converging cross-section area. When you are moving forward, then your cross-section area is going to decrease. 1 minute. Yes. Internet is not connecting. On my screen. Okay. Yes. Come back. So, if I draw the velocity triangle, so in this case, my dear, if this VR1 and VR2 in ideal condition are same, then you can simply say it is the best example of the impulse turbine. In the next point, if this VR2 is greater than VR1, then it is the example of the reaction turbine. Then it will be the example of the reaction turbine. Are you getting my point? The difference between the impulse and the reaction turbine, relative velocity at the outlet of the reaction turbine is higher than the inlet of the reaction turbine. In case of the relative term, because of the converging cross-section area, and in impulse turbine, both relative velocity are same, my dear. Both relative velocity are same. Okay. Correct. Next, let's discuss some important parameter. One is known as the velocity parameter or the velocity ratio, that is given by rho. It will be equal to U divided by V1, and where V1 is your impulse turbine, V1 is your nozzle velocity. K already we have discussed. Blade friction angle, my dear, it is equal to VR2 divided by VR1. After that, let's come to the next point. What is the diagram efficiency? Diagram efficiency can be written like this, VW, or it can also be written like this, M and M will be cancelled out. V will be the blade velocity, it will be equal to VW1 plus of VW2, my dear, into U divided by 2V1 square. Even this term is also written here like this. Okay. So this will be the diagram velocity for this parameter. You must know what is the value of BW1 by solving this triangle. You must know what is the value of BW2, because in this case, alpha is given to us like this. So this is the stage efficiency we are talking about. What is the total efficiency? Stage efficiency, sir, change of enthalpy, BW1 into U. After that, what is the axial force on the wheel? That is equal to VF1 and VF2. If I will find the condition of maximum efficiency, it can be written as rho optimum. What should be the value? That is U divided by V1 must be equal to cos alpha, my dear, by 2. And maximum efficiency in this case must be equal to, can you please tell me the answer? What is the maximum efficiency in the impulse turbine, my dear? In the impulse turbine, maximum efficiency will be this one. So at least you are aware with these formulas. इतने formulas भी अगर आपको पता है, you will be able to solve the questions related to the impulse turbine and related to the reaction turbine, my dear. Definitely you are able to solve the question if only these parameters are known to us. इतने पैरामीटर्स भी अगर आपको पता होते हैं तो एटलीस्ट आप सॉल्व कर सकते हो. आफ्टर दैट, व्हाट इज द डिग्री ऑफ रिएक्शन? Degree of reaction is the change of enthalpy on the moving blade to the change of enthalpy of a stage. Alpha is the nozzle angle. Alpha is the nozzle angle. Already I have written. And in any question, my dear, nozzle angle will be absolutely given to us. Nozzle angle. Okay. After that, if the degree of reaction is 0, that is normally known as truly impulse turbine, not tally, it is truly impulse turbine. 100% reaction is known as hero turbine and 50% turbine is the Parson turbine, my dear. When you discuss the Parson turbine, then what is the condition for the 50% reaction turbine, sir? Already we have discussed that for 50% reaction turbine, my dear, that is also known as Parson turbine. Parson turbine, what will be the formula for this case? First of all, we know some important condition from here, that sir, alpha nozzle angle at inlet must be equal to blade angle at outlet, and this alpha to absolute angle at outlet must be blade angle at inlet. First thing, absolute velocity at inlet from nozzle must be equal to VR2, and my dear, V2 must be equal to VR1. These important parameter must be known to us if we all are able to solve the question related to this one. And after that, the maximum diagram efficiency of this reaction turbine can be written by 2 cos square alpha divided by 1 plus cos square alpha, my dear. It will be the numerical value of the maximum efficiency of maximum diagram efficiency of the Parson turbine. Sir, if for the Parson turbine, if you are able to recall these all the formulas, then this will be more than sufficient for the Parson turbine. So again, in this topic, my dear, you have to solve the question related to the impulse turbine. What is the impulse turbine formula? 2VW1 plus VW2 divided by V1 square. Clear to all? What is the maximum efficiency for the impulse turbine? Cos square alpha. Similarly, what is the maximum efficiency for the Parson turbine? So 2 cos square alpha 1 plus cos square alpha. What is the condition for the 50% reaction turbine or the Parson turbine? Sir, alpha is the nozzle angle, my dear friend. Is the nozzle angle that is always at the inlet, my dear. And after that, if you want to write what is actually diagram efficiency, you write from the starting, that will be equal to, my dear, total work done, that is M into VW1 plus of VW2, we have already written this point, into U divided by total kinetic energy that is coming from the nozzle, my dear, coming from the nozzle. This is the diagram efficiency, and this is also known as mechanical efficiency. Sir, why mechanical efficiency? Because kinetic energy is the one form of mechanical energy, and work whatever you are producing now, that is also one kind of mechanical energy. So mechanical to mechanical you are calculating, that is the reason diagram efficiency is known as blade efficiency. Blade efficiency is also known as mechanical efficiency. Someone of you have earlier started in the starting ask, sir, what is the meaning of the blade efficiency? What is the meaning of the mechanical efficiency? When mechanical, one form of the mechanical energy is going to convert it into other form of the mechanical energy, then this one is known as. So let me tell you numerical aspect of this important topic, my dear, related to turbine. Let me discuss first of all, Sroth. First, sir, related to impulse turbine, what exactly you need to calculate impulse turbine? First, you need to know what is the value of power output. Can I write M VW1 plus VW2 into U? U is the blade velocity. My dear, U in this case is the blade velocity. are we not able to find the value of u, that is blade velocity? Are you not able to find that u will be equal to 2 pi n by 60 and d by 60? Blade velocity, pi d n by 60, we always write like this. Pi d n by 60, we always write like this. Agree or not? So blade velocity is known to us, and after solving the velocity triangle of the impulse turbine, my dear, only the purpose, because nozzle velocity is a measurable quantity that can be measured. So nozzle velocity and, my dear, nozzle angle, these are the given parameter in most of the problem. V1 and alpha 1 is the known parameter for us. V1 and alpha 1 and u is known to us. We can easily find the value of BW1 and BW2. If BW1 and BW2 is known to us, my dear, we can find the efficiency. We can find the efficiency. We can also find the condition for the maximum efficiency, because alpha 1 is the nozzle angle. This is the u optimum. We can also find the maximum efficiency like this. Okay. After that, second question related to the impulse turbine. What is the condition for the maximum efficiency of the diagram in reaction? That is again BW1 plus BW2 into u divided by this. If I solve this entire problem for the maximum efficiency, then maximum efficiency can be written like this. Again, the formula of the maximum efficiency can be written like this. This will be the simply the diagram efficiency for impulse turbine. Impulse turbine. So impulse turbine we have discussed. Parson turbine we have also discussed, my dear. In this case, 50% reaction means Parson turbine. Just in the previous topic, we have already discussed the portion of the Parson turbine. We have already discussed in this case what will be the effect on this Parson turbine, my dear. Let's move forward and discuss the next and the last important topic of the power plant, that is the compressor, my dear. Compressor. Sir, some I will ask to all of you. पता नहीं बाकी लोग कहाँ चले गए, थोड़ी देर को नेट चला गया था तो. You all people try to run away from the problem. For 1 to 2 minutes there was a problem at net, and then definitely you ran away. Come back. Sir, this is the last important topic before the compressible flow of the power plant. I just want to know, my dear friend, because this is the very lengthy topic of the entire thermodynamic, and that is the reason from this particular topic at least 2-3 question, at least 2 questions you can just expect, either related to Brayton cycle, related to Rankine cycle, related to turbine, whatever we have discussed, theoretical, numerical, or related to this compressor. Let me tell you, my dear, compressor. In the compressor, I am going to discuss again all numerical portion in such a way so that you will be able to solve each and every problem. First of all, tell me, sir, till the topic of the steam turbine, everything theoretical as well as numerical portion clear to all or not, my dear? Tell me the point. Theoretical and numerical clear to all or not, my dear? Very nice, Srut. Only you are there. Very good, Midhun. Sujis, where are you? ये तेजू कहाँ है? Washing powder Nirma, where are you? Okay, Sujis, very good, wonderful. Okay, sir, हूँ यहाँ पे. Very good, Malays. Okay. पता नहीं आपके friend कहाँ गए? Let me share the session. Rohina, because from here I am going to start very important and very easy topic of this power plant, my dear. You generally skip, that is related to the power plant, that is the compressor or the centrifugal plus reciprocating compressor. You just share the session with your friend, because कुछ देर के बाद में फिर से चिल्लाएंगे सर कंप्रेसर हमको करना था. and after 2-3 days they will ask the same doubt, but the same thing we are going to cover in the session, my dear. 2-3 दिन के बाद वही क्वेश्चन आएगा जो हम अभी कर रहे हैं. Okay, चलिए, let's start the session. You can take the break of 1 to 2 minutes if you want to take. Let's take a break of 2 minutes. After 2 minutes we'll come back and start this topic of the compressor. 2 minutes का break लेते हैं. 2 minutes I think more than sufficient if I'm not wrong. Maggie बनाओ and after 2 minutes we'll come back. Okay. Okay, 5 minutes. Okay. Take the 5-minute break. No issue. See you at. Okay, take the 5 minutes. 10 minutes you want to take? Mention earlier. If you want to take the 10 minutes, my dear, it is okay. You want to take the break of 10 minutes? The time is 1:04. See you all. It is okay. Okay for all of you? Yes. See you at 1:15 p.m. I think 10 minutes is there. आराम से चाय बाय पी लो. Again, next 3 hours, again we are going to clear this reciprocating compressor. After that, IC engine. After that, refrigeration, and finally psychrometric. All the topic we are going to cover in the today's session, my dear. Each and everything which may be asked in the exam, definitely I am going to cover each and everything here. See you again after 5-10 minutes. हाँ. So welcome back. You just write in the comment section, is all fine or not? Can we start again? Is everything clear, my dear? Audio, video all set? Can we move forward? Good. Okay. Okay, good. Sujis, centrifugal compressor topic. Very easy, I think. No, total compressor topic is very easy, my dear. One by one, we are going to discuss everything. All fine? Great. So, let's start, my dear. Compressor. Compressor is a work absorbing device. You have to do some work in this case, which is used to increase the pressure of the fluid at the cost of work done. Whatever work you are going to do on the system, my dear, on the compressor, that is going to increase the enthalpy, or at the last you can say that is going to increase the pressure of a working substance or the working medium, my dear. Okay. After that, if the compressor is going to enter at this place and the compressor is leaving at this point, my dear, compressed air is going to leave at this point, then if the pressure of this point is P1 and the pressure of this point is P2, my dear, then simply after passing through the compressor, then P2 by P1 greater than 1. This is the ideal requirement of the compressor, whatever you want. But this is also the requirement of the blower. This is also the requirement of the fan. So in generally we want that pressure P2 by P1 must be greater than 2.5. Then it will be considered as a compressor. Lower than this, you will say that maybe the blower or it may be the fan, my dear. Blower, fan or compressor. Okay. So after one, any working device, maybe the compressor, maybe the blower or maybe the fan, but after 2.5, if the compression ratio, pressure ratio is there, my dear, then definitely it is the example of the compressor. Generally, to do the compression in a system, we are having two type of device. One is known as positive displacement type of device, and second is known as rotary or the dynamic device. Sir, what is the meaning of the positive displacement type of device? Positive displacement type of device is you are going to trap your volume within the system and you are just compressing the volume. That's why you are increasing the pressure. Are you getting my point? You are trapping your volume inside a controlled volume, then again system is closed, then you apply some force, your volume is decreasing and your pressure is increasing. Are you getting this point? Like the example of a reciprocating compressor. Clear to all? First of all, is this point clear to everyone, my dear? Reciprocating compressor for all of you. Great. Second, what is the meaning of this rotary compressor or the dynamic compressor? Sir, in this rotary or the dynamic compressor, what exactly you are doing, my dear? That first of all, you are imparting some energy to the working fluid in the form of kinetic energy. Means a shaft is rotating, with the shaft some blade are attached, shaft is rotating, your blade are also rotating, and when the fluid will come into the contact of these blade, that will attain some kinetic energy. So first of all, some form of the energy is imparted over the fluid, and after that this kinetic energy is converted into the pressure energy to get the sufficient value of the pressure. Are you getting? There are two different ways. In positive displacement type of compressor, yes, In positive displacement type of compressor, the working is intermittent. Intermittent means for some time your flow will be stopped because you are trapping your working medium. You are trapping your air within the control volume. So that's why you take the air, trap it, compress it and discharge it. So for some time, some duration of the time, your process or your output and outlet and inlet delivery will be discontinued. Getting my point in this positive displacement. But in case of rotary or my dear, in case of dynamic compressor, your flow will be continue energy is supplying. After that it is passing to the diffuser to increase the pressure, continues from the back side, working fluid is also coming. That example is your centrifugal compressor. Yes, best example of this topic is the centrifugal compressor, my dear. Example of this one is the centrifugal compressor. In this topic we are going to cover first of all reciprocating compressor, my dear friend, and second is the centrifugal compressor. Centrifugal compressor and reciprocating compressor both are very easy topic for the mechanical engineers, and even this reciprocating compressor is nothing but just an example of the piston cylinder arrangement. Sir, if you have studied the piston cylinder arrangement in basic thermodynamics now, then you are not going to feel any single problem in this topic of the positive displacement compressor. Are you getting my point? In this reciprocating compressor, you are not going to feel a single problem if you have already discussed the piston cylinder arrangement device in the basic thermodynamics. Clear? Let's see. Sir, reciprocating compressor. Let's draw. This is the suction volume. If I draw, my dear, how the air is going to enter into the system and how this work. Let's try to discuss this entire problem. My dear, this one is a discharge. Here I want my pressure is 10 bar. 10 bar pressure is required to me in the control tank, and after that this one is suction where the pressure is available only the atmospheric pressure. Are you getting my point? 1 atm, or you can write 1.013 bar, my dear. So what is your purpose? You want to increase your pressure from 1 bar to 10 bar. Now, what is the PV diagram of this entire problem? Without clearance, if I draw, then suction will started from this point, that is at the suction pressure, my dear, that is P1. After that both valve will be closed, then your 1 to 2, my dear, it will be the compression process till the discharge pressure, and after that when it will reach to the discharge pressure, then definitely, my dear, volume will decrease and pressure will increase. Your working medium will discharge to the system, because until unless your valve will not open. Now, so this one is going to define the suction pressure, P of suction, and this one is going to define the P of discharge, and this is the process of compression. This is the main process of the compression you are doing when both the valve at the inlet and outlet are closed, my dear. Compressor is example of a open or closed system. 100% it's example of a open system. So if you want to find the numerical value of the work done in this case, my dear, you can easily compress your working medium into 3 ways. One, this one, adiabatic. Getting my point? Second, lower slope, polytropic. Third, my dear, isothermal. You know very well, area of the diagram is known as, in thermodynamic, area of the diagram is known as the work required in the compressor. Can you please tell me, out of these all the 3 processes, which will require the minimum amount of the work done? Yes, yes. Which will require the minimum amount of the work done? I mean, isothermal, adiabatic, polytropic, which one? What do you think? Isothermal. So can we write the work done in the isothermal, my dear? It will be equal to, if I write P1 V1 ln V2 by V1 if I'm not wrong. Yes or no? But you know very well that isothermal work is not possible because it's a very slow process. What is the next one? Then it will be better you will go with the polytropic work done. What is the polytropic work done? Can we write like this? P2 V2 minus of P1 V1 n minus 1 into n, my dear. It will be equal to n into n minus 1. If I'll just solve it, then this value will be equal to n P1 V1 divided by P1 V1 n minus 1 upon n minus of 1. Or similarly, work of polytropic will be equal to n upon n minus 1. P1 V1 means actual volume that is going to enter into the system. V1 means actual volume that is going to enter into the system. P2 by P1 raised to n minus 1 upon n minus of 1, my dear. This can also be written as n upon n1 minus OK. P1 V1 will be equal to MRT1 if you don't mind. Can I write like this? P2 divided by P1 raised to n minus 1 upon n minus of 1. So are you not feeling? This is the total amount of the work that can be done in actual process. In actual process, this is the requirement of the work when you want to increase the pressure from P1 to P2, when your actual volume is entering with the mass of M and temperature of T1. At this point, my dear, your actual volume is going to enter into the system with the mass of M and temperature of T2. This will be the example. Clear to all? So, two formula you can write. The work done of polytropic process can be written like this. Can be written like this. Okay, without clearance is there, my dear. This is the work done without clearance. But in actual problem, you know very well, in actual problem, if I draw the piston cylinder arrangement like this, my dear, if I draw the piston cylinder arrangement like this, then definitely it is not possible. Yes or no? Definitely it is not possible to have the zero clearance. So some clearance we have to provide it, and that volume is not known as clearance volume. And between this top dead center and bottom dead center, what volume we have to swept, my dear, that is known as swept volume. And from here, because we are not able to cover the entire volume, this very important ratio is introduced, that is known as, what is it? Clearance ratio. Can you please tell me what is the value of the clearance ratio? Anyone? What is the numerical value of the clearance ratio, my dear? Can we write clearance ratio will be equal to VC divided by VS? Is it or not? Yes. Now, what will be the total amount of the work done with clearance? If I'll ask what is the total amount of the work done with clearance in this case, my dear, can we write total amount of the work done with clearance can be written by n upon n minus 1 into P1 into V actual of air that is going to enter into the system, P2 by P1 minus of 1, polytropic index. Only this actual volume is entering into the system is changing in this case. Why, sir? Because in the previous volume or previous case, this total volume was entering into the system, but in this case, the actual volume is not entering into the system, that is V1. So in this case, only one term will be changed. P1, but actual volume is changed by V1 minus of V4, that will be equal to P2 divided by P1 raised to n minus 1 divided by n minus of 1. Okay, so this one is a work done of polytropic process with clearance, my dear. This one is the work done of the polytropic process without clearance. Most of the time, yes, most of the time this question is asked to us. What is not without, it is with clearance. Asked to us what is the work done without clearance and what is the work done with clearance in first portion of the reciprocating compressor, my dear. Tell me very honestly, is this part clear to all? How will you find the numerical value of the reciprocating compressor work without clearance or with clearance? Clear to everyone? Malesh, Midun and Sujis, Teju, is this point clear to all? Very nice, very nice. But after that, my dear, when you feel in this case, then in this case, by introducing the clearance between the cylinder head and the piston, now there is a one problem you have just introduced. What is that problem, sir? Sir, in this region, if you are not wrong, then in this region your piston is sliding here to there. From this point to this point your piston is sliding. That's why this is known as swept volume. But your actual volume is entering with this amount, my dear. So by providing the clearance, yes, work is asked. Midun, work is asked only. From here, question is only one, that P1, P2 is given. I want to increase my pressure from this limit to this limit. Then what will be the value? Polytropic index is also given to us. Then what will be the numerical value of the work done without clearance? Most of the time without clearance is asked in the GATE exam. So from this only one numerical is there up to this. That is what is the work done of the polytropic process. But let me tell you in advance, my dear friend. Yes, let me tell you in advance from upcoming topic, that is the intercooling, is one of the favorite topic of the GATE exam from this portion. Okay, now come back. Sir, there is one problem come, that actual volume that is entering into the system is a little bit lesser. It is a little, give me 1 minute only. Okay. Yes. So the actual volume that is going to enter into the system, that is little bit lesser than the swept volume swept by the piston. So definitely when ideal and actual thing are not matching, a very important concept come into the picture. Can you please tell me? When ideal and actual things are not matching, a very important concept come into the picture. Any one of you can give me the name of that? Anyone? Efficiency. Because it is the efficiency related to the volume, my dear. So here the volumetric efficiency will come into the picture. Yes or no? Here the volumetric efficiency will come into the picture. So from here we write the volumetric efficiency. Generally the volumetric efficiency is actual volume that is entering of the air and swept volume by the piston. Generally, let me write actual volume. There are lot of way to calculate the actual volume, my dear. Sometimes mass is given to us, mass flow rate, and if you will multiply with the specific volume of the air, you will calculate the actual volume. This is the one way to calculate the actual volume. Swept volume, my dear. Swept volume is nothing but 5/4 d square into L. It is the swept volume into NY system, NY 60. With what RPM it is going to rotate, my dear? Meter cube per second. Meter cube per second. So this is the one way to calculate the actual volume and the swept volume, my dear. But again, story does not end here. With this one, when we substitute all the values, then clearance volume or this volumetric efficiency can also be write in the term of P2 raised to P1 1 by n minus of 1. It can also be written by V1 raised to V2 minus of 1. So these all parameters are just the numerical value of clearance volume. So these are the three important way to find the volumetric efficiency, my dear. Sorry, two important way. One is this: directly calculate the actual volume that is entering into the system and find the actual volume and find the swept volume, get the answer. Third, or the second one, you can get the direct formula of the swept volume. You can get the direct formula of the volumetric efficiency and you can apply it into the equation. Sir, clear to all? Yes. Volumetric efficiency we have already written. One minus. Yes, you can also write in the term of temperature. Sir, mass flow rate, Sujis, mass flow rate is given to us in kg per second. Specific volume is meter cube per kg. Kg will be cancelled. Final answer will be in meter cube per second. Okay. This also can be converted into the temperature if you want, my dear. This also numerical value can be converted into the temperature if you want. Now, this is all about the, yes, exactly. This one is the all about the volumetric efficiency you can find. After that, let's move towards a very important topic. Why the multi-stage compression is required, my dear. Sometime, let me share an important point. Sometime, sir, from a single given compressor, if you will increase P2 by P1, whenever a very high value of the pressure ratio is required, when this value will be increased a lot, what is the effect on the volumetric efficiency? When in bracket term will increase with the very high value, what is the effect on the overall volumetric efficiency? Can you please tell me the answer? What is the effect on overall volumetric efficiency? So are you getting? In a single compressor, my dear, single compressor, when the pressure ratio is going to increase, means it is not possible that what pressure you want to increase, you can increase in a single compressor. Not possible at all. Why, sir? Because when you are going to increase the pressure now in a single compressor, then ultimately volumetric efficiency will going to increase. Decrease. What is the effect on decreasing the volumetric efficiency? Actual volume is entering into the system will decrease. Getting my point? So, it may be the time if this numerical value like this, epsilon P2 by P1, 1 by gamma, minus of 1, if this numerical value become 1, at that time, my dear, 1 minus 1 will be the 0, volumetric efficiency will be 0. It means you want to increase a lot of pressure in the compressor, but volumetric efficiency is 0. What is the meaning of it? Your piston is just sliding. Your piston is just traveling from top dead center to bottom dead center. There is no effect on the volume. There is no such volume that is going to enter into the system, my dear. Enter into the compressor, my dear. That's why up to a limit, if you want to increase the pressure, it is okay. But after the limit, if you want to increase the pressure, definitely it's dangerous, my dear, for all of us. So what do you do? There is a limit in a single stage compression. If the compression ratio is increased, then volumetric efficiency decrease. One theoretical question, Malice. One theoretical question, my dear. Decrease to such extent that pressure ratio at this numerical value, your volumetric efficiency becomes 0. कोई मतलब नहीं उसका. It will become 0, my dear. Also, as the pressure ratio increase, the leakage pass to the piston increase, bulky cylinder is required. That's why multi-stage compression is preferred. Generally, up to the 5.6 bar of atmospheric air If you want to compress, single stage is better, but after that you must go with the multi-stage compressor in this case. Then if it is up to the 185 bar, then you must go with the 3-stage compressor in this case, my dear. Now, sir, this one is a perfect intercooling. Perfect intercooling in multi-stage compression. Like if I will draw the PV and TS diagram of this multi-stage compressor, my dear, so just try to feel it will look like PV and TS diagram. Sir, from one compressor is entering into the first compressor, 1 to 2 it is the compression process, 2 to 3 it is a heat exchange process, and 3 to 4 it is the second, and after that it will be discharged. This is the PV diagram. Is it or not? So this is P3, this is P1, and this is P2, my dear. This is the PV diagram. After that, if I draw the same process on the TS, can any one of you draw the process? Sir, 1 to 2 isentropic compression, 2 to 3 isobaric cooling, and 3 to 4 again isentropic compression. Is it? When you say for the perfect intercooling, you always say that there is the perfect intercooling now. It means T1 is numerical equal to T3, my dear. Or in this case, for minimum work required, P intermediate, that is P2, must be equal to P3 by P1. Already we have discussed for the minimum work done. Yes. Or can we write like this? P2 by P1 will be equal to P3 by P2 will be equal to P4 by P3 will be equal to Pn plus 1 divided by Pn is equal to constant. What we are getting? Pressure ratio in each and every stage of the compressor is same, my dear. If you want to use the multi-stage compressor, if this is the compressor, for example, in this case, my dear, P2 by P1 will be the 10, then in this case, P4 by P3 must be the 10. Are you getting my point? If you are having this kind of pressure ratio in the compression or in the pressure in the compressor, then definitely you are going to accept that your multi-stage compressor will require the minimum amount of the work done. Are you getting my point? Now, how many number of stages will be required? Can we write like this? To increase this final pressure from the initial pressure, how many number of stages will be required? Can I multiply all the values? P2 by P1, multiply by P3 by P2, multiply by P4 by P3. Is it or not? All of you, can we substitute all the values to find this? C into C into C into C like this. Can we write? Okay, sorry. Can we write the numerical value? That to find the number of stages, my dear, it is equal to n, where n is the number of stage and where C is the pressure ratio of a single stage of compressor. Are you getting my point? The pressure ratio of a single stage of compressor. If you are having the 3 stage, then every stage is having some pressure ratio. Numerical value of the C is the pressure ratio of each stage. So if you want to increase your pressure from 1 bar to 200 bar, and if it is asked what will be the number of stages required, my dear? What you can do in this case, you can easily write how many number of stages required by calculating the formula of equation 1 and formula of equation 2, my dear. Tell me all, is it clear to everyone? In the multi-stage compression with the perfect intercooling, are you able to find how many number of stages will be required or not, my dear? Please write in the comment section. All of you, is it clear? Good. So, 3 type of numerical question may be asked from this topic. 1, related to numerical work done in the reciprocating compressor, my dear. सुनो सही से, numerical work done in the reciprocating compressor. Second, good, wonderful, wonderful. Second, volumetric efficiency. You are having the 2 important formula to find the volumetric efficiency. One formula related to actual work divided by swept volume. Actual volume divided by swept volume. Second formula in the term of the pressure ratio. Second numerical. Third, in the multi-stage compressor, what is the condition of the minimum work when the perfect intercooling is there between all the stages, my dear? These 3 type of question will be asked from the reciprocating compressor. How many of you are fully confident कि sir answer ले आएंगे? If the question from any part of this reciprocating compressor will be asked, we are able to solve the answer, my dear. Please write in the comment section. Write down, I am waiting for the answer. How many of you are sure that कि sir answer आ जाएगा if the question related to reciprocating compressor is asked? Yes, tell me the answer. किसी का आंसर क्यों नहीं आ रहा? Are you having some confidence? Nice, thank God. किसी को तो कॉन्फिडेंस आया, चंपक. Okay, चलिए, let's come to the point, my dear. Sure. And if you want, my dear, within the comment section, you just write the list of the question. For example, after that, only one topic is left, my dear, that is the compressible flow. So I don't even, and you should not waste your time. I don't want to waste your more time. If you feel, sir, I am very good in this Brayton cycle problem, don't ask for the question. If you feel I am very good in this centrifugal part, don't write in the comment section. After just completion of the power plant, I'll give you the reminder, my dear. Write the topic for which topic you want the session as a practice session. Like if you want for the centrifugal compressor, if you want for the reciprocating compressor or the steam turbine, or from the steam turbine, or from steam power plant, like this, you can write the session. So today I'll just make the session, and shortly I'll just arrange one more session for you guys. Most probably this Sunday. It will be, I think, okay for you if you don't mind. This Sunday? Yeah. Good. Great. Nice. No. Sir, centrifugal compressor. See, if you have not studied this topic, I'll give you hardly 3 to 4 points for it. You just mug up these all the 4 formulas or point, my dear. Recall these all the formulas or point, my dear. It will be more than sufficient to solve problem related to the centrifugal compressor if asked. Let me tell you, till now no question is asked in the GATE exam from the centrifugal compressor. That is the reason I am not going to force you that you need to cover each and everything. No, what things are required, my dear, if you are able to write only these things, now then these will be the more than sufficient to solve the problem if they ask from this topic, my dear. Sir, what is the centrifugal compressor? The centrifugal compressor is a radial flow machine turbine compressing the fluid due to the dynamic action. Dynamic action means centrifugal action. They provide the energy into the kinetic energy to the fluid, and after that they are converted into the pressure energy. After impeller mounted on the driving shaft, diffuser and volute casing, my dear. Working is very simple. Lot of time you have seen the air is going to suck from this one, and in the impeller it will be divided like this. In the impeller it will be divided like this, and after that this is the diffuser, my dear. It will circulate in this diffuser and it will leave the system like this. Okay, leave the system like this. This is the working. So radially your air is going to enter into the system. Okay, radially your air is going to enter into the system. So in this case, if I draw the velocity triangle, this is the radial impeller. Radial impeller, my dear. Now, your blade is moving in this way. This is your V1 velocity. Radially it is going to enter, but U is also there. That's why U1 is also there. So your relative velocity is going to enter at this place. Beta 1, this one is, my dear, BR1. This one is alpha 1, that is 90. Okay. So this is V1. VW1, VW1 is 0 because there is no component of V1, and after that, my dear, your at outlet, this is leaving the system like VR2 because it's a radial blade, and U2 is also there. So this is the U2, and my dear, this one is nothing but V2. This angle is the beta 2 and this angle is the alpha 2. This is the very common diagram of the radial blade compressor. Even you need not to worry about. You need not to draw this diagram, my dear. After that, anything if you need to focus is the ideal value of the work done. ये थोड़ा diagram टेढ़ा हो गया. What is the ideal value of the work? That work will be, we have already written like this, mass flow rate into VW2 plus minus VW1, is it or not, my dear, into U, or it can be written by M VW2 U2 plus minus VW1 into U1. Are you aware with this formula? Yes. So in this case, my dear, VW1 component is 0. So W will be equal to M into VW2 into U2, or W will be equal to, what is V? This is also VW2. So this will also be equal to M into U2 square, where U2 can be written, U2 can be written like pi D2 N divided by 60, where D2 is the outer blade diameter, my dear. Sir, till now, 2 formula I have written. Please write in the comment section if any one of you having the problem in these 2 formula. If any term is not aware to you, my dear. Anyone, please write in the comment section. If you are not aware with this term, can you please write in the comment section? Anyone is not aware with this formula? If you feel, sir, anything that this term, sir, I am not aware with. Question is very simple. The impeller of the centrifugal blade is rotating with the N at the outlet of the blade. Diameter is 20 centimeter, and mass flow rate of the air that is coming into the system or coming into the impeller, that is 20 kg per second. Then what will be the numerical value of the work required, my dear? Are you able to write this for, means are you aware with each and every alphabet or not? First of all, you tell me. N is the RPM of the impeller, because sir, this one is the impeller, this one Let me move forward. This one is the impeller. Are you not able to feel that this RPM of this impeller can be calculated, can be measured? Yes or no? Write the answer, my dear. Is it yes or no? All of you? So if RPM can be measured, then my dear, outlet velocity can also be measured, outlet diameter can also be measured, that is d2. So with this one, I am very well aware with the formula that U2 will be equal to pi d2 into n divided by 60. Let me tell you, this radial blade formula is a very common formula of this centrifugal blade. Even the forward and backward blade are also there, but most of the time or maximum time question is asked from this radial blade, my dear. So this one is the ideal work of the, this one is the ideal work required for the centrifugal compressor, my dear. But in that case, what is the problem? Problem is there is some loss due to the slip. There is some loss due to the actual power. That's why the actual work of this system is written by multiplying some important factor. That's a phi s is known as slip factor. And my dear, this phi w is known as power factor. Getting my point? Power factor. So the actual work done of the centrifugal compressor will be given by slip factor multiplied by power factor multiplied by U2 square. Sir, till now please tell me the answer. Are you feeling any problem up to it? Madhun, Sujis, Umar, any one of you feeling the problem in this case? No one? None of you? Great. After that, so this is the formula when actual work done is asked related to the centrifugal work, my dear. And after that, there is one topic where the thermomechanical analysis of the centrifugal work is done, my dear. What is it? Okay, where is M? You are asking where is M? Just a minute. What is the meaning of this M? Kilojoule per kg. No issue in it. Whenever kilowatt will be asked, then definitely you will multiply with mass. Whenever kilojoule per kg will be asked, you will write like this. It's not a big deal. Mass is not always a big deal, my dear. Okay. Clear? Umar? Great. After that, sir, let me tell you, till now, only one formula we have covered. Whenever you have to set your mind in such a way that I will tackle only the problem from the centrifugal compressor. Right now, if you are at 0, whenever actual work done for the centrifugal compressor, having the radial blade is asked. Radial blade is asked. This one. Second question may be asked, my dear, related to. Second question may be asked related to the thermomechanical analysis of the centrifugal work. Sir, what is the meaning of it? Generally, we are aware with it that if I will write in thermodynamic, what is the total actual work? Sir, in thermodynamic, what is the total actual work? Total actual work I want to know. Can we write total actual work? Can be written like? Yes or no? Yes or no? All of you? Okay. Is it or not, my dear? Is it or not? Good. So this is the total actual work in thermodynamic, and this is the total actual work in mechanical. Sorry. In mechanical, this is the total actual work like this. How much? Sir, m dot Sir, phi s power factor into U2 square. If I compare both, can we find this overall relation of this pressure ratio? Whenever I will draw the centrifugal compressor, the diagram will be somewhere like this. Sir, 1 to 2, it is the isentropic process. Sorry. Like this. So in this case, you can easily find what is the pressure ratio from here. So only two questions are there, my dear. One is the numerical value of the work done. Numerical value of the work done on the TS diagram like this. Thermodynamic work done we are aware with, and after that you can easily write what will be the numerical value of the work done from here, my dear. After that, if any one of you feeling the doubt, feel free to ask in this case. Yes, please. किसी को कहीं भी कुछ भी डाउट आ रहा है, you feel free to ask. Sir, I have just compared these both the equations. I have just compared these both the equations like this. And I have just calculated P02 divided by P01. It will be the work done multiplied by the centrifugal compressor efficiency like this. Yes, please tell me. Any one of you having the doubt in this case? Only two formula you need to recall again and again. That if outlet velocity or RPM is given to us, what is the U2 value, my dear? What is the actual work done of the compressor in the mechanical term? What is the actual work done of the compressor in thermodynamic term? You will compare most of the time. Sir, what about the MSQ question? I'm coming on the MSQ question. Give me 1 minute only. I'm coming. First of all, let's clear the numerical part. I just want to confirm. Is the numerical part clear to you or not? Yes, I'm coming on the point. Is the numerical part is clear to you or not, my dear? So two formula you write, it will be more than sufficient to solve the numerical related to centrifugal compressor. Let me tell you, generally most of the time you start to think like this. Then in the GATE 23, we are not going to discuss, we are not going to tackle any problem from the compressor. If you are not wrong, then hardly three important points are required to solve any problem of reciprocating compressor. Work done without clearance, work done with clearance, volumetric efficiency and multi-stage compressor. Yes or no? Yes or no, my dear? Yeah. What about this? Are you asking? Sir, this value is the P2. This value, my dear, is the P01. This value is P02. If it is the ideal work, then 1 to 02 it go. And if it is the actual, my dear, then 1 to 02 dash. So if you use this formula, either as it is, because most of the time, let me tell you, the U2 value is not given. That will be given in the term of pi d n term. Okay, why, sir? How we are drawing the, are you asking why this TS diagram is drawn? Do you want to ask like this? Why this TS diagram? What is the requirement to draw the TS diagram? Is it? Srut? Okay. What is the requirement of TS diagram? Very good question. Tell me. What is the requirement of velocity diagram, my dear? What is the requirement of the velocity diagram? Then you say, sir, we want to calculate the actual work done in this problem. That's why we have to draw the velocity diagram. Yes or no? In this problem, I want to find the maximum actual work done. That's why from this formula, I have got the actual work done like this. Phi s, slip factor, work factor or the power factor into U2 square. With the help of this one, I have got the actual work done. Similarly, when you are comparing the actual mechanical work done and actual thermodynamic work done, so you must know now that how this thermodynamic formula is coming. This is coming from here now. If it is the ideal, my dear, if it will be the ideal, then efficiency will be 1. Getting my point? Efficiency will be 1. So in that condition, my dear, T02 divided by T01 will be equal to somewhere like this. Yes. So TS diagram you have drawn to find the actual thermodynamic work done. Velocity triangle you have drawn to find the actual mechanical work done. Clear? After that, yes, very good, sir. Generally, theoretical question, very important theoretical question is there. Vanless space in centrifugal compressor. Vanless space in theoretical centrifugal compressor. Sir, this one is the impeller, my dear, that is going to rotate like this. Okay. After that, these are the diffuser. This is the fixed. Your fluid will start to flow like this. So, are you able to see that between this and this, my dear, between the diffuser and the impeller blades, we are having some space. We are having some gap. This gap is known as vanless space. First point, tell me. Theoretical question is there, my dear. First point, tell me, is this point clear to all? What is the vanless space? Between the diffuser and the outlet of the blade on impeller, we provide some space, and that space is known as vanless space. To make the proper turning, not burning. Okay, sorry. Yes. To make the proper burning of the air in combustion chamber after the compressor, because you know very well, air come to the combustion chamber after the compressor. So air is required, that must be at very low pressure and very low velocity also. Velocity must be very low. But when it is leaving from the impeller, my dear, then velocity is very high. So vanless space is required to reduce the Mach number or the velocity overall. It is the excessive variation of the centrifugal stress due to sticking of the air on the blade. Means if from the same speed, if it will be strike over it, then definitely due to the centrifugal force, stress will be developed in the body and there will be a chances of failure of the blades. That's why vanless space is provided, and vanless space is provided first to reduce the velocity. This vanless space is provided to reduce the velocity, and second, to reduce the variation of the centrifugal stress between the blade material and, my dear, your diffuser material. So generally it is asked, what is vanless space? This is the theoretical question, may be asked to you, but otherwise for the numerical, if you will follow two important formula, one important formula for the actual work done, my dear, for actual work done of the centrifugal compressor, and second, my dear, the relationship of the mechanical work and, my dear, thermodynamic work. Okay, good. After that, the last important formula or the topic we are going to discuss, the compressible flow. Let's start the topic. Again, new topic for maximum of you. For most of you, my dear, it will be the new topic. Yes or no? Yes or no? Tell me. How many of you have already covered this topic, my dear? किसी ने ऑलरेडी पहले किया है क्या? Anyone? No. No for me, Umar. Okay. Okay, good. Sir, if you are at 0, so let me tell you, these all point I'll just tell you in this slide, in this PPT, my dear, in such a manner that if you are attending the class of the today's session, it will be more than sufficient. You need not to go anywhere. Yes, if some typical problem, some difficult level of the problem will be asked, then again definitely you have to cover all the thing in little bit much detail, right? But if the basic level of question or 2 marks simple 2 marks problem or 1 marks problem is asked, then only if you are at 0, then in today's session I have just planned each and everything in such a manner that at least numerically you will be able to solve the problem related to the compressible flow. Don't worry about this, sir. One by one, I'll clearly mention before starting the topic, it will be asked for the numerical point of view and it may be asked as a theoretical point of view. Okay, so let's move forward. जल्दी से आगे बढ़ जाओ. There are 42. अच्छा 42 आपने कर दिया, 50 तो करो इनको. Can you make 50? Come back. Whenever you are tired, जब आपको लगे सर अब आगे थोड़ा रुकने की जरूरत है, you directly tell me and we can take the break. Otherwise जबरदस्ती के उस साइड में सो के मत करते रहना, right ना, that you are in the sleeping mode और पता चले मैं दीवारों को पढ़ा रहा हूं, ऐसा मत करना, right? Whenever you feel tired, whenever you feel that there is some requirement of the break, you try to write in the comment section. Otherwise from that side you are in the sleeping mode. मैं बस इधर से बोलते चले जा रहा हूं and you are not listening anything. Even सुन भी रहे हो, you are not going to focus on anything. Okay, चलिए, can we start? Because after each and every topic, my dear, you have to make some difference. Do you know, after each and every topic I discuss something other than technical part. The reason is so that, yes, I discuss something so that you can just shift yourself from the old topic to the new topic. Otherwise there will be a lot of mixing in the entire chapters, my dear. Because right now, if you feel, till now we are only going to discuss the one topic, that is the power plant, and definitely it is the last topic of the power plant for the GATE syllabus, that is the compressible flow. But again, IC engine is not completed, refrigeration is not completed, psychrometric is not completed. Okay, it is the different thing that the syllabus of the IC engine is not so more and the syllabus of the refrigeration is not so high, and similarly for the psychrometric. But definitely we have covered only the one chapter out of 4 chapters. And one thing let me tell you clearly, this one chapter I think is equivalent to other 3 chapters of the IC engine, refrigeration and psychrometric, right? Okay, come back, sir. Chaliye, let's start the topic. What is the compressible flow? The fluid whose density change under the pressure, my dear, is known as compressible flow. Okay, whatever you say, we can move in the same way. If you want the break, we can continue after the break, my dear. Come back, sir. Yes, what is the compressible flow? If the density change under the pressure, my dear, then flow is known as the compressible flow. Like in the case of air, if any working medium is going to flow, then definitely some pressure wave will be generated, and these pressure wave are the example of the flow in the compressible flow. Okay, good. Next, on this part I'll come later. First of all, you all are able to know what is the meaning of the compressible flow. Sir, compressible flow is the flow in which density can change. Like water density is not going to change, but in gas or air, my dear, density every second is going to change. Okay, chaliye. After that, let's discuss what is the meaning of the stagnation point. Sir, I just want to know, if the air is flowing like this, air is flowing like this. Okay, now at this point I just want to know how many number of energy right now this air is having. Can you please write the answer? One, definitely it is having the kinetic energy. It is yes or no, my dear. Second, please write in the comment section. One, it is having the kinetic energy, plus tell me the answer. It is having the potential energy, or yes or no? It is having the internal energy, yes or no? Internal energy, my dear friend, due to the temperature. And this combination of the internal energy and the potential energy is known as enthalpy. So whenever any working fluid is moving, it is having the total content of the energy is the summation of the kinetic energy plus of the internal energy, that will be simply known as enthalpy plus kinetic energy. It is clear to all, because this flow work or this potential energy is nothing but it is one kind of flow work. So can I say right now, my dear, this total amount of the work that this working medium or air is having, that is equal to kinetic energy plus of enthalpy. First of all, try to understand one by one. Can we write that total energy of this working medium or air that is flowing, that will be equal to 1 by 2 into V square plus of H, my dear, H into M. But generally we write the specific total energy. Total energy. Can we write like this? V square by 2 plus of specific enthalpy. Is it clear to everyone? First of all, from here we are going to start the concept, my dear. Yes. Okay. Right. First, you tell me the answer. Is this point clear to all? Total energy that a working medium can have in a compressible flow is the kinetic energy plus of enthalpy, Vomik. Okay, good. After that, sir, if I will ask, just a minute. If I draw enthalpy versus entropy diagram, so if this one is the point, then at this local point of H1 enthalpy is why the system due to the temperature, plus one more energy is also there, my dear. That is kinetic energy of the system. Is it okay? Is it okay for all of you? Nice. So now, what is the stagnation point we are going to define from here? Sir, if the, what is the vehicle that is moving with the very high speed, or the air that is moving with the very high speed, can you please tell me, if it will be stopped at this point due to sudden brake or due to the sudden obstruction, if it will be stopped, can you please tell me what will be the kinetic energy at that time? What will be the kinetic energy at that time, my dear? What will be the kinetic energy at that time? Can you please tell me the answer? All of you? Sir, 0. So at that time this kinetic, and you know very well kinetic energy or any energy cannot be created nor be destroyed. It can be transferred from one form to another form, my dear friend. So can we write at that time this will be stored into the total form of the energy? Yes or no? It will be converted, kinetic energy will be converted into the enthalpy. So in this case, can I write that stagnation point is the point at which kinetic energy becomes 0, and this kinetic energy is converted into the enthalpy, my dear. And this total enthalpy is known as stagnation point. Stagnation point means total energy of the working medium which is in the flow, which is in the motion. Let's now try to understand what is the stagnation point, my dear. When the fluid is brought to the 0 velocity isentropically, then the state is known as stagnation point. The property like temperature, pressure, density at the stagnation point are known as the stagnation property. Where this entire, like missile is having a very high velocity and suddenly on the target it will be stopped, total kinetic energy is converted into the enthalpy. Then at that time it is asked what is the stagnation enthalpy, what will be the temperature developed at that time at the target. So these are the all stagnation properties. Okay, now to find out, to calculate the numerical value of these all property is the ultimate aim of a mechanical engineer or the aerodynamic engineer, aerospace engineer. So can I write, if you don't mind, at the stagnation point, my dear, at stagnation point, H0 will be equal to H. H means local point enthalpy plus of V square by 2, where what is H, my dear? Local enthalpy, local specific enthalpy. What is H0? Stagnation enthalpy. Specific enthalpy. Okay. Any doubt? कोई doubt नहीं अभी तक? Good. Now, sir, before discussing these all the properties, let's move forward and try to discuss few important points. Sir, what is the speed of the sound? Whenever you disturb the medium, any medium or the compressible medium, when you disturb, then some pressure wave generate, my dear. Like you just throw a stone into a pond, then definitely some pressure wave will be generated, and the velocity of the pressure wave is known as velocity of the sound or the speed of the sound. Generally, the speed of the sound can be given by rate of change of pressure with respect to density, rate of change of pressure with respect to density in isentropic flow, my dear. There are assumptions. Whenever you are going to calculate the value of C, value of velocity, then it can be considered there must be only Bundy flow. Then second flow must be isentropic. So the velocity of sound, normal derivation of the velocity of the sound can be given by dP over ds, d rho under the isentropic flow. So this is the one MSQ question may be asked, that what are the important assumptions to drive the formula of the speed of sound in the ideal condition. That one is flow is a steady state condition, second flow is perfectly isentropic flow. Are you getting my point? Perfectly isentropic flow is there, my dear. So this is the velocity of sound. Now what is the speed or the sonic speed in an ideal gas? Then, my dear, sonic speed in an ideal gas can be given by gamma RT, most of the time asking question from the compressible flow. Have you seen any time? कभी कुछ ऐसा formula देखा? Please tell me the answer. Anyone? Any one of you? Yes, at least किसी ने तो देखा. No one is writing. Let me check the comment. No one is writing. कोई तो लिखो. Why you are not writing? Is it the problem from my side? Is it the problem from my side? Okay. No. Okay. Great. No. I'm getting your comment. Nice. Come back. Sir, first formula, it is valid for an ideal gas. Second, in the term of bulk modulus also, just a minute. In the term of bulk modulus, velocity of the sound can be given as K by rho, where K is the bulk modulus. This is normally is the speed of the sound in the liquid working medium. So there are two formulas. Generally for our thermodynamic topic, this formula will be used, and based on this velocity of the sound, sir, what is the speed of the sound? Speed of the pressure wave, na? And one more object is going to travel. Sir, when one object is going to travel into the medium, that will generate the pressure wave. And when you compare your speed of your own object to the speed of the pressure wave which is generated by the object, that is given by a very beautiful number that is known as, कुछ तो नाम दे दो, Mach number. That is given by the Mach number. That Mach number can be defined, Mach Mach number can be defined the ratio of actual velocity to the velocity of sound in the same medium, my dear. Mach number can be given by V, velocity of an object, to the velocity of sound C, or it can be written by velocity of object and velocity of sound will be equal to gamma RT. Most of the time question is asked from this topic that what is the Mach number when a aircraft is traveling with the velocity of 1000 km per hour at the higher altitude of 1 km from the sea level, or higher altitude of 10 km from the sea level, where the temperature is 15 degrees centigrade and gamma is also given at that time. Then what will be the numerical value of Mach number? It is generally asked in the exam, my dear. बहुत important question आपको numerically पूछा जाता है. What is this question related to the Mach number? Now after that, if the Mach number is exactly equal to 1, then flow is known as sonic flow. Mach number is less than 1, subsonic flow. Mach number is higher than 1, it is the supersonic flow. Mach number is higher than 5, my dear, 5, that is known as hypersonic flow. And Mach number is nearby 1. Nearby 1 means 0.95, 1.05. That is known as transonic flow. Yes. What is your doubt, Shruth? Height. Generally, flight travel at a particular height now where the temperature is little bit less. So if it is given that at this height your flight is traveling, where the temperature and pressure and all other parameters are given to us, then in this simple way, my dear, we can find what will be the Mach number at this place. Are you getting my point? What is the numerical value of the Mach number? Listen first this point perfectly. First, height is not required. It is generally mentioned. Height is not required. Okay. Good. First question. From the compressible flow, my dear. First question from the compressible flow. What is the sound velocity? Either in the term of ideal gas equation or in the term of bulk modulus equation. Second important numerical may be asked, what will be the Mach number when it will be given to you. And third and last important point related to the numerical point of view, what is the numerical value of the stagnation property that can be calculated. My dear, if your fluid is flowing in this way and the flow is the isentropic flow, so definitely at this point enthalpy is this, and in this case, my dear, if you don't mind, your velocity is going to increase. Are yes or no? If velocity is going to increase, then definitely your enthalpy is going to decrease. That's why velocity is increased by V2 and enthalpy is decreased by H2. Are you getting my point? Enthalpy is increased by D2, decreased by D2, and velocity is increased. So if I want to know what is the stagnation enthalpy at 1 point and stagnation enthalpy at 2 point, what should be your answer? It must be the same or different. What do you say? Stagnation, total enthalpy. Stagnation enthalpy at 1 point and 2 point must be the same or the different, my dear. Tell me the answer. Must be the same or different? Same. So let's find first of all same. Let's write down first. First of all, what is the numerical value of the stagnation property? Sir, at any point, stagnation enthalpy can be equal to H plus. Sorry, what was the value? V square by 2. Is it or not, my dear? Yes. So first of all, what is the stagnation temperature? Can you please tell me? What is the stagnation temperature in this case? Can we write stagnation temperature H0 means Cp T0 will be equal to Cpt plus of V square by 2, my dear. Can we write from here? T0 by T will be equal to 1 plus of B square divided by 2 Cp into T. Is it? Can we solve this? T0 by T, if I'll write the exact line, it can be written by gamma minus 1 divided by 2 into m square. So, the stagnation temperature can be given by this one, my dear. Stagnation pressure, are you able to find or not? That is equal to 1 plus of gamma minus 1 divided by 2 into m square raised to gamma upon gamma minus 1. Is it or not? So, third important question, after calculating the Mach number, are you able to find the stagnation property when local properties are given to us? Sir, what is the local property? Like H enthalpy, P pressure, T temperature, these are known as local properties, my dear. Local means at any particular point, arbitrary properties are there. And this H0 and this P0 and this T0 are the stagnation properties, my dear. First and the next question, are you able to find convert your local property into the stagnation property or not, my dear? What do you say? Can you convert all the local properties into the stagnation properties? Yes or yes? Anyone? Local properties into the stagnation properties. This is the next question, my dear. This one is the next question. All of you? Great. Excellent. बहुत सही. Sorry. After that, sir, in any isentropic flow, if the property is given at 2 points, point number 1, my dear, and point number 2, sir, tell me honestly, when this stagnation property is going to define the total property. So in this isentropic flow, total stagnation property is not going to change. That's why, if you don't mind, can I write from here that H01 will be equal to H02? Is it or not? What is H01? This one. Can we write from here, from H1 will be equal to V1 square by 2 will be equal to H2 plus of V2 square by 2, my dear. Is it or not? All of you agree? All of you agree from here? Good. T1 plus of V1 square by 2. Sorry, just a minute. Now, from here, if the stagnation property at point number 1 and point number 2 is same, can I also write T01 will also be equal to T02? Are yes or no? Temperature at point 1 and temperature at point 2 will also be same, my dear, but temperature must be the stagnation temperature. All of you, yes or no? What is the temperature at point 1 from here, my dear? What is the temperature at point 1? That value will be equal to T1 1 plus gamma minus 1 divided by 2 into m1 square will be equal to T2 1 plus gamma minus 1 divided by 2 into m2 square. This is the value of the T01 and T02 just right now we have calculated. So from here, are you not feeling? If it is the example of isentropic flow, then we are able to find the value of the temperature at any particular point if we are going to follow the stagnation property. Any doubt? At two important, sir, this property what you have written now, let me tell you, let me clear this difference. Why we are going to do, sir, in this case what T0, H0 or P0 whatever you have calculated, this is the difference between the T0 and T is the local temperature of a state and T0 is the stagnation temperature of the same state. Similarly, if I'll write T1, T01, what is the meaning of this? T1 means local position and temperature is T1. T01 means local position but temperature is stagnation temperature. Similarly, if I'll consider the flow at two important point, my dear, from here I will apply the two important point. If my stagnation property is not going to change in the isentropic flow now, then I can easily write that total stagnation enthalpy will be the same, total stagnation temperature will be the same if the flow is isentropic flow. So in the diffuser, in the nozzle, I can easily apply this concept, my dear. Clear? Are you getting this point? Clear? Yes, exactly. Exactly. Yes, Ruth. Is this point clear? Can we move forward? Yes. After that, so rewrite somewhere if you want. One question related to speed of the sound. Second question, find the Mach number. V divided by under root gamma RT. Third question, find the stagnation property from the local property. And fourth and last numerical, when the flow is flow is isentropic, at two important point of the flow, you can compare both stagnation enthalpy and temperature, my dear. These are the four type of question may be asked from the compressible flow. Numerical question may be asked from the compressible flow. If this point is clear to us, please clear to all, please write in the comment section. First question, speed of the sound, V C is equal to under root gamma RT. Second, Mach number, V divided by under root gamma RT. Third, local and stagnation property relation of a state. And fourth and last, if the flow is isentropic, my dear, then what will be the numerical value of the enthalpy, stagnation enthalpy at one state, two state, three state or any state, that will be the same. What will be the stagnation temperature at one state, 2, 3, 4, 5 state if it is the nozzle. Till now we have discussed everything in such a way. Please write in the comment section if each and every point is clear to all, my dear. Please. Is all clear? समझ आया? Numerical solve कर लोगे? What point are given to us? Let me tell you. Only the local temperature is given to us. Velocity of a vehicle is given to us. Velocity of sound is never given to us. Speed of the sound is never mentioned to us. Yes, local temperature will also given to us. Okay, good. Theoretical question. Best theoretical question from this topic I am going to tell you, which may be asked a lot of time. MSQ question is there, my dear, because if I will write what is the relationship between the change of area and the change of velocity, then it will be given by dA by area will be equal to dV by V under bracket of m square minus of 1. So from this relation, if you want to check what is the change in the velocity and area, that is clearly the function of Mach number. That is clearly the function of a Mach number, my dear. Function of a Mach number. Right. There are few important points. Let me read. In a compressible flow, there are three type of flow, my dear. There are three type of flow in theory. One, subsonic flow, when Mach number is less than 1. Second, supersonic, when Mach number is greater than 1. And third, my dear, sonic flow, when Mach number is equal to 1. When Mach number is equal to 1, 1 and 1 will be 0. No increasing or decreasing is possible. No change in the kinetic energy when the flow is sonic flow. When it is subsonic flow, my dear, then convergent cross-section area, convergent cross-section area in subsonic flow will behave like a nozzle. Means if the flow is subsonic like this, then it will be a nozzle. Okay, it will be a diffuser. When the flow is subsonic, convergent cross section nozzle, divergent cross section is a diffuser. Clear? This is entry, this is exit. This one is entry and this is exit. But if it is a supersonic flow, then convergent is a diffuser, but divergent is a nozzle. Just everything will be reversed. And in incompressible flow, this is all about the compressible flow. In incompressible flow, all the diverging cross section area will behave like a diffuser. All the converging cross section area will behave like a nozzle, because in that type of incompressible flow, there is no change in the density. Density kahin se kahin tak change nahi ho rahi. No density is going to change, my dear. That's why you can simply write like this. Okay. After that, I start the IC engine. First of all, tell me numerically, I'm coming on the same point. Numerically, are you solve these type of problem? Now tell me first, related to the power plant, from which topic you want the questions. Topic I can make. One, my dear, it was the gas power plant or the Brayton cycle. Second, it was the Rankine cycle we have discussed. Third, it was the steam turbine we have discussed. Fourth, we have discussed the reciprocating compressor. Fifth, we have discussed the centrifugal compressor. And sixth, we have discussed right now the compressible flow. From which of the topic you want to ask the question, my dear? Yeah, just let me confirm, Vijay. I'm coming on your point. Don't worry. Okay. Correct. Write down what numerical you want, from where you want the numerical. One is steam turbine. Very good. Steam turbine, Rankine cycle. Very nice. Compressible flow, someone of you say. Okay. Okay, sure. I'll be more focused on the steam turbine and, my dear, compressible flow and on Rankine turbine. Don't worry. Yeah, sure. So I'll be putting more and more problem related to the steam turbine. I'll be putting more and more problem related to the steam turbine, related to the compressible flow for you, definitely. Sure. Okay. Can we continue? You want break again? Can we continue? Again you want break? Continue. Okay. Good. Yes, yes. Sure, Umar. IC engine, let's complete IC engine, and after that we can move forward for the refrigeration. At that time, if you want break, you just ask the break at that time. Don't worry. Okay. Let's complete the IC engine first. It's a very easy topic, my dear. You need not to worry about this. Let's move forward for the IC engine. And after that, we come to the part. Yes. Again, related to the IC engine, we are going to coming. We are going to discuss all the numerical point. How many type of numerical may be asked from this particular topic. How the questions related to theory may be asked from this particular topic. Okay. Right. Sir. First, IC engine. It is the thermodynamic system which convert the chemical energy of the fuel into the thermal energy and then utilize into the mechanical energy. based on the internal combustion engine. These are classified between the IC and EC. We are going to focus mainly on EC engine. Now, first, what is the stroke? Generally, these point we need to know, sir. This point is very important. We need to know what is the total volume. So this one is the volume meter cube per cycle. Let me tell you, most of the time we feel the problem to find the answer, but when you want to convert this meter cube into per second now, then we write, my dear, at that time Vs is equal to pi by 4 d square L into n dash y 60. N dash means number of cycles, and where this n dash can be written like n dash. What is this n dash? N dash is n by 2, my dear, for 4-stroke engine. 4-stroke engine, and n dash will be equal to n for 2-stroke engine. Clear? This point is very important. Here when you write n by 60 now, its unit become meter cube per second. Sir, most of the time from IC engine, question related to the indicated power, question related to the brake mean effective pressure, and question related to the volumetric efficiency is also asked. So when volumetric efficiency, indicated power, mean effective pressure is asked now, at that time you have to compare the volume. Volume means, are you taking the volume meter cube per second or you are taking the volume meter cube per cycle, my dear. So let me tell you, when you multiply with the number of cylinder and all now, at that time you get the volume meter cube per cycle. After that you need to know per second how many cycles are possible, my dear. Per second how many cycles are possible. So that's why you just calculate what is the total volume every second you are going to cover. So in this case, what I'll do, if I want to check the total volume, that will be n by 60, and that can be written, by dear, written in meter cube per second. Clear to all? There is a difference between meter cube per cycle to the meter cube per second. Is the difference clear to all? Umar, Tujis, Surot, is this difference clear to all? First of all, try to make the difference between per cycle and per second, my dear. Otherwise, in volumetric efficiency problem, in mean effective pressure problem, and in indicated power problem, you always feel the problem to discuss the unit. Whenever you want to find per meter, per minute, per second, per hour, everything, anything, at that time, my dear, it is the best way to multiply by n dash by 60. N dash means n by 2 for 4-stroke engine, and n is equal to capital N is 2-stroke engine. Then what is the clearance volume? It is the volume of the cylinder when piston is at top dead center. After that, a very next important point, my dear, after that, compression ratio, main villain of this entire subject. Yes or no? Compression ratio of the IC engine. Generally, when the piston is just sliding between the top dead center and bottom dead center, my dear, is swept some volume. When the volume is swept, then this compression ratio can be given by, my dear, compression ratio can be given by volume before the compression to the volume after the compression. Before the compression will be the example of the total volume, that is VC plus of VS, my dear, and after the volume BC. So the compression ratio can be written by volume before compression and volume after compression. It can also be written by 1 plus VS divided by VC. We can also write like this. After that, let's start to discuss some important cycles, that is one, Otto cycle. Let's know the performance of the Otto cycle first, sir. In this case, again, let me tell you, first what parameter that can be given? Can you please tell me what parameter can be given in this question, sir? Process. What parameter can be given to us? Can I say one important thing related to the IC engine? That is the compression ratio must be given to us. What do you say? Compression ratio must be given to us exactly, yes or no? First of all, you know. So compression ratio is given, my dear. Is it or not? Either directly or indirectly. Sir, how directly? Directly given in the question. How indirectly? It is given like swept volume, clearance volume. These terms are given. You will easily get the value of the compression ratio. Then at that time, what is the numerical value of the efficiency? If I just want to find what is the efficiency of the Otto cycle, can I write 1 minus heat reject divided by heat supply? What is the answer? 1 minus heat reject, T4 minus of T1. What is the heat supply? T3 minus of T2, my dear. Yes. If I want to follow the efficiency of the heat supply, that will be written by 1 divided by R raised to gamma minus 1, where R raised to gamma minus 1 is a compression ratio. So if the compression ratio is known to us, from here we can easily find the numerical value of the efficiency and efficiency of the Otto cycle and compression ratio. If I draw the diagram, then diagram will be somewhere like this. Are you getting or not? If the compression ratio will increase, then efficiency of the Otto cycle will definitely increase. Sir, one more question may be asked from here. What is the net work done in this case? What will be the net work done in this case? If you don't mind, can we write net work done in this case will be equal to P3 V3 minus P4 V4 divided by gamma minus 1 minus negative work, that is P2 V2 minus P1 V1 divided by gamma minus 1. Check. Sir, work done in this process minus work done in this process, because two other process work done are 0. Can we write the work done? P3 V3 minus P4 V4 divided by gamma minus 1, because process is adiabatic. Reversely, P2 V2 minus P1 V1 divided by gamma minus 1. This is the adiabatic work. Say yes or no, my dear. Say yes or no. All of you. Everyone. Is it clear to everyone or not? Can you please write the answer? Is this point clear to everyone? Yes or no, my dear? Good. From here, good. From here, wonderful. What is the value of P3? P3 V3 is V2 into V1. Sorry, into VC, not V1. Just a minute. Into VC. Sorry. Into VC. If you are having any doubt, feel free to ask. The net work done in the Otto cycle can be given by the area of the indicated diagram. That will be written by P3 minus of RP4 minus of P2 minus RP1 multiply by clearance volume. Sir, if you are having any doubt, feel free to ask. In this case, even if you want to move forward, then VC value can also be substituted. Yes, it's not an open system. No, Sujis, it's an example of the closed system. Reason, whenever these all thermodynamic processes are conducted now, then at that time, my dear, inlet and outlet, both valve are closed completely. In the heat addition, valve are closed. In the compression, valve are closed. In the power stroke, valve are closed. So inlet and outlet valve are closed now. That's why you can simply write that this is the example of, getting my point? This one is the example of, my dear, the closed system work done. Sir, two important points are asked. Let me tell you very clearly. One is the numerical value of the efficiency. Numerical point of view we are talking about. One is the efficiency of the Otto cycle. Second is the net work done in the Otto cycle. Can you please write? Can you please thumb up if you are getting these two important questions from here? Yes, please write the answer. If you are getting two important points, one is the efficiency, second is the net work done of the Otto cycle. So two important questions may be asked to us. Yes, one is the efficiency, second is the value of the work done. Please, all of you clear to all? Good. Yes, great. After that, sir, let's discuss the diesel cycle. There are again four important processes in this case. We are directly talking about the numerical part which may be asked from here. Four important processes. Yes. Because in this case, my dear, you are going to take the cutoff of heat supply. Then this point is very important. That is simply known as cutoff ratio. That is rho, my dear. So cut-off ratio can be taken as V3 divided by V2. From here, V3 divided by V2 is the cut-off ratio. After that, TS diagram will be given by this first. Then if I will ask what is the efficiency of the diesel cycle, 1 minus, yes, heat rejection, T4 minus T1 divided by T3 minus T2 into gamma, my dear. Or it can be written by 1 minus 1 upon R raised to gamma minus 1 into rho raised to gamma minus 1 divided by gamma into rho minus 1. Let me share a very important story from here, my dear. First question will be there. How will you find the compression ratio? So can we say compression ratio is already given to us? Please write in the comment section. Can we say that compression ratios are already given to us? Yes or no? Compression ratio will be already given to us. What do you say? Yes. Now the question is there. कमेंट फिर से नहीं आ रहा है. Is it my problem? या आप लोग कर ही नहीं रहे हो? Okay, good. Now, so the main question is compression ratio is completely given to us. Sir, to find the cutoff ratio, there are two ways. To find the cutoff ratio, there are two important ways. How you will find the cutoff ratio, my dear? That is rho. There is one way, that your expansion ratio is equal to compression ratio divided by 2, or your compression ratio, that is R. Just a minute, let me rearrange these all the thing. Your one way is your compression ratio will be equal to rho into expansion ratio. First, this is one way to find the rho value, my dear. Once in the question it will be given that compression ratio is this, expansion ratio is this, then what will be the numerical value of the expansion ratio? Cutoff ratio. After that, because in diesel cycle, cutoff ratio is a very important parameter, because if you once you find the cutoff ratio, then my dear, each and every problem of the diesel cycle you can easily solve. Second, second is cutoff take place at C% of stroke. There are two ways to calculate the value of cutoff. Sometime have you seen that we generally write that cutoff take place at 10% of the stroke. Cutoff take place when swept volume is 10%, like this, 10% of swept volume. So in that, at that time, cutoff ratio can be written by 1 plus C divided by 100, my dear, into R minus of 1. So with the help of these two parameters, if you are able to find the value of the cutoff ratio, then definitely you can solve each and every problem of the diesel cycle. Generally, maximum of the engineer, if having the problem in any part of the diesel cycle, then this is the only part that you all are aware with the efficiency of the diesel cycle, but you don't know how this value of the cutoff ratio will be calculated. Are you getting my point? कैसे cutoff ratio की value calculate करोगे? Getting this point? Is it? All of you? It is clear to all? Good. So, can you solve the problem related to the diesel cycle? Very nice, sir. These points are very important, how you will find the cutoff ratio to solve the problem related to the diesel cycle. Or let me tell you, if the question related to efficiency is asked now, then most of the time question will be asked from the diesel cycle. Why, sir? Because in the Otto cycle questions are very easy if based on the efficiency is asked. Because only you need to find the compression ratio, you substitute the compression ratio in the equation, you will directly get the answer of efficiency. But in the diesel cycle you have to do a lot of things, because rho is never given in the question directly. Either you will find from this first equation relation, or you will find from the second equation relation, or you will find from the basic equation, that V3 divided by V2 will be known as the cutoff ratio. Somewhere like this you can find the answer. Okay. So this is the way you can find the efficiency of the diesel cycle. Let's move forward for the last point, my dear, that is known as efficiency of dual cycle. Dual cycle. Again, PV diagram and TS diagram are given to us. Very rarely, my dear, any question may be asked from here. Reason, if direct formula based question is not given from here, then my dear, every time what exactly you need to do, you have to solve this question for 5 to 10 minutes. So either directly based formula, like where the efficiency of the dual cycle can be given like this, 1 minus 1 divided by R raised to gamma minus 1 into RP pressure ratio into rho raised to gamma minus 1 divided by Rp minus 1 plus gamma into Rp into rho minus 1. So if you are able to recall this formula, my dear, only this will be more than sufficient to solve any problem of the dual cycle region. Because if he is going to ask the problem more complicated than this, then definitely it is going to consume a lot of time. Even you are not having so much of time कि आप इस पे पहुंच जाओ. Getting my point? Okay. So in this case, you must know what is the value of R, that is the compression ratio, my dear. That will be equal to V1 divided by V2. What is the value of Rp? That is the pressure ratio. That will be equal to P3 divided by P2. And what is the value of cutoff ratio? cutoff ratio will be equal to V4 divided by V3. And again, let me tell you, compression ratio will be equal to rho into this. So these all formulas are very well known to us. R is compression ratio, RP is the pressure ratio, and after that rho is the cutoff ratio, my dear. Rho is the cutoff ratio for you. So this is the efficiency of the diesel cycle. Let's know what is the mean effective pressure. The important parameter for you, my dear. Most of the time you have seen the lot of problem from here. What is the mean effective pressure? So it is the hypothetical or imaginary pressure which give you the same amount of the net power output of an actual cycle when you will multiply by the swept volume. Sir, generally you have written the first formula of the mean effective pressure is the area of the indicated diagram. Is it or not? Have you written like this? Area of indicated diagram divided by length of indicated diagram multiply by K, where K is, can you please tell me what is K? Where K is a spring constant, generally a unit conversion constant, my dear. It's a spring constant that can be written by bar per centimeter like this. But you are aware with only a single formula of this P mean effective pressure, my dear. Area of the indicated diagram divided by length of the indicated diagram. But story does not end here, sir. The indicated diagram, if I will define for the Otto cycle, then indicated diagram for the Otto cycle, it will be written like, very important point for the Otto cycle, it is efficiency of the Otto cycle multiplied by change of the pressure during the heat supply divided by during the process 2 to 3 divided by R minus 1 into gamma minus 1. And one more mean effective pressure diagram is already we have proved that P3 minus of RP4 minus P2 minus of RP1 divided by R minus 1 into gamma minus 1 is also the formula of mean effective pressure. Are you aware with these formulas, my dear? Are you aware with these formulas? Please write in the comment section. Yes or no? ये formula आपको पता है ऑटो साइकिल के? तो when you write that mean effective pressure is the area of the indicated diagram divided by length of the indicated diagram, my dear, these points are very general point. ये point बहुत general point है. But nowadays question is not asked up to this simple level. Now he may be mentioned when the pressure of all the point of the Otto cycle is given to us, then find the mean effective pressure. If the efficiency of the Otto cycle is given, change of pressure in this limit is given, R minus gamma, all these value are given. So these are some additional formula you must know whenever you want to go for the Otto cycle mean effective pressure, my dear. For Otto cycle mean effective pressure, if you want to go, then definitely you must know each and every parameter like this. Let's move forward and after that check what is the formula of some important cycles. Okay. Yes. Always. So this is not only the formula, that point I want to know. Even based on this formula, I have given you number of problem lot of time. बहुत सारी प्रॉब्लम दी हुई हैं. In 2-3 session I have just discussed the problem based on the mean effective pressure on the Otto cycle, mean effective pressure on this diesel cycle, like Otto cycle, or mean effective pressure like the common formula. So this is a very generalized form of the formula. This is the specific form of the formula when you will just get the value of the mean effective pressure when these all parameters are given. And this is the problem we feel number of time when in the GATE exam, my dear, or in any complete problem, test series even, some advanced level of questions are asked. So they never write total work divided by swept volume. They always write like this. Sorry. They always write like this. That in the Otto cycle, these limits of the pressure are given, pressure ratio is given, compression ratio is given, then what will be the value of the mean effective pressure, right? Okay, come back. Sir, linear cycle with the Otto cycle, with the diesel cycle and dual cycle, you must be aware to find the efficiency of any cycle, my dear. What is the way to find the efficiency? First of all, you introduce every process. Sir, this is the isobaric process. Isochoric 1 to 2 to 3 and 3 to 1. So in this case, if you want to find what is the efficiency of the linear cycle, 1 minus heat reject divided by heat supply, are yes or no? If after that I want to find the heat reject, my dear, can I write heat reject in this one? Can I write Cp T3 minus of T2 T1 divided by heat supply, that is Cv T2 minus of T1. So in this case, the value will be equal to gamma T3 minus of T1 divided by T2 minus of T1. Yes or no? So in this way, you are not limited. Don't limit yourself up to the efficiency, up to the numerical parameters of a cycle which are very well known to us. कोई नई cycle आ गई तो फंस जाओगे. You must know where the entropy is increasing. If the entropy is increasing in any process of the cycle, that is the blindly heat addition process in the reversible one. Getting my point? So heat is added only 1 to 2, where the heat is rejecting 3 to 1. Apply the formula, you will get the answer. Similarly, if we'll convert the temperature term into the pressure, then we are getting the efficiency in the term like this. We have written like this. The efficiency of the linear cycle, it may be written like this, my dear. If I'll convert T3, T2, then the final term efficiency will be written like this, where the numerical value of the Rp is nothing but that is the pressure ratio. Rp can be written, my dear, pressure ratio that is given from here, that is P2/P1 is the pressure ratio. Is the pressure ratio. So this is a very common formula of a linear cycle, generally asked in the question. Even once it is also asked in your GATE exam. I think in 2004, the question was asked. This was related to 4 marks. First question was PV diagram is given to you and you need to find what is the TS diagram of this question. Okay. Second, my dear, it was asked what is the overall efficiency of the cycle when the pressure ratio was given to us. P2 and P3 was given, P2 and P1 was given to us, and it was asked what is the numerical value of the overall efficiency of the linear cycle. Similarly, there is also one more important cycle, my dear, that is known as Atkinson cycle. Atkinson cycle is just a modification of the Otto cycle. Sir, we are very well aware with this cycle that 1 to, let me change the color, that 1 to 2, 2 to 3, 3 to 4 and 4 to 1 is the Otto cycle. Say yes or no? 1, 2, 3, 4 is the Otto cycle. Now, when it is expanded like 1, 2, 3 and this is 4, my dear, to get the extra work, then the cycle become diesel, Atkinson cycle. So if I will write all the process for MSQ, this question is for MSQ. If I'll write all the process of this Atkinson cycle, my dear, then definitely 2 will be the isentropic process. Can I write 1 to 2? Can you please write what is the process? Sir, isentropic process. Is it or not, my dear? Yes. What is 2 to 3? Isochoric heat addition process. What is 3 to 4, my dear? 3 to 4. Isentropic expansion process. Very nice, very nice. Expansion process. Yes, Sahu. And my dear, 4 to 1 is the isobaric heat addition process. Efficiency is a very important topic for GATE 23, my dear. Efficiency of this cycle is a very important topic for GATE 23. So the efficiency of this cycle can be given by this, means efficiency of this cycle, if you want to calculate, then 1 minus heat rejection, 1 minus heat rejection, that is 1 gamma heat rejection Cp by Cv. Heat rejection will be equal to T4 minus of T1 divided by heat supply will be equal to T3 minus of T2. So in this case, my dear, your efficiency can be given like this, where RE is the expansion ratio and my dear R is the compression ratio. RE is the expansion ratio, RE, that is given by V4 divided by V3, and R will be equal to V1 divided by V2, my dear. Clear to all? This is also the very important formula for your applied thermodynamic topic, my dear, for your IC engine application topic, my dear, that is efficiency of the Atkinson cycle or the efficiency of the Lanius cycle. Clear? Let's move forward and find what is the comparison of the different efficiencies. What is the comparison of the different efficiencies? Sir, when in this Otto cycle there is a case 1, same compression ratio and heat supply. Compression ratio is same and heat supply is also same. So what will be the answer? Efficiency of the Otto cycle will be more than efficiency of the dual cycle will be more than the efficiency of the diesel cycle. Similarly, comparison of the Otto and diesel cycle case 2, the compression ratio is same and heat rejection is the also same, my dear. Same compression ratio means you are having the same compression ratio for the diesel cycle and the same compression ratio for the Otto cycle. What will be the overall efficiency of the Otto cycle, diesel cycle and dual cycle? Can you please tell me the answer? Efficiency of Otto is greater than efficiency of dual is greater than the efficiency of diesel, and I am very sure these all points are very well known to us. When the same compression ratio is there and heat supply or heat reaction is there, then Otto will have the maximum efficiency, diesel will have the minimum efficiency, dual will be in between. Great. After that, if I am having the maximum temperature and the heat rejection is same, my dear, heat supply is more because heat rejection is same. So in this case, the efficiency of the diesel cycle or any cycle will be 1 minus heat rejection divided by heat supply. Heat rejection is the same, which will supply the more heat, that will do that will have the more efficiency. So can we write in this case, my dear, diesel will have the more efficiency, dual will have the less efficiency, and Otto will have the minimum efficiency. Is it clear to all? It is clear to all. Diesel, dual and Otto will be the comparison of the efficiency. After that, my dear, we are coming on the last important parameter of this IC engine topic, that is the performance parameter of the IC engine. Sir, again your complete IC engine is divided into three part. One, numerical part of air standard cycle. Numerical part of air standard cycle, like whatever you have discussed, like the compression ratio, pressure ratio, cutoff ratio, or the efficiency, mean effective pressure. Second, theoretical questions, MSQ, MCQ questions, like comparison of the efficiency between the Otto cycle, diesel cycle or dual cycle after giving lot of important condition. And third and the last important topic, my dear, third and the last important topic is the numerical based on the performance parameter. Like first performance parameter is, my dear friend, is the indicated power, IP. Can any one of you tell me the answer? Sir, IP. IP will be equal to mean effective pressure into area into length into number of cylinder into N by 2 into 60. Similarly, IP is also equal to mean effective pressure into area into length into K into N by 60. Do you know this NY60 is coming for the VS, mean effective pressure multiplied by the swept volume, and swept volume, this was for, can you please write the answer, for 4-stroke engine, my dear, and this was for 2-stroke engine, my dear. Is it or not? Is it or not? Yes. 2-stroke engine, only N, 4-stroke engine, NY2. So this is the IP. Let's come to the brake power, my dear. What is the brake power? That will be 2 pi NT by 60. If we are measuring the brake power with the help of rope brake dynamometer, that will be equal to pi N, and torque will be equal to, my dear, W minus S into D plus small d, where D, capital D is the diameter of the wheel, small d is the diameter of the rope, divided by 60, my dear. Clear to all? Is it clear to all? Let me tell you here, N or NY2 will never come. Only Saho is writing the answer. Where are you, Sujeesh, Vijaya? Where are you? Yes. NY2, N is not there in the brake power, because brake power is just measured from the rotation. That is not like the cycle. Why you are converting into NY2 or N? You must know, because in this case, this, if I'm not going to count the N, my dear, then definitely this is going to tell you the power per cycle. I am converting the power per cycle into the power per second. So this is the brake power, and after that, what is the friction power in this case? After this, what is the friction power in this case, my dear? That will be the value of Fp. What is the friction power in this case? So Fp, or the friction power, can be written by indicated power minus of brake power. Minus of brake power. Let me tell you one more point. Sir, when you write when you write the efficiency of Otto, diesel or dual cycle, and you write work done divided by heat supply, you write now. So this work done divided by heat supply is nothing but this IP divided by heat supply, you write. So there is also one more method to calculate the IP, that whenever you write the efficiency of the Otto cycle, and these all parameters are not given, if efficiency or air standard efficiency is given to us, then this is the best way to calculate the value of the indicated power from the heat supply. Heat supply and efficiency is given to us, then IP can also be calculated, because let me tell you, my dear, what is the IP? IP अगर आप देखोगे तो IP है क्या? What is the numerical value of IP? Yes. What is the numerical value of IP? Sir, this is the power. This is the mechanical work. This is the mechanical work done by the system in the piston cylinder arrangement. So what power is developed at the piston end, that is the indicated power. And this power is also produced due to the heat supply. यही तो power develop हो रही है ना, जो heat supply से आ रही है. So that is the reason, my dear, the indicated power can also be calculated with these formulas, and indicated power can also be calculated from this formula also. Don't forget to write. Don't forget to write again and again these all the points, my dear, because these points confuse you a lot. This N by 2 and N is taken only in case of IP. It is not taken in brake power, my dear. It is not taken in brake power. Okay. After that, what is the efficiency of IC engine? First of all, sir, can we write indicated? Thermal efficiency, 1 efficiency. That will be equal to IP divided by mass of the fuel into CV. Second, brake thermal efficiency. Very good, very good. MCV delta T is not required. Yes, for the heat supply you can also write MCV delta T. Exactly. Either you can use this one or you can use MCV delta T if the combustion loss is 0, my dear. Then and only then you can write brake power divided by MF into CV. Third is mechanical efficiency. Mechanical efficiency. That is V actual divided by V swept. Sorry. That is brake power divided by indicated power. And if I want to write, then brake thermal efficiency is also written as mechanical efficiency into indicated thermal efficiency. So the overall efficiency can also be written if I'll multiply all, then overall efficiency will come, my dear. That is equal to efficiency of this mechanical indicated thermal efficiency into volumetric efficiency. If I consider the volumetric efficiency. And again, what will be the volumetric efficiency? Any one of you aware with it? Already we have written in the compressor. It is not going to change, my dear. Volumetric efficiency in this case can be written what is the actual volume entering into the system, what is the swept volume. Here the unit is very important parameter. Unit will play a very important role in this case, my dear, because this must be meter cube per second, this must be meter cube per second also. So in this case you can also write that this value will be equal to, my dear, mass of the air that is entering into the system into a specific volume of the air that is entering into the system divided by swept volume. You are very well aware with it. That will be equal to pi by 4 D into L. Even in the GATE exam, the similar question is asked. Even in the GATE exam, my dear, similar question was asked. Anyone aware with it? Sujis, Midun, Sahu. Once this question was asked related to the points, my dear. Okay, good. Fifth, volumetric efficiency. Okay, now at last of this one, Mohs test. Sir, Mohs test, it is used for, very good, serious. It is used for, my dear, finding the IP, multi-cylinder engine, friction power and IP also, multi-cylinder engine. First, let me write the step. When all cylinders are working, my dear, measure brake power, cut off cylinder 1, cut off a cylinder then major, yes, yes, yes. One is Mohr circle, second is Mohr theorem. So these two things are different. Mohr circle is the different thing, Mohr theorem is the different thing, right? So Mohr is a name. He has just given the lot of theories, my dear, and Mohr circle is one of them to find the resultant of the tensor quantity. Not only for the stress, it is also valid for the strain. It is also valid for MOI, mass moment of inertia. So my dear, Mohr is a name who contributed a lot in the physics and maths, my dear. So definitely Mohr circle is one contribution of the Mohr. Getting my point? After that, he have just given a lot of theory, like Mohr theorems is also used in slope and deflections. So Mohr test. Okay, this one are you talking about? Okay, sorry. This is Mohs test. Okay, are you talking about this now? This one is Mohs test. Okay. No. It's not same person. It's a Mohr test. By mistake, I have just written the Mohr. Sorry. Anyway, chali. Cut off and then measure the brake power, my dear. Total. So this I will write 1. This I will write 2. Then IP of that cylinder will be equal to total brake power when all are working minus brake power when one is cut off, my dear. When one cylinder is cut off, what is the brake power? So generally you will do like this. You just cut the one cylinder, एक cylinder को काटो, total brake power measure करो. When all cylinders are working, subtract the brake power from that BP and you will easily get the indicated power of any cylinder. When you will get the indicated power of any cylinder, similarly you can also get the total brake power of the cylinder, my dear. Okay, you can also get the total brake power of the cylinder. Okay, next. Let's move forward for the refrigeration. Two topics are left. One is the refrigeration, second is the psychrometric. Length of the topic is not so high, then definitely in next 1 hour topic will be over, my dear. So I think break is not required, Vijay. What do you say, Shreyas, Sojis, Midhun? I think maximum of you have already taken the break. आप लोग आधे से ज़्यादा घूम के आ चुके हो, if I'm not wrong, yes or no? Yes. So hardly 1 hour topic or 1 hour marathon will be there. Then for that, I think no need to take the break. If you want, you write in the comment section, otherwise we can continue. Yes. Okay, good. Great. Okay, sir, I think in refrigeration topic, maximum of you will not feel problem at all. Maximum of you are very well aware with this topic of the refrigeration. Is it yes or no? Okay, let's see, sir. So refrigeration is the process of achieving and maintaining. Okay. Yes. So there are only two in this marathon who have not taken the break. One is you, second is me. There are only two. Okay. Okay, you also. Okay, Sirius, Midhun, and we three are there. Nice. We all three are there who have not taken any break, my dear, till now. Great. Good. After that, sir. So, first of all, you must know unit conversion. Generally, the refrigeration effect is given to us in TR. Most of the time, it is given in TR. First is, if you want, because let me tell you what question are asked. TR are given to us TR value is given to us, and it is asked what is the power input required, my dear. I think the similar kind of problem you are aware with it. Yes. So in this power input, when it is asked, you have to give me the answer of in kilowatt. So whenever TR is given to us, blindly, first of all, what you need to do, you have to convert your TR into kilojoule per second or the kilowatt, my dear. Kilojoule per second or the kilowatt, first of all you need to convert this value, and after that you will start your question. In any refrigeration topic, my dear, when refrigeration capacity or when VAR is given, when refrigerating effect is given to us into the TR, what exactly you need to do, my dear, you convert your TR into the kilojoule per second or the total numerical value of the kilowatt, and after that you move forward. Okay, now after that, what is the refrigerating capacity, my dear? Refrigerating capacity we have already calculated. By calculating the COP, work input to the compressor is taken into the account. So the COP can be given by RE. Let me tell you, COP can be written by two terms. One like the RE divided by work in, my dear. That will be at that time in kilojoule per kg. So at that time this will also be in kilojoule per kg. There is also one method, my dear, to calculate the value of COP, that will be equal to cooling capacity divided by power input. Sir, what is the meaning of it? Cooling capacity will be taken in kilowatt and P, power input, will also be taken in kilowatt, my dear. Power input will also be taken in kilowatt, my dear. Okay. Now, next, what is the ideal refrigeration system? First of all, that is the VAR system, and that is the reverse Carnot refrigeration system. And the reverse Carnot refrigeration system we have already discussed in the basic thermodynamics, that the COP of the reversible Carnot refrigeration system, that can be written by lower temperature divided by higher minus of lower temperature. So this is the ideal refrigeration cycle. Now if you will come to the VCR cycle or to the modification of the Rankine cycle, my dear, then Rankine cycle modification of the Carnot cycle, then, my dear, the modification of the Carnot cycle is the VCR cycle, in which we are having the reversible adiabatic compression process, constant pressure heat addition process, isenthalpic expansion, and after that constant pressure heat addition process. If I draw the TS and pH diagram, my dear, of VCR cycle, if I draw the TS and PV diagram, then this one is the simple Brayton cycle. Sir, why simple? If nothing is mentioned, then you try to enter the refrigerant into the compressor in saturated vapor state, my dear, and refrigerant will leave the condenser at a saturated liquid state. This is the simple VCR cycle you can have. So from here, if I'll write what is the power required in the compressor, can I write mass flow rate of refrigerant into H2 minus of H1, my dear. Second, cooling capacity will be equal to, my dear, M H 1 minus of H4. It will be also equal to M1 minus of H3. Similarly, I can easily write COP of VCR cycle, my dear, will be equal to H1 minus of H4 divided by H2 minus of H1. Are you getting some important point? To find everything related to VCR cycle, my dear, you have to move forward for the previous study, that is the pure substance topic. So if the pure substance topic is clear to everyone, my dear, you are not going to feel at you are not going to feel any problem in the VCR cycle. Each and everything is purely related to my dear your VCR cycle. Yes or no? VCR cycle. After that, there are performance parameter we have already calculated. Sir, this is very important point you need to know. Most of the time, volumetric efficiency of compressor is asked. Sir, because refrigerant is entering into the compressor at a volume of V1, if you don't mind. Yes or no? At this one point, your refrigerant is going to enter into the compressor. So what will be the volumetric efficiency of the compressor? Can we write actual volume entering into the refrigerant, into the compressor divided by swept volume? Sir, what is the actual volume? Can I write mass flow rate into a specific volume that is entering at a point A? And at point A, your actual volume is going to enter into the saturated working condition, my dear, saturated vapor condition, my dear. So this is the actual volume that is going to enter with the meter cube per second, my dear. Getting my point? After that, what is the swept volume of this compressor? Can we write like this? Swept volume of this compressor will be equal to pi by 4 into d square into L into n by 60. Is it or not? This is also meter cube per second, na? So this is the one way to find the volumetric efficiency of the compressor. In general, COP find karna. To find the COP, to find the refrigerating effect, to find the cooling capacity of the working medium is a very easy task nowadays. Most of the student, 90% of the student can solve this type of problem very easily, my dear. Now, some advanced level of questions, Mithun, are asked nowadays that is related to this one. That if the refrigerator is working under this condition, my dear, then what will be the dimension of the compressor? Are you getting my point? So how will you find the dimension? D and L. Whenever volumetric efficiency will be given to us. So first of all, from the problem, you will find the numerical value of the mass flow rate. From the mass flow rate in the steam table or from the refrigerant table, my dear, you will calculate what is the actual volume flow rate that is entering into the system. With the help of this, you will find the total swept volume, and with this swept volume, you will find the dimension of the compressor, my dear. Are you getting my point? You will find the dimension of the compressor. How the dimension or how the numerical value are increasing or decreasing, you will get the idea that what is the diameter D of the cylinder, what is the stroke length of the cylinder when it is running with the m RPM. So this is the equation 1 that will give you the VA, and this is the equation 2. Similarly, there is also one more way to find the efficiency of the cylinder, that will be given by, my dear, P2 divided by P1 raised to 1 by n minus of 1. So you don't stop yourself that compressor is limited up to that topic of compressor. No, whenever compressor is included, my dear, you can apply each and every concept of the compressor in that topic. हर कोई concept वहां पे apply कर सकते हो. Are you getting my point? Either it is related to the compressor, it is related to the refrigeration, it is related to the gas power plant. You will be eligible to apply each and every concept of this compressor in the gas power plant also, in the refrigeration also, even whenever it will be used. Clear? Okay, next. Yes, what is the effect of different parameter on the COP of the cycle? What is the effect of different parameter on the COP of the cycle, my dear? Now, pH diagram I have drawn. Most important question, most expected question as theoretical point of view, my dear. When we are going to increase in the condenser pressure, means first 1, 2, 3 and 4. This one is the original cycle that is working between the evaporating pressure, and this one is working with the condenser pressure. Now try to increase the condenser pressure a little bit, then your condenser pressure will be reached somewhere here, my dear. How much change you are feeling? Let's check the effect, my dear. What are the effect of increasing the condenser pressure? there is the reduction in the refrigerating effect, there is the increase in the work output, there is the there is the reduction in the COP, and there is the reduction in the volumetric efficiency, because condenser means P2 dash divided by P1 is increasing, my dear. Volumetric efficiency will decrease in this case. Very nice. After that, what is the effect on next variation? That decrease in the evaporating pressure. Right now 1, 2, 3 and 4. After that you have decrease by 1 dash, 4 dash, 3 and 4, like this. Okay. What is the effect? Refrigerating effect is decreasing. Work done or the power increasing. COP definitely will decrease, because COP is refrigerating effect divided by work output, and power ratio will increase, my dear. Then what is the efficiency? Definitely decrease. Whenever power ratio will increase, whenever pressure ratio will increase, your volumetric, not total efficiency, this is the volumetric efficiency of the compressor, will decrease. If you want to increase the COP of the cycle, there is only one process, that is subcooling, my dear. If you want to write the effect of subcooling, can you please tell me? If you want to write the effect of the subcooling, my dear, can you please tell me what is the effect on power input? Same now, it is not going to change. What is the effect on cooling capacity, my dear? What is the effect on cooling capacity? Increase. What is the effect on volumetric efficiency? Volumetric efficiency I want to know. Same. No pressure ratio is going to change. Then what is the COP, my dear? Definitely increase. This is the process. This is the modification in the cycle, what exactly you want, in which there is no change in the power, cooling capacity increase. With the cooling capacity, my dear, COP of the cycle will increase, because volumetric efficiency is also same. Yes. Now, modification. Modification of the VCR cycle is the VAR cycle. This is the pressure reducing valve we generally attach, my dear. Yes. After that, what is the modification in VCR cycle we are doing? In VAR system, we are using the low grade energy like the solar energy, like the heat energy, like the heat waste we are using. And in this way, my dear, we are replacing our compressor with the absorber system. What is the absorber system? Can you please tell me? Compressor in this case will be replaced by, very common question of MSQ. Compressor will be replaced by, can you please write the answer? Compressor is replaced by absorber. Yes or no? Heat generator. My dear, heat generator. After that, pressure reducing valve, a pump, pressure reducing valve, and heat exchanger. Even the heat exchanger is not given here, but in the actual cycle, my dear, there is also one more heat exchanger that is applied in between this strong solution and weak solution. So your compressor is the component in the VCR cycle that is replaced by the group of the component in VAR cycle. VR cycle. Clear? What is the COP of VAR cycle? COP of a VAR cycle, ideal VAR cycle, can be given by evaporating temperature divided by condenser atmospheric temperature minus of evaporating temperature multiplied by efficiency of a heat engine. COP, maximum COP of the ideal VAR cycle can be given by COP of a Carnot cycle and the efficiency of the Carnot cycle, right? After that, Electrolux refrigerator, my dear. Very important topic for the MSQ question. Electrolux refrigerator. This type of refrigerator is also called as three fluid absorb system. Three fluids, my dear, are ammonia, hydrogen and water. Sir, in this case, can you please tell me ammonia work as, very important theoretical question, ammonia NH3 work as, tell me the answer, refrigerant. Water is used as absorber. Water is used as absorber. Hydrogen is used as hydrogen. Can you please tell me? Hydrogen is used as, anyone? My dear, hydrogen is used as yes. At a catalyst to increase heat transfer rate. To increase heat transfer rate in evaporator. In evaporator. At a catalyst to use the heat to increase the heat transfer rate in evaporator. After that, VCR cycle we have discussed, reverse Carnot cycle we have discussed, VAR cycle we have discussed, Electrolux refrigerator we have discussed, and my dear, in the Electrolux refrigerator, no pump or compressor is used. No moving device is used. You are not using any mechanical work in this Electrolux refrigerator. Neither compressor and nor pump is used to supply the working medium from low pressure to high pressure, from low temperature to high temperature. It is just maintaining the flow of the refrigerant from lower temperature to higher temperature, or from high density to low density due to the density difference, and for the liquid due to the gravity difference, my dear. Okay. Next. Gas refrigeration system, or simple you can say it is working on which cycle, my dear? Reverse Brayton cycle. A 1 marks question you can expect from this topic. Region newly added topic is there, means not newly added topic, you can say. Just right now or up to this, most of the questions are not asked from here. Either it is asked from the VAR system, it is asked from the VCR system majorly, or the reverse Carnot cycle. But my dear, most of the questions till now are not asked from here. Hardly 1 or 2 questions is asked. So definitely, if any new topic they want to search, this will be the new topic, that is the reverse Brayton cycle, my dear. In this case, if you want to write, so this is the low temperature heat addition, means refrigerating effect. And this one is, my dear, heat supply to the higher atmosphere. So in this case, if I'll write, so the COP of this reverse Brayton cycle, my dear, or gas refrigeration system will be given by refrigerating effect, that is heat supply divided by heat at higher temperature minus of heat at lower temperature. It can be written by MCP delta T, MCP T1 minus of T4, my dear. This will be equal to MCP is common in the denominator, that is T2 minus of T3 minus of T1 minus of T4. If I solve it in the term of pressure ratio, then COP of the cycle, my dear, can be written as COP of this cycle can be written as, that is 1 divided by RP, pressure ratio, gamma minus 1 upon gamma. Please write in the comment section. Are you aware with this formula? Anyone? Have you studied, my dear, this formula? पढ़ा है ना ये? Any one of you? Have you studied these all the formula? This formula related to the gas refrigeration system? Yes or no? You just write in the comment section. Serious? What do you say, Midun? Yes. Very good. Very nice. We have covered already in the theory part. In our paid class, so definitely you all have studied, my dear. Good. After that, refrigerant and the nomenclature of the refrigerant. Very important question. Very important question, my dear. For theoretical part, like these type of refrigerant are written by RAVC, combination of the hydrogen, carbon and, my dear, fluorine. A plus of 1 will be equal to number of carbon. B minus of 1 will be equal to number of hydrogen. Yes, chemistry में भी पढ़ा होगा. Very good. And C as it is the number of fluorine. Even the balancing is not completed, add any component, especially you will focus on the chlorine from the halogen group. Like if it is given like this R12, my dear, so we can easily write R12 means R012. R012. How many number of component of carbon will be there? 0 plus 1 is equal to 1. How many hydrogen will be there? My dear, 0. How many fluorine will be there? C. C is having the one component, one atom, and fluorine is having the 2 atom. That's why you have to add 2 more atom of the chlorine. So the final balancing will be somewhere like this. Fluorine, fluorine, chlorine and chlorine, my dear. This will be CF2Cl2. What is this? Dichloro-difluoro-methane. This will be dichloro-difluoro-methane, my dear. Is it or not? Dichloro-difluoro-methane will be the portion. Methane. Similarly, you can go with this R22. Just try to solve for R22. If any one of you can give me the name. R22. Carbon again 0. Hydrogen 1 and fluorine 2, my dear. Monochloro-difluoro-methane, if I am not wrong. Yes or no? Monochloro-difluoro-methane is the answer. Is it or not? The chemical formula of R22, when you are solving it, you are getting like this: CHClF2, my dear. Monochloro-difluoro and methane will be the answer. Is it? Yes, Midun. Absolutely right. Good. This is the homework question. If you want to solve, then definitely you should solve at your home. R134, C2, F2 and fluorine, my dear, C2, H2, F4. Balancing is completed, my dear. That is tetrafluoro ethane. So this is the nomenclature of all the halogen group you have discussed. You are able to understand, my dear? Yes or no? All the halogen group. Let's come to the next point, that is halocarbons. We have already discussed. Let's come to the inorganic compound. Sir, all inorganic compound, they start with number 7 followed by followed by molecular weight, like R7 followed by molecular weight. For example, R717, what is it? NH3. Very nice, wonderful. R718, my dear, H2O. R744, CO2. R764, SO2. Inorganic compound. They start from letter 7 followed by molecular weight. Second nomenclature of inorganic compound, and after that azeotrope, my dear. Azeotrope mixtures or azeotrope refrigerant are generally the combination of two halocarbons. That is the reason azeotropes are also known as the halocarbons. वो halocarbons ही होते हैं. Two halocarbons in combinations are combined and they make the azeotrope. R500, R300 and R507. These are the combination of the azeotrope which are completely ready from these halocarbons group, my dear. ये सारे के सारे किससे तैयार हुए हैं? Halocarbons group से तैयार हुए हैं, all azeotrope. So, and again there is also one more series, that is the 400 series, is known as the zeotropic refrigerant. This is the nomenclature of all the type of refrigerant. From here, my dear, we all are going to start, all are going to start the last important topic of your applied power plant, that is nothing but the psychrometric. Sir, you just share the session once, otherwise your friend फिर again आपको परेशान करेंगे, because the last topic is going to start. Let me ask if anyone of your friend want to discuss, नहीं तो कुछ देर के बाद फिर से वही क्वेश्चन लेके आएंगे, that we are facing the problem in this topic of psychrometric. Hardly 20-30 minute topic is left, my dear. We are coming back with the same concept. Yes. Okay. नहीं वो वही करते हैं सारे. Okay. Let's start the topic. Take a drink if you want, tea or coffee, whatever you want, because near about 30-40 minutes will be left, my dear, will be taken by this topic, and after that we are able to complete the entire applied thermodynamics. Definitely a little bit lengthy topic, you all are able to feel, but sometime it will make the difference. Okay. Yes, okay. This topic is skipped because for the GATE exam, yes, it's not so much of important, my friend. Definitely I'll take 1-2 questions related to the choking of the nozzle. Yes, you reminded me somewhere, but I forget in the IC engine, if I'm not wrong. Otherwise उसी time पे किसी ने doubt पूछ लिया था. Anyway, definitely I'm having few important questions related to choking, but again let me tell you, not so much important for the GATE exam. For the ESC exam, it is the most important topic, my dear. Yes. Convergent, divergent, nozzle, like, yes, for the GATE exam, it is one of the, for the ESC exam, one of the important topic, my dear. Chali. So let's start the topic. Oh. Yes. Psychrometric topic, my dear. Again, you have to divide this topic into two parts already before moving forward. One purely related to the numerical, second purely related to the, okay, serious, I am back, Gabbar, good. Second, related to the theoretical part. Yes. Yes. Okay. Kabhi. That point definitely I'll share. And I'll put approximate 1 to 2 marks. Come back. Question. Come back here, sir. What is the psychrometric topic? It is the branch of science that which deal with study of the moist air. Moist air means dry air plus of water vapor, or simply you can say humidity. Sir, before moving forward, you need to know few important points like all temperature in the psychrometric, because this is the only point where more than one temperature are used to define the same state of the working medium. Means at the same state of the working medium, my dear, dry bulb temperature may be different, wet bulb temperature may be different, and at the same time your dew point temperature may be different, may be same or may different, because it will be same, it will be a condition of the saturated temperature or saturated air, my dear. Sir, try to understand this point in very clear way. Coming on the same point, Vijay, our target should be something like this, that from the psychrometric topic, at least one question is sure. So if one question is sure, this is short, one question at least, minimum to minimum, my dear. So we should cover each and every part, I mean numerical part also, theoretical part also, understanding part also, every part we should cover in such a manner, my dear, that nothing is going to skip. Okay. Good. Let's come to the point. First of all, let's try to know what is the meaning of this point. Sir, what is the dry bulb temperature and what is the wet bulb temperature and what is the dew point temperature? Dry bulb temperature is the temperature of simple atmosphere. You just expose the atmosphere into the open air, then temperature measured by the thermometer will be the perfect example of dry bulb temperature. After that, when the wet cloth is wrapped, I think I have already shown this dry bulb temperature and wet bulb temperature measured device, my dear. Yes, I am coming on this point. For all 8 the process, na, I just covered this. These all the process in numerical as well as theoretical way, my dear, in this same session. Definitely देखते हैं, उसके बाद देखते हैं ना कैसे नहीं आएगा. First of all, let me introduce one point for you, that is the numerical point, and after that we are coming on the theoretical point, my dear. Come back to the point, sir. Wet bulb temperature, a wet cloth over the thermometer is wrapped, and when air is passed over the thermometer, what temperature is measured, my dear? That is the wet bulb temperature. And what is dew point temperature? Dew point temperature is the temperature so that you will start to decrease the temperature in such a manner, my dear, so that steam or the water vapor mix in it start to condense. Okay, good, serious. Start to condense. But let me clear this point. This must be condensed in constant pressure process, my dear friend. In constant pressure process, you condense this or you decrease the temperature of the atmosphere. Let me share this perfect example right now. Where you all are living. If you are living in North India, right now I am living in Gujarat. So there is no condition of the fog in Gujarat, my dear, especially in Ahmedabad. No cold weather, nothing. But if you are any one of you living in the North India, my dear, then right now there may be the temperature of 20-30 degrees centigrade. Right now I don't know, but you know very well. But tomorrow in the morning, temperature will start to decrease continuous. When this temperature will start to decrease continuous, my dear, then definitely there will be a limit at which water vapor which is already mixed into the air, that will start to condense and it will start to convert into the fog or the dew, you can say, in the morning time. Why? Because temperature you have decreased in isobaric process. Why isobaric? Because from today to tomorrow, pressure of the atmosphere is not going to change. So temperature that is changed, my dear, in an isobaric process. Are you getting this point? So the temperature at which the water vapor which is already mixed into the air start to condense, that is known as dew point temperature. Is this point clear to all? Dew point temperature is clear to all. So this is the experiment, my dear, you have to do to measure the dew point temperature. But with the help of the sling psychrometer, you can easily measure the dry bulb temperature and wet bulb temperature directly. So if I will talk about any numerical measured value, then my dear, you are having two important value. One is known as dry bulb temperature, second is known as wet bulb temperature. These values are known to us, measurable to us. You come with the sling psychrometer, you can directly measure the dry bulb temperature and wet bulb temperature of any position. There are few important points related to temperature are asked, my dear. Wet bulb depression. These are nothing but, this is the difference between the dry bulb temperature and wet bulb temperature, my dear. Similarly, dew point depression. This is the difference between the dry bulb temperature minus of dew point temperature. Okay. The air are generally having two types. One is moist air. My dear, second is saturated air. What is the saturated air? Right now in our atmosphere or in our room, my dear, either you where you are sitting or this, most air is available. At least in my room, most air is available. Reason? Because there is no dew, there is no fog here. So if I will spray in my room the water, if I spray the water in my room having the same temperature at the temperature of the atmosphere, at the temperature of this room, my dear, then some water vapor start to mix into the air, and this will be a process at which your air will be saturated when he is not going to add any water content into it. So what is the process? What is this process? If you want to make the moist air into the saturated air, what process you have conducted? Have you not felt that process was isothermal process? Is it or not? So when moist air is converted into the saturated air, then it is the isothermal process, and when moist air is converted into the saturated air in isobaric process, this is the dew point temperature. Okay, so something is clear to you. In isothermal process, if you spray the water vapor, then it will be the saturated condition can be achieved. And in isobaric process, if you will cool the air, it will be the dew point temperature we can achieve, my dear. Two important parameters we can very easily achieve from this condition. Okay, next. Let's find some numerical parameter from here. How you will find the numerical parameter? Sir, generally one numerical questions is asked related to numerical property of the system. You know very well that this one is a system, like this is the volume. In this volume, my dear, few drops of dry air is mixed like this. Few drops of dry air is mixed like this, but in the same mixture, few drops of water vapor is also mixed like this, like this. So this one is the mass of the dry air, and my dear, this one yellow color is the mass of vapor. Can you please tell me in general, mass of the vapor is higher or mass of the dry air is higher? Dry air means combination of all the gases. Mass of dry air is higher or mass of vapor is higher? Dry air. So definitely pressure of the vapor will also be lower. Pressure of the dry air will also be higher. Temperature, because they are in equilibrium, they are in same. Temperature is same. Volume is same. Volume is same. And the value of the R, specific gas constant, RV, and this is RA, my dear. Now, first of all, if I apply the Dalton's law, that can be written by PV. PV means barometric reading will be equal to air pressure plus of vapor pressure, or air pressure, dry air pressure can also be written by barometric pressure minus of pressure of vapor, my dear. Partial pressure of vapor, this is equation 1. Now, if the question is asked what will be the pressure of the dry air, you can easily write like this. Now, second is what is the specific humidity or the humidity ratio or the moisture content per kg of dry air, my dear. In the moist air, what is the moisture content per kg of the dry air? So can we write this is kg per kg of the dry air. This is the amount of moisture content or available in the mixture. Like this. Now, sir, in this case, what is this vapor pressure? Unknown quantity for me. Or what is this PV? PV is the barometric reading. So this one is very clearly known to me, my dear. Very clearly known to me because it is the atmospheric pressure. After that, sir, if this unknown quantity PV is known to me, then I will be able to find the value of the pressure. First question mark to find the numerical value, my dear. I don't know the value of PV. Similarly, what is the specific humidity or the humidity ratio when it will be perfectly saturated? WS. In this case, PV. So when you will start to spray the water in the isothermal process, my dear, there will be a condition when your water vapor will start to add into the system, and in this case, my dear, pressure of the partial pressure of the vapor will start to increase, and at the condition, my dear, where the air will be saturated, that increased pressure will be converted into PS. जो आपका increase वाला pressure होगा, that will be converted into PS. So again, it is also the unknown quantity. Clear or not? From here, if I'll see the next question, what is the degree of saturation? This is the humidity of the moist air and humidity of the air when it is saturated. After that, what is relative humidity? Again, from the relative humidity, my dear, question mark is how will you find the PV? How will you find the PS? Next, if I will find the density of the water vapor, W is the specific humidity, PB barometric reading, PV is the partial pressure of vapor, and my dear, R and D is the dry bulb temperature. Even till the 6th point, if I am able to know the value of vapor pressure and saturated pressure, we will be able to find the numerical value. After that, what is the enthalpy of the moist air, my dear? Enthalpy of the moist air can be given by the first formula like this, and the second formula is the approximate formula. So, can you please tell me which formula will be used when? Sir, the first formula you will use when dew point temperature is given. Second formula you will be using when dP is not given. Okay. When dew point temperature is not given, you are using the second formula. When dew point temperature is given, you are using the first formula. Clear? Dew point temperature is given to you. Dew point temperature, if it is not given to you, then you will be using the first formula. So from all the parameters, we are getting one important point, my dear, that if you are able to know the value of PV and PS, ये दो वैल्यू मुझे पता चल जाए ना, I'll be able to find the value of all numerical points. Let's know from the steam table. Sir, from that partial pressure, what I have done, I have just located my point like this. At a given pressure of partial pressure of vapor and the drivable temperature, I have located my working medium as a vapor. Here at this point A. Now, sir, if you move isobarically in this way, can you please tell me what temperature you will get? You will get the temperature, dew point temperature. If you move isothermally, my dear, isothermally, then your vapor or your air will be saturated air. Regarding this, what pressure you will get, my dear? Regarding this, what pressure will you get? Sir, saturated pressure. If you will move adiabatically like this, then what temperature will be this? This temperature will be vat bulb temperature, and this pressure, my dear, will be the PW. So if you want to find what is the value of PS, what is the value of PW, what is the value of PV, my dear, that is clearly dependent upon the temperature and the steam table. How, sir? Check it. PS is the saturated pressure corresponding to drivable temperature from the steam table. Sir, if you want to know the saturated pressure na, PS, then go to the steam table, check the second column. In a given temperature, in the second column, saturated pressure is given, that is PS. If you want to find the PV, my dear, go to the steam table. With regarding this dew point temperature, check the second value, that will be the vapor pressure. Similarly, for the PW, my dear, saturated pressure corresponding to W, from the steam table you will get. So, are you not able to find these all the values? If you find these all the values, in the previous case, my dear, PV and PS is not known, you can substitute all these values, you will get the very easily answer of all numerical parameters. सारे numerical parameters के answer आ सकते हैं if you will utilize these all the points, my dear. Getting this point? Yes. If I'll write at saturated point, very good. Yes, I'll share this PDF. First of all, Vijay, is this point clear to you? So you was also asking in the starting, sir, PW will be more than dew point temperature but less than saturated temperature. Getting my point? More than vapor pressure but less than saturated pressure. Good. Next. My dear, for saturated air, very nice. For saturated air, my dear, air, drivable temperature, dew point temperature, vat bulb temperature, both are same. Getting my point? And what will be the numerical value of the relative humidity? Can you please tell me the answer? Relative humidity numerical value, my dear. 100%, na? 100%. 100% will be the relative humidity in this case. Now, psychrometric chart, sir. Psychrometric chart, sir, how any numerical property increase, because from here major portion are the MSQ question. Major portion whatever we are going to cover are related to MSQ question. Very minor or very few questions are the numerical questions we are going to discuss. We are going to move forward, my dear. Major and major problem are related to the theoretical portion. All the process you were asking in the starting that sir theoretical question में बहुत ज़्यादा problem हो रही है, we are not able to solve. Whenever you discuss this the psychrometric chart, different psychrometric process on this chart, you will be able to solve each and every problem directly, my dear. First of all, you must know some line, few important line you know. So this diagram is clearly specific humidity on the y-axis and my dear dry bulb temperature on the x-axis, constant dry bulb temperature vertical. Second, at this point my dear, there is also barometric reading that is going to tell you the vapor pressure of most air. This one. Is the saturated pressure, my dear, or saturated air line that is going to move like this. Move like this. This is the psychrometric chart. So sir, from here I will take two lines every time. Session is over now or going still? Sir, yes, session is hardly 20-30 minutes left. And after that it will be over, my dear, because this is the last topic, psychrometric and psychrometric process. Okay, good. Sir, first of all, these dotted lines are the constant dry bulb temperature line which are moving from left to right, which are increasing from left to right. Okay, first line. Second, these lines, inclined lines, my dear, are the constant specific line which are increasing from left to right. These are constant WBT line, my dear, which are increasing from left to right, which are increasing from left to right, like this, right? Increasing from left to right. Like this. After that, sir, the value of RH is equal to 100%, my dear, here. And after that, when you are moving inside, relative humidity is going to decrease, going to decrease, going to decrease. Only you must be aware with these all the lines, all important process. After that we can draw it. Like, so this is the vapor pressure. Let me tell you, like, there is one process that is sensible heating process. What is the meaning of the sensible heating process, my dear? That there is one heating coil like this. There is one heating coil, my dear, and cold air, very cold air, at a temperature of dry bulb temperature DT1 is going to enter, and temperature of the working medium in this fluid is DT2 3, and the air is going to leave the system, my dear, with the temperature of DT2. Are you getting my point? Are you getting? This was the question from your side, that you are not able to understand how the properties are going to increase, my dear. So just try to feel it is the example of the sensible heating, my dear. Sensible heating means air is going to enter and the same air is going to leave the system, because the working medium is following in this case. That's why it is not mixing into the air. Are you getting my point? So mixing, it is not mixing. That's why humidity is not going to change. Humidity means mass of water added or subtracted. No added, no subtraction. That's why. And dry bulb temperature is increasing. Process will be somewhere like this. Is it okay for you? Tell me the answer, Vijay. Is it okay for you? Yes. After that, let me ask you important question and see how you are not able to write the correct answer in this case. Let me ask you important question to you, my dear. Effect of sensible heating. नहीं है क्या विजय? Good. Now you give me the answer. Sir, let me ask one question. What is the dry bulb temperature? Are you not feeling it is increasing from 1 to 2? What is RH? Sir, it was the RH and this was the RH. What is the relative humidity? What do you say? My dear, relative humidity. I mean increasing, decreasing or constant? RH Midun. Definitely decreasing. Vijay? Yes. Sir, specific humidity. Specific humidity, this line, my dear. Same. After that, dry bulb temperature, my dear, inclined lines are dry bulb temperature lines. Sorry, by mistake, it is drawn wrongly. Check it. Yes, please. This WBT, bat bulb temperature, my dear. Are you not feeling it is increasing? Because this line is increasing from here to here. If it is a 40, my dear, then definitely it is equal to 50. Increasing. Very nice. Very nice. After that, what is dew point temperature? Sir, to check the dew point temperature, you have to move horizontally and touch this saturated point. So, what is this dew point temperature? Not going to change. So, dew point temperature is ultimately the indication of specific humidity. If the specific humidity is changing, then definitely dew point temperature will change. Specific humidity constant, dew point temperature will be constant. Okay. Similarly, if it is the reverse question, it was the question. If it is the reverse question, question of cooling, definitely you will be able to give me the answer. Now, after that, when sir air is passing over it, then heat supply should be T1 minus T3 or T3 minus T1. But in this case, heat is supply only this one. So after that, again, when actual is not equal to ideal, then definitely a very important point is coming, my dear. That is the efficiency of heating coil. Efficiency is coming in this case, my dear. That is the efficiency of the heating coil. That also can be write actual heat transfer to the ideal heat transfer. Actual is TD2 minus of TD1 ideal heat transfer, actual heat transfer, and TD3 minus TD1, it's an actual heat transfer. So TD3 minus TD2 is not converting into the heat transfer of the working medium. That's why some energy is bypassed, some energy is not going so into the system. So bypass factor will be equal to amount of the heat that is not converted into the system, TD3 minus TD2, that is bypass, loss of the energy, TD3 minus TD1, or it can also be written like 1 minus efficiency of coil. So my dear, these type of numerical question may also ask from this important topic, that is different process on the psychrometric chart, different process on the psychrometric chart. Let's see the second process. Let's see. Sir, humidification process. Sir, what is the meaning of the humidification process? Let's try to understand. Humidification, right now I have told you, same temperature, at the same temperature, start to spray the water vapor on the air, then definitely temperature is not going to change, but other parameters are going to change. So in this case, if I'll ask, my dear, first let me ask, what is the specific humidity? Definitely it is going to increase. Dry bulb temperature, dVT, it is same, my dear. Are you getting this point? It is same. After that, dew point temperature increase. As first of all, you have to move like this. Right now you have to move like this, increase. After that, my dear, WBT, increase. And at last, my dear, what is RH? Relative humidity. Anyone? RH. In the starting, this was RH. In the last, it was RH. Tell me the answer of this question, my dear. What is the numerical value of the RH, my dear, in this case? What is the numerical value of the RH in this case? Decrease. Vijaya, is everything fine? Are you getting the answer, my dear? Good. Great. After that, let's come to the next question, that is heating and humidification. Heating plus humidification. Sir, what is the meaning of it? Air is entering into the system like this. Cooled air is entering into the system at a temperature of TD1. Like somewhere here air is there, my dear. At a temperature of TD1, air is there somewhere like this. At this state 1, my dear. Now, after that, very hot water at a temperature of TD3 is sprayed over the cold air. Then at this point, when the air is leaving, are you not feeling a temperature will be a little bit more with some addition of vapor? So the next condition, temperature will be high, but my dear, humidity will also be high. The next process will be somewhere like this. Any doubt? Please. This is non-H, which is increasing the temperature only. This is non-H sensible heat. This is non-H latent heat, my dear. This is the point A, where the enthalpy will be written like this: H1 enthalpy, this H2 enthalpy or HA enthalpy, and this is H2 enthalpy. Any doubt? Can you write the answer? Which property is increasing, decreasing, or remain constant? Are you sure now? Are you sure to write all the parameter? Which property is increasing, decreasing, or remain constant, my dear? If just I want to know the effect, my dear, are you able to 100% write? Are you 100% sure that you can write the answer of each and every point? Like first, what is the dry bulb temperature? Definitely increasing. What is the specific humidity? Definitely increasing. What is the WBT, my dear? WBT, definitely increasing. After that, what is dew point temperature? 100% increasing. I mean increasing, not 100%, sorry. After that, what is RH? Relative humidity. It may increase, or it may decrease, or it may constant. Yes. No. It will be somewhere like this. Constant, increase, decrease, or constant. Why, sir? These are the curve. These are the curve, no? So if it is touching at the same point, like this. So if it will touch, this is the line of same R constant. So if this point and this point are touching to each other, RH constant. This point is shifted this side, RH increasing. This point is shifting this side, RH decreasing. Why it is confusing? You are getting the answer. This is the answer, my dear, not a confusion. It may increase, it may decrease, or it may be constant. Clear to all? Vijay, serious? Is it clear to all, my dear? Yes. Very nice. From here, when we are having the sensible heating, similarly, we can have the sensible cooling also. Why the sensible cooling, sir? Means if you are spraying the water vapor or the water in such a manner, from here, my dear, such a manner, if you are going to spray the water, that is temperature of the water is less than dry bulb temperature of the air that is going to enter, but more than dew point temperature of the air. Why more than, my dear? Why it is more than? Because if it will be less than dew point temperature, then air or the water vapor, it starts to condense. This will be the process of the dehumidification. You are doing the humidification by mistake at that time, my dear. Process will be dehumidification. So in this case, when this temperature is lower than the dry bulb temperature, then T2, my dear, with what temperature this air will coming out now, that will be lower than the dry bulb temperature. Lower than the dry bulb temperature, but higher than the dew point temperature. Humidity will be added definitely. Like this will be a process, my dear. 1, 2 and 2A. This will be the process. Again, I am very sure you all are able to write the correct answer. Yes or no? If I'll ask what will be the effect of this process, my dear? What is the effect of this process? Can we write the numerical value of the RH? Increase. dPt, dry bulb temperature, decrease. No, sorry, increase. Dry bulb temperature, increase, sorry. Dew point temperature, increase. Dry bulb temperature will decrease. Specific humidity will increase. Once specific humidity will increase, H may increase or may decrease. It not be constant, because constant is the condition of a point, my dear. और वो condition किस point की है? When the same water is recirculated again and again, and that condition is known as adiabatic humidification. That condition is known as no heat gain or no heat loss humidification. So it may be increase or decrease, but not constant. After that, if we write what is the, yes, dPt will decrease. No, dPt will not decrease. Reason? For this one, my dear, dPt will be this one. For this one, dPt will be this one. Okay. So dPt is increasing, because dPt ultimately the function of specific humidity. Specific humidity is increasing. Then your moisture percentage is increasing, partial pressure is increasing, dew point temperature is increasing. Getting my point? Yes. Okay. At last, what is the dry bulb temperature, my dear? It will definitely decrease, because it is the process of cooling. From this, there is a one important concept of the sensible heat factor. Then, my dear, sensible heat factor can be written by sensible heat divided by sensible heat plus of latent heat. In the term of enthalpy, it can be written as sensible heat HB minus of HA is the sensible heat, but HC minus of HA is the latent total heat. So the sensible heat factor can be given by this. This is the amount of the sensible heat factor. We can also write a very small numerical point is given to us. We can easily calculate, my dear. After that, what is the adiabatic dehumidification process? Yes, what is the adiabatic dehumidification process, or by air washer, my dear? When the same water is again recirculated again and again, like this. Again and again when it is recirculated, and in this case, my dear, temperature of this TD3, temperature of this spray water now, if it is less than dry bulb temperature, more than dew point temperature, but equal to WBT, then at that time, my dear, adiabatic humidification process is achieved. Adiabatic humidification process is performed. In this case, if it is coming with the TD3, if it is coming with the TD1, my dear, if it is going out with the TD2 like this, then the process can be represented like this, in which if I just want to know the effect, what is the effect? WBT 100% constant, not going to change, my dear. Dry bulb temperature decreasing, my dear. Dew point temperature increasing, my dear. Specific humidity, increasing. RH, increasing. After that, enthalpy, constant. These all important processes are the example of this adiabatic humidification process. No gain or no heat is there, my dear, in this case. No, neither gain nor there is the heat loss. Total heat transfer will be the zero. Process will be the adiabatic process. But in this case, the water what is recirculated again and again, the temperature must be same. So in this case, WBT at the outlet and the WBT at the inlet will be the same, my dear, of this air. Dry well temperature will definitely decrease or will definitely change, but WBT is not going to change similarly. There is also one more example of the chemical dehumidification process. Sir, chemical dehumidification process is just a reverse, means when the air is passed over the silica and alumina, my dear, which is having the attraction towards the moisture, then the silica gel and alumina will absorb the water vapor and the process will be just reverse of this one, where you can write the dry well temperature, my dear. What it will be? Increase or decrease? Increase. After that, what is the WBT? Same, my dear, no change. Is it or not? Where the specific humidity, my dear, it will be decreasing. Where the relative humidity, my dear, it will be decreasing. Where the enthalpy, it will be same, and where the dew point temperature, it will be decreasing. First of all, it was the dew point temperature. In this process, it is the dew point temperature. Definitely decrease. Vijay, now is everything okay? This was the doubt you were having in the starting. Now is everything clear to you, my dear? Ab okay hai sab? After that, there is the last important process related to this, mixing, or you can simply say adiabatic mixing, sir. Whenever to complete a stream of air are mixed, so can we write from here that total, if I'll write the conservation law of mass from here, my dear, can I write, if I will write the conservation law of mass, if I'll substitute, can we write like this, that total M1 plus of total M2 will be equal to M3, my dear. That is the outlet. Just a minute, give me 1 minute only, Vijay. Total means dry air at 1. It will be written like 1 plus of the W1 plus dry air at 2. It will be written by 1 plus of, my dear, W2, and it will be equal to Ma3, and so 1 plus of W1, where A is the clear to all? Is it clear to all? Yes or no, my dear? In this, are you feeling any problem? So are you not able to find when mass at the inlet of the dry air is given, mass at the inlet of the dry air is given from the second stream? Are you able to find what is the mass at the outlet, or what is the humidity at the outlet of the working medium? Yes. At last, if we are able to apply the conservation law of energy, my dear, energy. Sir, can we write this is coming with the enthalpy of Cp Td1 plus of W into enthalpy of vapor plus Ma2 Cp Td2 arrival temperature plus, means this is the enthalpy of air plus this one is the enthalpy of vapor, my dear, is equal to Ma3 Cp of Td3 or Td3 plus of W3 already you have calculated by Mv3, my dear. This is the total value of the enthalpy we can found at the outlet of the system. Yes, please feel free to write if you are having any confusion in the second equation, that is the conservation law of energy we are going to apply here. So total energy at the inlet from one stream, total energy at the inlet from the second stream, total energy at the outlet from the exit stream. So this is the conservation law of mass and conservation law of energy, with how much mass flow rate dry air is entering in both the extreme, like this Ma, Ma2, H1, S2 is also given to us. If we are able to find these all the solution, then definitely in the adiabatic mixing there is no issue at all. Yes, your doubt is, sir, in cooling and dehumidification process, let me go back, cooling and dehumidification process, there is no dehumidification. Cooling and humidification process is WBT. You are asking what is the effect on the WBT, my dear. Where is the WBT? I have written. I have not written WBT. Getting? Cooling and humidification process. RH is this, DPT is this, DBT is this. Okay, okay. I have not written WBT. Then WBT is required to write here, my dear. Yes. Yes, it may increase or decrease. Absolutely right. Yes, yes, absolutely right. It may increase or decrease will be the answer. I just forget to write it. So this is all the thing we have discussed regarding the numerical point of view of enthalpy. Sir, we have started the point from the gas power plant. After that we have discussed the steam power plant, then a steam turbine, then reciprocating compression, then centrifugal compression, then compressible flow. After that IC engine, performance of IC engine, then refrigeration, VCR cycle, VAR cycle, gas refrigeration system. After that, my dears, all the refrigerant, nomenclature of the refrigerant, finally all the psychrometric basic term, numerical value of the psychrometric term. After that, my dear, psychrometric chart. After all the different process on the psychrometric chart we have discussed, and at last we have written the solution for all the different process in the psychrometric chart. In this way, my dear, the topic of applied thermodynamics is also over. I am planning to have some question related to the applied thermodynamics. Few of your friend already text me in the comment section that, sir, you can just take some more questions related to some particular topic. I'll mix these all the questions, either I share in the Telegram channel or I may have one important session for the question if you want to join in definitely 1 or 2 days. Yes, definitely I'll arrange that part. Sure, Vijay, I'm having these important questions related to the nozzle and convergent nozzle, definitely. So see you again. Thank you all. It is near about 6 to 7 hours of marathon. You have shown a lot of energy. Few of you are starting or you are here from the starting. कुछ लोग जा चुके थे, कुछ लोग हैं, but there are very few who have just started the session and just you are going or leaving after winding the session, my dear. So thank you all. Take care. Bye-bye. Be energetic. Work hard till the last date of the exam, because until unless something not go wrong, तो आप जो मेहनत कर रहे हो ऐसा नहीं कि वो आपको धोखा दे देगी. Work hard and definitely will meet you again in the next session, my dear. Thank you all. Bye bye. Take care. See you again, my dear. Just like the session. उसके बाद फिर से next session में मिलते हैं. Thank you. Take care. Sure, I'll share the PDF in the group.